Okay, thank you. Thanks very much for the introduction, and thanks to the organizers for putting this on. So I will give you a review of changes in the coupled Antarctic climate system in models and observations. There we go. Okay, and I will do this in three parts. The first, a review of the observed changes. Then I'll discuss some of the mechanisms proposed for muted Antarctic warming. And then in the third section, I will talk about model observation discrepancies with a focus on sea ice. I still can't advance the slides.
I can advance them for you.
Okay. Next slide, please. I think we missed one, sorry. There we go. So first, I'm showing here the 2-meter air temperature average south of 60 degrees south in 3 different observational products. This is GISTEMP, ERA 5, and JRA 55 across the satellite record. And in these 3 products, we have a weekly positive trend, but you can see that there's very large interannual variability, some observational uncertainty, and the trends are only significant at around 90%, and this varies a little bit between the different observational data sets. If we look at the trends, for example, in ERA 5 vertically, this is latitude against pressure, you can see that globally we've had warming throughout the atmosphere. In the Arctic, you see this especially close to the surface, but at southern latitudes, we don't have significant trends. Turning to the spatial maps from these 3 different observational products, this is averaged over 79 to 2022. You can see that this pattern is very heterogeneous, and there's quite a bit of observational uncertainty between these 3. They generally agree on aspects of cooling in parts of the Southern Ocean and then warming in the Antarctic Peninsula region. If we turn to station-based data, we can go further back. This is the Southern Annular Mode Index from Gareth Marshall. And you can see that this has trended more positive in recent years, especially after the late 90s. And this is associated with a strengthening of the westerly winds and move towards poleward. This belt of westerly winds has moved more polewards. The changes in the SAM are a combination of impacts due to ozone depletion, which we think was particularly pronounced before about 2010, and greenhouse gases. And so the balance of those 2 different forcings will determine how these westerly winds change in the future. Besides the more positive southern annular mode, there's also been a deepening in the Amundsen sea low, especially in more recent years, and this has been linked to the sea ice reductions. Other work has highlighted the importance of the interdecadal Pacific Oscillation, potentially particularly for sea ice expansion, and other work has highlighted the role of ENSO in determining Antarctic climate variability. Here I'm showing the changes in the Southern Ocean sea surface temperatures, averaged over 50 to 65 south. And this is from NOAA ERSST version 5 and HAD-SST version 4. There's maybe a little bit more observational agreement in these circumpolar averages. And we see in both cases a cooling from the late 70s through to about 2010, and then some suggestion of a warming after that. And in the spatial patterns, we see again this quite big differences in different places, with the cooling in ERSST version 5 being strongest in the Pacific sector. We've also seen very unexpected changes in Antarctic sea ice. Here I'm showing the 3 products from the NSSIDC Climate Data Record, version 4. This is the annual mean Antarctic sea ice extent. And we had this small expansion from the beginning of the satellite observations through to about 2015. And then these really large lows in 2016, 17, and then more recently this past year, 2023. And I think it's kind of interesting to contrast this to the annual mean Arctic sea ice extent, which is the gray line. We've had this really steady decline here that has been held up as a bit of a symbol of climate change. But when what we see in the Antarctic now really stands out in that the maximum in 2014-15 is larger than any sea ice extent we see in the Arctic record. And then 2023 goes down to be lower than anything we've seen in that record as well. So these recent changes are really very large in amplitude. The sea ice changes have been the net result of regionally opposing trends. Here I'm showing September and February, especially in the summer. There's been strong decreases in the Amundsen-Bellinghausen Sea in the observations. And then this is the sea ice extent seasonal cycle. So these are the data from the NSIC climate data record. The gray line showing every year since 1979. And you can see that up until the year before last, we saw this really consistent shape to the seasonal cycle, quite smooth with a slow advance period followed by a rapid retreat. But then 2023, which is shown in red, really I think caught a lot of us by surprise, falling outside the range of everything that had been seen before and breaking many records, especially in June through October. And I think we'll hear more about this in the sea ice session. Then we've also seen some changes in the subsurface ocean. This is from Argo data from Purick and Doddridge, showing the temperature anomaly over 50 to 65 degrees south, where we've had some cooling in the start of this record, followed by warming after about 2016. But this observational record is quite limited. We only have data from 2004. And I think there's still some more to tease out here about the relationship with sea ice and the causality. A study from GFDL in 2022 using their data assimilation system and constraining that model towards atmosphere or ocean observations suggested that the subsurface ocean heat played a key role, perhaps about 50%, in the sustained sea ice lows that happened between 2016 and 2021. Then, in terms of the ice sheet, we've seen changes in the mass loss from the grounded ice. These are the observations from Grace. And this shows a steady increase in mass loss from the beginning of that record. There's perhaps some suggestion of a reversal in more recent years. And this is, on the right, a snapshot of the ice mass change relative to 2002, to highlight that this is very localized and largely occurring in the West Antarctic region. The net grounded ice mass loss is, together with the sum of the ice shelf loss and precipitation minus evaporation, input that goes into the Southern Ocean. The figure on the left here is from ice shelf observations, and these show that this loss has been relatively steady over the observational record. The work of Andrew Pauling highlighted the importance of precipitation minus evaporation in this freshening, although there's still quite some uncertainty amongst different reanalyses here in terms of the input into the Southern Ocean. And then I also wanted to show this figure from Fan and co-authors, which gives a longer-term perspective to these changes. This is based on a variety of data sets, including marine archives and station data. And so here we have the sea ice extent, sea surface temperature, winds, sea level pressure, and surface air temperature, highlighting the fact that there is large multi-decadal variability in this system, and that the beginning of the satellite observations in the late 70s happened to coincide with a maximum in some of these records. And so really emphasizing the need to consider the longer term picture. So next, I'll give a quick review of some of the mechanisms suggested for muted Antarctic warming. Here I'm showing the 2-meter air temperature trend from those 3 observational products as a function of latitude in the zonal mean. And so I have also the global mean trend from these 3 products. The range of that is shown as this gray shaded line. So clearly, as we've seen before, we have this very large Arctic amplification. In the Southern Hemisphere, things are more messy at the high southern latitudes. These dashed lines are statistically insignificant trends. So you see that these are quite weak, and we also have quite large differences between these different products. But regardless, you really see this really strong asymmetry between the two hemispheres. There are a number of hemispheric differences that are understood to play a role in this. Of course, Antarctica is a very different geographical setup, surrounded by ocean. The continent is really high and it has a huge ice sheet on it. We think that these, we know that this plays a role in some of the differences. The figure on the right is from Goose and co-authors in 2018, showing the contributions of different feedbacks to polar amplification from CO2 quadrupling experiments in CMIP 5, and emphasizing that the ocean heat uptake, cloud feedback, and lapse rate feedback are the three largest contributors that give Antarctic amplification relative to Arctic. This strong ocean heat uptake in the Southern Ocean and the background ocean circulation comes from this general setup where we have sinking of dense waters near the coast, which can move warming to depth. Further into the Southern Ocean, we have upwelling of circumpolar deep water, which can mute these signals we see at the surface. And then the surface heat uptake can also be balanced by anomalous northward heat transport. In the Arctic, we have strong climatological temperature inversions with this very surface amplified warming, which support a strong lapse rate feedback. So there's weak long wave emission to space. And in the Antarctic, these inversions are much weaker. Work by Lily Hahn and co-authors at the right shows results from experiments where the Antarctic continent is flattened, showing that this gives us stronger lapse rate feedback through having stronger inversions and brings us closer to the Arctic. And then not included in the CO2 only picture, another hemispheric contrast that's important to mention is ozone depletion. The Antarctic atmosphere is highly susceptible to ozone depletion due to the unique weather and chemical properties. And so this, together with the influence of greenhouse gas forcing, has caused the strengthening westerlies that we've seen. And these are typically described in terms of the southern annular mode, with the impact strongest in DJF. Ferreira and co-authors proposed this idea of a 2 timescale response in the Southern Ocean to ozone depletion, with a fast cooling relative to slow warming. You can see this in the figure on the right. But recent work has cast this more into doubt, given especially by Yue Dong and co-authors in 2023, who highlighted that this SAM-SST connection was relatively weak. It could explain around 40% of the variance in DJF, and it couldn't be sustained between on long time scales between different seasons. And then another key difference is in terms of the interactions with the Antarctic ice sheet. A number of studies have highlighted the importance of freshwater forcing. The SOFIA project has a summary of these. These are related to the negative ice shelf sea ice feedback, whereby increasing meltwater, we promote sea ice expansion and reduce melt. There are a number of processes still to be understood around this. I have a few citations here. And there's also the potential for rapid ice sheet change, such as marine ice sheet instability. And these processes are something that are not included in CMIP models. So in this third section, I then want to make the case that that limitation, along with a couple of other issues, means that there are some limitations associated with our models that mean that really prevent us from understanding that balance of processes in terms of what's been observed and limit our confidence in projections of the future. And here I'm going to focus on sea ice because there's a few studies that I think have made some progress here. Antarctic sea ice has long been an issue for climate models across all the CMIPs. There's been some modest improvements in CMIP 6, but we still see a very large intermodal spread. And models have consistently underestimated summer sea ice. If we look at the trends shown at right, we can see that many of the models simulate strong declines in contrast to the observations Many of these are those that have strong warming trends and high climate sensitivity. To determine the consistency of each model with observations, we should account for internal variability. And so here I'm showing a figure that's similar to Chemke and Povani, but I've extended this to 79 to 23 and included a few more models here. And you see here that the GFDL models have the observations fall well within their spread. But many of the other single model large ensembles have the observations falling outside of the range of trends, or they appear to be quite unlikely based on those histograms. This is a little bit sensitive to the choice of time period now, given the big drops that we've seen in recent years. But I did that comparison over 79 to 2023, and even taking that longer time period, I would suggest that this gives a hint that something is missing from the models. And then I think that the experiments that I'll talk about in the next couple of slides further highlight that things are missing. And just to add here that we see a similar picture in the Southern Ocean sea surface temperature trends. This is a figure from Rob Wills and co-authors showing the trends over 79 to 20. Observations are the lines, and then we have our different single model large ensembles in the different colors here. And again, you see that it's quite unlikely that the models are able to pick up this neutral trend, but also a range of internal variability across these different model ensembles. So then I think there's been some progress from a range of different experiments that have been done by different groups in terms of understanding the sea ice expansion and why it's not captured in models. Here I'm showing the Antarctic sea ice extent trend. This is quite a short time period, 1992 to 2015, which is the common period available from these different studies. And I'd like to thank all of the authors here for making their data available. So I'll go through these. The first set of experiments come from nudging models to observed winds. We see that, this experimental technique is quite a powerful tool that constrains models to follow the observed realization of atmospheric internal variability, such that if you start the model from high or low Antarctic sea ice conditions, these ensemble members converge within a few years and tightly agree with one another throughout the rest of the period. They also then pick up much of the phasing that we see in the observations, which is shown in black. And so this technique allows us to ask the question of whether, given the observed atmospheric variability, we can capture the sea ice trends. And so here I show results from experiments with the CSM-1 climate model and also with the NASA GISS climate model. You see that the nudging the winds gives us sea ice trends that are towards the upper end of the ensembles, more towards agreement with the observations. And I also wanted to add in here this additional experiment where in purple, where we nudged, rather than nudging winds to the full wind field, we nudged the model to the reanalysis wind anomalies. So you use the model's mean state plus the reanalysis wind anomalies as the nudging target. And you see here that these purple diamonds have a bit less of an impact if you compare with the red ones, suggesting that there's some influence here in the model mean state winds that may be biased. And by correcting this, we can improve agreement with observations. Sun and Eisenman asked the question of whether, given the observed sea ice drift, we could capture the sea ice trends. And they found a positive result here, which I think highlights the importance of dynamical processes. And then other studies have looked at correcting the strong surface ocean warming that we see in the mid-latitudes in the Southern Ocean. So there are a couple here, one from Blanchard-Rigglesworth et al. In 2021, and then Sally Zhang and co-authors also in 2021, highlighting really that the Southern Ocean SSTs and sea ice are tightly coupled. We then more recently did some experiments at NASA GISS where we asked the question of, given that the CMIC 6 models don't include interactive ice sheets, what's the impact of adding meltwater In contrast to previous studies that have largely used idealized amounts, we added this the amounts based on observations from Slater et al. And if you compare our freely running ensembles here, you see that with meltwater, it becomes much more likely that we simulate sea ice expansion. And if we compare the control ensemble and the ensemble with meltwater at the right, this does a much better job of picking up the signals that we see in observations. And then finally, CMIP6 models are non-eddy permitting. So this motivated Thomas Rakow and co-authors in 2022 to look at varied resolution. The two squares shown here show their low resolution model, which is 65 kilometers in the Southern Ocean, versus high resolution, which is 14 and has the eddy parameterization switched off. And they find that the eddy permitting simulations exhibit lower poleward heat transport than non-eddy permitting simulations, delaying Antarctic sea ice decline. So if we look at these all together, we see that there are several different factors that can improve model agreement with observations. And I think this really highlights that there are many different factors at play in this system. And really, I think we need to be considering some of these factors together. So we've started to do that. I have a recent study looking at the influence of meltwater together with winds. But ideally, we would be able to compare them all in a common modeling framework. If we turn just to look at what we have currently, I think the nudging experiments are really helpful. They highlight the role of the observed wind variability. They don't tell us whether that is really internal or external in origin. So it's possible that the observed wind variability could be captured in these model ensembles. It's just unlikely. But if we look at this, this difference from changing between nudging to wind anomalies and nudging the wind to the full wind field, I think this suggests that the mean state winds are biased, at least in this model, and that this can impact sea ice trends. The Antarctic ice sheet meltwater experiments suggest that this should be accounted for, but then I think there's a lot of limitations still understanding how we should do this. If we implement this as a forcing, how do we put this into the models in their future scenarios? And then we've also seen impact of increases in ocean resolution, but this will depend on how the eddies are parameterized in each model, so we may not always see the same response in comparing these low and high resolution simulations. So to summarize, the observations show changes in different components of the Antarctic climate system. They highlight that the interannual and multi-decadal variability is very large, and the satellite record is quite short in comparison to this. In this really undersampled region, we need to have more and longer records. I also mostly focused on two-dimensional things, especially for sea ice. We don't yet have sea ice thickness, and our subsurface ocean observations are quite limited. So clearly, we always have these observational needs. A number of different mechanisms driving the muted Antarctic warming have been proposed, but I think it's difficult to trust climate models in this region. The experiments from recent studies suggest that winds, meltwater, ocean resolution, and model thermodynamic biases, which could be related to clouds, are likely important, and it's probably some combination of these. But given the current state of the models, I think this means that the confidence that we have in attributions of recent observed change in the climate system, in the Antarctic climate system, and in projections for the future is low. And so I think it's difficult to make claims about any emerging state for this Antarctic climate system based just on the CMIP models. Okay, thank you for your attention.
We have time. You finished ahead. This is great. So if there are any quick questions, we can take those right now.
This challenge to extend the observational data sets, Is it just that we need to start them and then continue them and sustain them? Is there a role for paleoproxy records that could help illuminate, particularly the multifactorial variability?
Yeah, I mean, I think there is a role for paleo. I don't know a whole lot about paleo proxies, but I think that seems like something that we really need. And I guess I don't have a good sense yet of how well constrained these are. But I hope that we would see more of that in the future.
All right, so let me ask a quick question. I was struck by the differences in the regional patterns that you showed of temperature trends. Can you just comment more on how important it is for us to, could that be limiting specifically our understanding and our constraint of models to have such different regional patterns in the warming of the Antarctic in our reanalysis / observations?
Yeah, I think it's a really big issue. I think that part of it is related to the relation to some of these ice sheet surface processes in the reanalysis, and we see a lot of differences over the continent. But yeah, I was also a little bit concerned when I started looking at these that there are such differences in the different signals. There are some, I didn't add the reference here, and I can't remember it off the top of my head, but I did see a very recent paper that's looking at the different station data records and comparing to reanalysis. And so I think maybe a more contending to those products would be helpful.
One more question.
Back to the nudging experiments with the winds. So the later experiments seem to work better. I don't follow all details that changed, but one of them might be that you they started first with error interim and then probably switched to error 5.
Right.
And so you go from 6 hours to 1 hour, and there's katabatic winds that are pretty intermittent. So what about that part?
Yeah, great question. I kind of skipped through that a little bit fast, perhaps. The CSM1 experience, we have a nudge towards error interim. And then the NASA GIST ones, we have a nudge towards error 2. We don't actually have error 5 yet, but I think Ed Blanchard Bigglesworth is working on those. But yes, I would really like to have a much nicer set where we could compare the difference between the different reanalyses. We don't have a totally like-for-like comparison between those different experiments yet, but working on it.
All right, thank you, Lettie. We're going to move on to our next speaker. And then there'll be plenty of time for discussion after our next two speakers. So next we're going to hear from Chad Thackeray from UCLA, comparing the seasonal cycle of trend-based emergent constraints on future sea ice albedo feedback.
Thanks to the organizers. So switching to the Arctic, this is basically following on from 2019 paper that I did looking at trying to constrain the Arctic sea ice albedo feedback. Motivation I can pretty much skip over in with this audience, but essentially the key thing to take away is that there's a large diversity in ice albedo feedback strength under mid-century climate change across, in this example, various CMIT 5 models. And so throughout the, let's see if we can get the pointer. Yeah, so throughout, when I'm referring to the feedback, it's essentially just some sort of albedo sensitivity metric shown on the right-hand side, where your deltas can either be like a month-to-month change or the difference from, say, a historical period to a future period. And so on the right, this would be a case where we're looking at, say, mid-century climate change. So you're comparing, say, the summer from a historical period to, say, mid-century. And on the left is basically derived from radiative kernels to convert this sensitivity into a feedback. So that's all that you really need to know from this slide. And in this past work, we showed that the model spread in the climate change case can be reduced through an emergent constraint using a measure of ice albedo feedback derived from climatological summer sea ice retreat. So the plot on the left is basically a ensemble mean map of this metric, so the seasonal cycle ice albedo feedback. And on the right, I'm showing the climate change case averaged over those summer months. And so you see there's some broad similarity in the spatial pattern with weaker values over the pole and stronger values closer to the land. And so in this case, this is the typical emergent constraint plot that we showed, where each different dot is a different GCM, in this case from CMIP 5. In gray, in this case, is our observational estimate with some uncertainty around it. And then you can see our sort of just general correlation value in the top left. And so we found a pretty strong relationship between the seasonal cycle isobated feedback and this climate change case when you didn't look too far into the future, which I'll get into why that is. In this instance, the models are color-coded by their historical August ice thickness. And we found that the models with the most unrealistically thin summer sea ice were hindering this relationship. So if you were to take away or discard the models with the most unrealistically thin August sea ice, you see a much stronger relationship. In follow-up work, however, we found that there's some differences when you look at this in CMIP 6. So on the left, I'm basically showing this a similar plot to what was just shown on the last slide, but including all models, so CMIP 5 and CMIP 6. And on the right, I'm showing a similar example, but basically we're just averaging over the entire summer instead of just the early summer. So this is a much more representative metric of the annual ice albedo feedback on the right. And so in that case, CMIP 6 actually performs better than CMIP 5. But this change doesn't really sit well with me, which is why I've sort of done this new analysis to try and better understand what's going on. And it also brings up the question of whether other potential observables might perform better in an emergent constraint framework. The main reason why there's some of these differences is there's a lot fewer of these super unrealistically thin ice packs in CMIP 6 than in CMIP 5. So you can somewhat see that in the summer months here. The CMIP 6 ensemble mean is higher than the CMIP 5 ensemble mean. And just some brief info on the data that I'm using here. So in this analysis, I'm using 41 GCMs from CMIP 5 and 6, using 5 different radiative kernels blended together. The observational data comes from APPX and Clara A2. I couldn't update to the new version in time for this talk, but that's in the process. And then temperature data from MERA 2 and NCEP 2. And so I'll basically walk through these different examples of potential metrics you could use as your x-axis and emergent constraint. So the first one is this surface albedo feedback that I just showed. A second one that I'll refer to as albedo climatology basically just takes the Arctic average albedo from May and August and takes the difference and then averages over the most recent decade. So basically just looking into climatological seasonal cycle differences across the models. We could also look at trend-based metrics. So one example would be to take the trend in summer surface albedo across the Arctic. And in this case, we take that measure and regress it by the temperature trend over that period. So over the last 4 decades in that case. We could also actually look at the trend in the albedo feedback itself. So instead of calculating the albedo feedback based on a climatological monthly value, as we did in example A, in this case, we can calculate this for each year over the past multiple decades, and then extract the trend and see how the actual albedo feedback is changing over the recent decades. And so I think that's all I need to talk about on this slide. First, starting with our past example from our 2019 paper, this is basically what you see if you look at all 41 models. This time our observations are shown in red from a variety of albedo and temperature metrics. So I think we have 4 different estimates of the seasonal cycle albedo feedback. You see a reasonable relationship between the seasonal cycle and the future change. If we, again, get rid of these models that were hindering our relationship in our previous paper with the very thin summer sea ice, you see an improved relationship, which is sort of supporting our prior work. Although ideally, we would not have to discard models at all. But I'll get to that in a second. And so this is the same figure from the right-hand side of the last slide. We could also take this albedo climatology metric shown on the right, which is basically the August minus May albedo change, basically a climatology over the past decade. In this case, we see a similar, the observations fall in a similar area in relation to the model spread as they did for the ice albedo feedback. If we look at trend metrics, they're less sensitive to a model's initial ice conditions and more sensitive to the historical warming over the past 4 decades. So in this case, I'm looking at all 41 models. The x-axis is the seasonal albedo feedback trend over 40 years, and the y-axis is staying the same. And so we see a correlation of about 0.57. In this case, the 2 models that are really weakening the relationship are these 2, which are a pair from the same modeling center. And they just have basically no warming trend over the Arctic over the past 4 decades. Could be because I'm only looking at realization number 1 rather than sampling across many different simulations. But that acts to weaken the relationship because they have a strong warming trend in the near future. In the case of the albedo trend over the summer, we actually have a larger observational uncertainty with this metric than for the ice albedo feedback trend itself. In this case, the observations are actually the furthest away from the model mean of any of these metrics. And this goes along with some past work that has shown that most models underestimate the observed ice loss in the Arctic over recent decades. So that's consistent with that result. So from each of these constraints, we can basically produce a PDF of what is the likely, what we call a 95% prediction interval based off this Bowman et al. Method. And so this is our example of what the ensemble looks like in an unconstrained sense. So just taking all models as equal. And we can do the same thing for our seasonal cycle, seasonal sea ice albedo feedback constraint. You see a shift to higher values as more likely. We can continue that with the albedo climatology metric, which supports our previous work. The albedo trend work, which is kind of hard to see in yellow, actually supports a stronger ice albedo feedback in the future than our ice albedo feedback metrics. And then the trend in ice albedo feedback agrees with the other 2 metrics pretty well. So the takeaway here is just that these findings support a larger ice albedo feedback than the ensemble mean, which is consistent with what we showed in our past work. And so there's various ways to try and combine these different constraints. Thank you. I haven't totally made it in time for this workshop to combine everything, but that's what I'm trying to do. But essentially for now, I'm just taking the average PDF across these different examples, which is obviously not ideal because they might be correlated, the x-axis quantities themselves. But in this case, if you take the average PDF, it essentially gives you a value of about 5.4 watts per meter squared per degree Kelvin, which doesn't really mean a lot, but I'll convert that to a more standard global albedo feedback value later on. There is a better way to do this aspect of constraining them, which I'm planning to do, but I didn't have time to when we had our deadline to upload slides by Friday. Didn't quite make it. This is work from Chris Bretherton and Peter Caldwell that they developed for equilibrium climate sensitivity. So in that case, there have been so many different observable metrics that people have proposed as being related to variability in climate sensitivity. So this is just a sampling, each of these different lines, the sampling of different published proposed constraints. They break it down into what they deem as credible versus possible. And the takeaway is just that there's a lot of variability when it comes to these constraints and what they suggest for ECS. A key component of this work is to assess the interdependence of these constraints. And so in this work, Chris and Peter suggest computing partial correlation coefficients between each metric so that you can then calculate weights to then generate basically a more sophisticated version of my black line here. So I've done the correlation work, and none of these constraints surprisingly have a very strong partial correlation coefficient. Strongest relationship, if I'm remembering correctly, is between, strongest correlation is between the two trend metrics, which is somewhat understandable just because the historical forcing has a big impact in that case, or on the intermodal variability. And so to make sense of that result, this is just from the last IPCC report. If you just look at the surface albedo line here, to make sense of the numbers that I was showing that whole time, the central estimate for the surface albedo feedback is about 0.35, but a decent uncertainty range around it. In our prior work, we had assessed that the global albedo feedback was about 0.12, I believe, in the Arctic. Or sorry, the ice albedo feedback from the Arctic was 0.12 of that. With some changes to our methodology, I think it's closer to 0.1, so a slight change, but nothing too drastic. And I could mention how to calculate that, but it's basically just consistent with past work. You take this summer value that we've constrained, multiply it by the ratio of annual to summer ice albedo feedback, the ratio of the Arctic domain to the global area, and the ratio of Arctic to global mean surface warming. So to summarize, basically this work expands on our 2019 paper. The goal is to test the robustness of this past work, yet also to see if there's something out there that's more robust in a sense, and doesn't have as much need to remove these outlier thin ice pack models as we do for our seasonal ice albedo feedback metric. And so what we find is that two metrics capturing the seasonal cycle are well correlated with future ice albedo feedback when these models with thin ice are excluded. The two alternative trend-based metrics that we propose generally support these findings, but I think they're hindered a bit by larger observational uncertainty when you're looking at trends. And so this combination that I have right now suggests a 24-25% reduction in model spread, which is somewhat useful, but hopefully it can be improved as I further improve the methodology. And then lastly, I'll just mention that further work needs to explore the areas of the Arctic that are driving each relationship. So I didn't have time to throw up a bunch of maps to look at where these trends are different in each of the models. I think that might be a bit susceptible to if you're looking at one realization or averaging across multiple realizations. And then it should be noted, as I kind of referred to on the last slide, that none of the ECs or different metrics here surprisingly have a significant partial correlation coefficient with each other. I think I'll end there, right on time, apparently.
Is there one quick question, Clifford?
Hi, so you mentioned using a blend of 5 different albedo kernels. We know there's kind of a big difference in the Arctic albedo feedback depending on which kernel you use. So I was curious, I guess, one, if you've looked at the spread introduced depending on which kernel you use, and then also if you have considered using a more like observationally based kernel, like the ERA interim radio kernels.
Yeah, so if you use the ERA interim one, you'll get a stronger albedo feedback than any of the model-based ones. So in a 2021 paper, I basically got a whole bunch of kernels from Mark Zelenka, and we compared the spread or the impact that using these different kernels had on your albedo feedback value. The blend that I'm using here is basically just consistent with that 2021 paper. It's, I forget the 5 models, but it's 5 GCM-based kernels. And basically, it seems like using the observational value will just push your estimate higher. I might incorporate that eventually, but for now, I was just tight on time. So doing the method that I already had. But yeah, it's a good point.
All right. Thank you, Chad. We're going to move on to our next speaker, and we'll have time to come back to some of this stuff in our discussion, because there's lots of items that I'm sure we can get to. So our next speaker will be Stephanie Hay. She is going to come to us online, so she'll be a virtual presenter here. And so she's going to talk about the steady but model-dependent polar amplification of CO2 forced surface warming and CMIP6 projections. So with that, Stephanie, take it away. Are you muted? We can't hear you.
Stephanie, you're muted.
Oh, can you hear me?
Yes, we can hear you. Thank you.
Great. Okay, and you can see my screen.
Yes.
Great. Okay. Right. So this is work that's under review at the moment, but I've also extended it to look at the Antarctic because of the theme of the workshop. Right. So outline. I wanted to look at the CMIP6 models to understand how the sources of uncertainty in what were the sources of uncertainty in Arctic amplification. And for the workshop, I also looked at the Antarctic. To do this, I use the Hawkins and Sutton framework, where you look at scenario uncertainty, model uncertainty, and internal variability. So I came at this actually looking at things a bit differently. I wanted to know if there was a relationship between Arctic change and the storm tracks. I'm sorry, I need to stop one moment. Sorry about that. Can you hear me now? Right.
Yes, we can hear you.
Sorry. Yeah, so I was looking at explaining model spread in the storm tracks in terms of Arctic change. And so I was looking at these different metrics of the storm tracks of cyclones, intensity, speed, and lifetime. And I was comparing that to measures of Arctic amplification in winter and summer in CMIP6 and CMIP5. And so this is quite a nice figure here to show that basically there's no correlation between these things, at least over the historical period, in either summer or winter in CMIP5 or CMIP6. So next I started looking at the future. And I started thinking about how we define Arctic amplification and how we should define it in the future. And so I looked at the 4 different forcing scenarios in CMIP6. And I noticed that, there's a lot of intermodal spread here, but they all actually have about the same amount of Arctic amplification, which is just about 2.5. I thought, is this strange? Is Arctic amplification a constant number? And I looked into it a little bit, and I'm certainly not the first person to have observed it. I found this quote here from Barnes and Pavani. The long-term values of Arctic amplification are quite similar to the near-term values. They looked at 2 different time periods. And that's what I'm showing here on the right in one specific model. So a value of surface-based Arctic amplification in 4 different scenarios and how it changes in time. And there's a lot of variability there, but it's about the same through time. At the same time, what I'm showing on top is that the sea ice area drops quite a lot. So I thought, how can we take advantage of this for assessing the uncertainty? And for this workshop, I also thought, what about the Antarctic? So first looking at local uncertainty in scenarios. So I'm showing here the trend, it's the difference at the end of the 21st century in terms of the amount of warming in the 4 different scenarios. And this, the local amplification is that relative to the amount of warming globally. And then if you average over the Arctic, you find this number about 2.5 times as much warming. I showed in the last slide as well. And that's across all scenarios. This pattern of local amplification is quite similar across the different scenarios. And this is actually, I thought this was quite strange at first, but it's just pattern scaling. And that's the idea that the change in some variable is proportional to the amount of global warming. So that's how we define Arctic amplification relative to global warming. Not always, but often. One thing I wanted to point out was that you have this sort of uncertainty here, this model spread, well, standard deviation here. And it goes down as you go from the lowest forcing scenario, so 0.42, all the way down to 0.28. Right, so then the Antarctic, these numbers are much smaller. So about 1.2 times as much warming at the end of the 21st century. And that's actually, if you look at this map, similar to any other landmass. So it's just sort of a land-sea contrast as it appears there. But like the Arctic, there's little difference with scenario in terms of local amplification or in that number if you average over the Antarctic. And you seem to reduce the spread as you increase the strength of the forcing. Okay, so there's a lot going on in this figure. What I'm showing is at different 30-year time periods, the Arctic amplification relative to an earlier time period in each of the CMIP6 models in the 4 different scenarios. And then you can see each model is colored in a different way. And then there's the boxes are showing the interquartile range, I believe I showed. And you can see that it is relatively flat in the multi-model mean. If you look at any individual model, there's more variability. It's not necessarily that it doesn't change in time. If you look at sort of the current period, so the first boxes in each of these are about the same. There's quite a lot of spread. It goes from something like 1 to 4.2 as an estimate of Arctic amplification. If you look at the end of the 21st century in SSP 585, so I think this is the best you can get as an estimated model uncertainty. There's still internal variability in there, but it should have the strongest forcing, so that should be smallest. And you look at something like 1.8 to 3.2, so it's a very large intermodal spread still. If you look at the Antarctic, it's not quite as steady in time. In fact, there's something of a downward trend. The spread is presently something like 0.5, so not amplified, to 2.3 in the models. This is not surprising. We know that the models are not great at simulating what's actually going on in the Antarctic. The spread's actually still smaller than in Arctic amplification, though. And I want to point out that many models don't support amplification of our Antarctic warming, so they fall below this one line. Looked a little bit at how that varies by season. And so this is back to the Arctic now. The Arctic amplification ratio, DJF, MAM, JJA, and Sun. And you can see that, not surprisingly, it's largest in the winter and smallest in the summer. It is, actually, I haven't explained well what I'm showing here. I'm showing this versus the global mean surface warming. So I've pooled all the scenarios now because they basically show the same amount of Arctic amplification. So I thought you can just pool them all into one nice plot. And what's interesting here is that as you get to the models with the largest surface warming, so the right hand here, they seem to the model spread kind of converges towards this value, which is, and the solid lines here show you that the CMIP6 mean. So it's sort of an interesting thing I observed here, where you get this convergence towards one value of Arctic amplification. It's true in the different seasons, particularly the colder ones. In summer and autumn, it's a bit different. So you start to see this increase as you go towards larger amounts of surface warming in summertime. And then you see a decrease in fall. And you say that's, people have suggested that's a sea ice feedback that's maintaining Arctic amplification. And if some models go ice-free at higher amounts of warming, then you'd have a decrease in Arctic amplification. I looked a little bit at that. And so what I'm showing, the top two are looking at the end of the 21st century. If you separate the models by those that remain ice-covered or not, so kind of basically have more than 1 million square kilometers is defined as ice-covered. And this seems to make a difference in the summer So if you look here in the SSP 585, the ice-free models have a larger Arctic amplification ratio than the ones that aren't. It doesn't seem to appear that way in autumn, though. So that was quite interesting as a discovery. So I looked a little bit at other state dependence. And so if you can, so the next is the different seasons and how the correlation between the amount of sea ice there in the models and the amount of Arctic amplification, and it's uncorrelated in the fall. So it's a bit strange, really. It's something I found. Same thing if you would compare it to the equator to pole temperature gradient. So as that decreases, that could decrease as the Planck feedback would decrease Arctic amplification. And that's also uncorrelated, so you can see that here. And if you look at this through time in the different seasons, they become, it's less correlated in time. So as things like sea ice change, it becomes decorrelated from Arctic amplification values. Antarctic, looked at the same thing now, the seasonal variation. There's not as clear of a convergence in the cold season, and there's a really large intermodal spread. But it is a similar idea, but you can see that the model spread's quite large. Finally, looking at internal variability, I'm looking at large ensembles. And so now I'm defined the trend over different 30-year periods. And I've plotted that. So the trend in global warming versus the Arctic amplification ratio you get from the trends. I've included 7 different large ensembles, and then the CMIP6 large ensemble. I've also plotted, I don't know what happened. I've also plotted some the ERA5, JRA, and MERA2 against that, and you can see that across the different models, large ensembles, you still get this sort of convergence at high amounts of warming toward a value. It's not necessarily 2.5 in all the models, but it's not too far off, actually. Some of them are, a little bit higher, a little bit lower. Something like CAN-ESM, which has very low sea ice area and strong climate sensitivity, does seem to drop off at high amounts of warming. But interestingly, all the different reanalysis products mostly lie within the spread shown by internal variability. So some of them are very different from one another, but they do seem to fall within it. So it's quite consistent given the same amount of global mean surface warming. Finally, if you look at, so this is the same thing still, but now I'm pointing out that some of these really high amounts of Arctic amplification are actually emerging at the end of the 21st century as the global warming really slows down in the highly mitigated scenario. So that's kind of a consequence of the way we define it as a ratio. When you get a small number on the bottom, the number gets really large. Finally, for the Antarctic, I've done the same thing where I looked at the large ensembles. And I noticed here that some of the large ensembles seem to show this sort of C shape. So at low amounts of warming, you get a higher Antarctic amplification ratio, but you also do at higher amounts of warming. So this seems to show some sort of non-linearity into the amount of warming over the Antarctic relative to the amount of global warming when you consider 30-year trends. Only JRA 55 actually has a statistically significant Antarctic amplification, and it does fall outside of the spread for quite a lot of the models. Again, it's probably not surprising. We know that the models have not done a very good job of simulating the Antarctic over the observed period. Okay, in summary, I'd say to first order, at the Arctic, and to a slightly lesser extent, the Antarctic amplification ratio can be considered a constant across time and scenario in the absence of internal variability. When you include internal variability, it's quite similar in magnitude to the model uncertainty in the Arctic. But the model uncertainty is probably a bit larger than in the Antarctic, though not by a large amount. It's still quite a large amount. And this last point makes it quite difficult to know, basically to determine whether we're modeling Arctic amplification, Antarctic amplification consistently with observations or not, because there's such a large spread at low amounts of warming, like we've had in observations. And so the point I want to bring forward for the discussion based on all of this kind of goes back to what I was saying at the beginning. Is this the right metric that we want to use when we're trying to understand things like model spread and how they correlate with aspects of the circulation response? Thank you.
Do we have any quick clarifying questions for Stephanie before we move into the discussion period? Not right now? All right, so now we're going to move into the discussion. We have 30 minutes set aside in the agenda to talk about what we just heard and start thinking about some of what we can do as a community in order to kind of address some of the challenges and questions that were just raised by this morning's speakers. So the first thing, and I know I didn't warn the speakers this, but I'm going to ask you guys to go up to the front of the room and sit at those nice microphones right there. So it'll make it feel a bit more like a panel discussion. Now, while they move on up there, and I noticed, if you guys didn't notice while you're speaking, if you do need water, there is actually water bottles hiding behind the podium. So if you need some of that. But so just because I asked them to come up, this doesn't mean that we're just going to pepper them with questions. It just might help the flow of the discussion. So does anybody have any initial thoughts or questions as to what we've heard this morning? So, and also, I won't run the microphone around, but if we can start just lining up at the microphones in the center, and I'll leave this one here, and folks can step right up to the microphone and start this.
And I know we just said that this was going to be a discussion. I did have one question from the virtual participant, Gaopeng Xu. In AWI paper, so this is to Lettie, sorry. In AWI paper, they compared high resolution and low resolution simulations and found meridional heat transport are different. Do you think meltwater can impact sea ice extent by impacting meridional heat transport? Did you compare meridional heat transport in your meltwater experiments?
Hi, thanks for the question. That isn't actually something that we've looked at yet. I think what we've put out so far is kind of our high-level results, but we're planning to look more into the processes and especially into more of the ocean processes.
Thanks for that question. Go ahead.
Hi, this is Will Hobbs from the University of Tasmania. I have a question for Chad. It's probably a dumb question, but if nothing else, hopefully it'll encourage the early career researchers to feel comfortable asking questions as well. So in your, you're talking about the sea ice albedo feedback. Is that purely the surface albedo, but does that include changes in the incoming solar radiation? Because presumably if you get a more ice-free Arctic, you've got changes in clouds, and how does that feed into that question around the albedo feedback?
Yeah, so the feedback would be calculated as basically just calculating your albedo using downwelling, upwelling terms. So there would probably be some slight contribution from cloud changes, but in general, because it's defined at the surface, you would expect that to be pretty minor. When it comes to thinking about internal or intermodal variability, it's quite possible that there is some role for differences in the future changes in Arctic clouds to influence that. In the seasonal cycle, it's less likely that there's a big impact. One of the reasons why we don't look too far into the future, besides a lot of the models going ice-free, is also that the cloud impacts become larger the further into the future you go. So with the more warming. So for a lot of the stuff I showed, we're only going to 2030 to 2050. So the cloud changes are pretty minimal in that time step.
Hi, so sorry. This question is following from Steph's talk, but could be also for everyone. Steph, you said that some of the metrics, well, this ratio metric potentially was not the best metric to characterize Arctic amplification. Have you tested any other metrics? Do you see the same kind of pattern emerging? And or is there like some metric that could be better to characterize Arctic amplification or Antarctic amplification?
So I'm not sure what the best one is, so I didn't really end my talk with an answer to that. I've thought a bit about it. This also applies if you look sort of at the lower troposphere. It's not just it's not just at the surface. So I sort of think what people are trying to get at when they do these things like correlating model spread and Arctic amplification with some circulation metric, is they're trying to get at the equator to pole temperature difference. And since I showed in one of my slides that it actually becomes this sort of ratio version of Arctic amplification becomes decorrelated from something like the equator to pole temperature difference. I'm not sure that you're then getting at the thing you want to get at, and so I think you need to define it as a difference between the Arctic and I'm not sure if it's the mid latitudes or if it's the tropics or something else. That remains to be seen.
Everyone, Kyle Armour here from the University of Washington. I have a question about the role of internal variability. So in the context of Lettie's talk, you mentioned, you gave kind of a compelling case that is a combination of winds and freshwater. Do you have a sense of whether the changes in winds and changes in freshwater are forced, or could it be internal? And then to follow up for Chad, if we think that roughly 40 or 50% of the Arctic sea ice loss is internal variability, I'm making those numbers up, that's my general reading of the literature maybe, how does that affect your estimates of albedo feedback and the biases in the models? Is that something you corrected for, or do you have to worry about that in your estimates?
Great question. I think that's kind of the big question. So like I said, I don't think these wind nudging experiments can really tell us whether we're putting in internal variability or something that's not really sort of captured in the models. And so it's really hard to talk about whether the wind changes themselves that we're adding are externally forced or internal variability. I mean, I think that you can see it depends a little bit what time period you look at, but a lot of those trends in the sea ice, at least, are not that far away from the range of the ensemble. So I suspect that that a lot of it is internal variability, but I can't really put a number on it. And then, yeah, the meltwater trends, I mean, I think we can't really do that until we have coupled models that compute that themselves so that we can really do the attribution. But yeah, I mean, definitely big questions.
I'm sorry, can you try another microphone maybe? There should be a green light when you press the button.
Yeah.
Okay, now we can hear you.
Okay. Yeah, so the impact of internal variability is definitely larger when you're looking at these trend-based metrics than the climatological things like the ice albedo feedback, as I defined in my past paper. I think that was one of the reasons why we used a metric like that previously, just because it's more robust to things like internal variability. In what I showed so far, I haven't accounted for the influence of internal variability yet. One possible way to do that is what we did in a 2022 paper where we looked at the observed trend in heavy rainfall occurrence and used that to constrain the future change. And so obviously there's a lot of internal variability in that as well. So we basically just took all realizations that were available for each model as a way to extract the force or better measure the force response. I think that would be better correlated with the future change. You could do something similar with the albedo change metrics that I showed. I just haven't got around to analyzing that much data. But yeah, I think one thing that'll hinder the trend-based metrics for now still is observational uncertainty, as you mentioned. So yeah, I think we can use it as a tool to build on what I showed before with the climatological things, but I don't think it works independently right now.
Go ahead, Dave. Yeah, so I have a question for Chad, which is kind of a question for the community as a whole, but trying to move beyond maybe just trying to constrain the surface albedo feedback. I think like Nicole Feld has some nice work showing that the surface albedo feedback can constrain the lapse rate feedback. Jen K has worked with surface albedo and kind of clouds. Do you think that the same framework could be used to kind of constrain the net feedback?
Yeah, that's something I've written in my research plan for ages. I just don't have any funding to work on Arctic stuff right now, even though I put this together quickly. But yeah, I think there's definitely room to. So because we know from Nicole's work and some of my work and others that robust constraints exist for various feedbacks that are driving Arctic amplification, there should be some way to combine them in a sense and form a robust constraint on Arctic amplification that's physically based rather than say something that's based on just like a recent trend in one metric. I think a more robust way would be to constrain each of the individual contributions that are most important and use that to feed into a constraint on Arctic amplification. Yeah, I think that's a challenge, but something that could be done.
I think it's important for us to discuss further as we move forward and into the breakouts this afternoon. But we do have an online question.
Yes, we have two online questions.
Two online questions.
The first is from Olivia Link, and she says, this is a question for Chad. Can internal variability in parts explain their intermodal spreads you showed? If yes, how do you account for that effect?
Yeah, so that goes back to Kyle's comment as well. I haven't assessed the amount of variability across different realizations yet. If you look at, say, one of those trend-based metrics, based on prior work prior analysis that I'd done, I wouldn't suspect that that one model could generate as much spread as the ensemble can. But usually there can be a substantial amount of internal variability based on, especially if there's differences in the warming trends across the Arctic over 40 years or so. So that's something that still needs to be accounted for and is a big source of uncertainty.
Great, thank you. The second question is from Tim Carlson. It says, I have a question for Steph. Very interesting to look at. Thank you. Do you think your Arctic amplification value, and even more so, maybe the Antarctic amplification value, stay constant because you haven't reached a certain warming threshold yet? For example, you plotted your Arctic amplification until around 2100, if I remember correctly, and there has still been Arctic sea ice in the model simulations. Do you expect the value to change at one point after your simulation period, when processes like sea ice albedo feedback, et cetera, become less relevant?
Yeah, so I would expect it to change at some point. So I guess this holds under the sort of pattern scaling, which the first part is that it only holds for like a strongly mitigated scenario. You'll start to see that the pattern of response will change, which is kind of what happens in SSP 126. On the other side of it, as you do lose the sea ice, you would expect to lose sea ice feedbacks. It's not clear to me if other feedbacks would then change. So there would be a sort of a change in the strength of a feedback when you lose the sea ice for the other ones to compensate in some way. And I do think that there is a paper by Marika Holland that did look at some of these large ensembles out to 2300, and I think the sort of Arctic amplification did start to drop off at some point when you pass some sort of threshold or tipping point or whatever, that it could then change. I was careful to put in my title "in the 21st century" to specify that I meant kind of near-term change, not really strong climate global warming.
So I will ask the next question, but if you have anything in the room, please step up to the microphone. I think this is a good point to start to transition from maybe just questions to the speakers is to more kind of broad discussion about some of the objectives of the workshop, which, to try to understand where our key kind of tall poles are, and what we need to do, what we can do as a community for that. One of the things, and again, this is for the room, but let me ask ask this. So internal variability versus the force responses come up a lot. Are there some things or some ways that we can use large ensembles that we haven't yet? Or are there some tweaks we need to the way we run the large ensembles now that could really help us get at kind of the specifically what we're seeing in the Antarctic versus the internal variability versus the force response? And so are there new ways we can think about using large ensembles? You have a response? Go ahead, Lettie.
Well, I don't have a response, but maybe I could ask another question, which is, yeah, I'd be interested to hear what people think about whether the ranges that we see of internal variability from these models are realistic and how we assess those.
People can think about that, but go ahead, Lisa.
Talking about large ensembles. For the analysis that I've heard presented today, I would appreciate clarification whether CMIP6 models used all the ensemble members or only individual contributions. Like I think, Chad, you mentioned that you only used one. Yeah, so if you use one and there's 40, you might have actually quite a different representation of that model if you consider all the ensemble members. In our recent paper, we actually found that chances for one ensemble member to be skillful relative to whatever metrics increase if you increase the ensemble size beyond 10 members. And the idea is that this relates to the acceleration of the sea ice decline, which we analyze. And that's my question for both of you, actually, three of you, whether you have considered that over whatever satellite period, there was a significant change in the trends, whether the emerging constraints, sea ice decline, or deep water formation in the Southern Ocean, for example. So over the historical period, the first 20 years or so was so different compared to the more recent couple decades.
Yeah, just quickly on that point. In the paper that I referred to, the 2019 paper, CMIP5, I looked at multiple realizations to see how susceptible that ice albedo feedback metric was to internal variability. I just haven't done it yet for CMIP6. In terms of the climatological metrics, there wasn't a big impact going from one realization to the next. In the case of these trend-based metrics, I think there will be a big difference. And so I think that's one thing that needs to be added to that analysis going forward. So yeah, it's a good point.
Lettie or Steffi, do you have anything to add? Use some ensembles or more of the ensembles that are archived in the CMIP6?
Yeah, so I did show one slide with the large ensembles. The CMIP6 figure I had did have multiple ensemble members, but it was quite close to the, I was trying to get that into the IPCC report, so we didn't have that many realizations for each of those models in the scatter plot that I showed. But yeah, obviously really important to look at the spread of the trends. For the sea ice comparison, there's, yeah, I mean, I think it's kind of a bit difficult to think about now that we have this really different, depending on which years you include, you can have a very neutral sea ice trend or you can have quite a strong expansion. And so I think we have to be careful about how we assess how the models are doing and think about the variability in the trends as well as just the linear trend over the whole period.
Stephanie, do you have anything to add, or we can move to the next question in the room?
I don't have anything to add to that.
Okay. Wait, Claire.
Hi, Clara Desser from NCAR. I've really enjoyed this session very much, and I wanted to pick up on Kyle and this whole discussion of the internal variability. I think we really need to start to look at the patterns of internal variability and not think of it as a black box. And, models, of course, are going to have their deficiencies. And I think we should break it down into what we know about internal variability. So, for example, ENSO teleconnections. I'm just curious how much of this mismatch between models and the real world in terms of Antarctic sea ice as a whole is really a spatial mismatch in, say, teleconnections coming from the tropics or patterns of just internal atmospheric variability in the high latitudes. And when we look at, this metric of zonally averaged, say, Antarctic sea ice, it's a very specific thing, and it's going to highlight just the regions where there is sea ice, and that's going to be where the sensitivity comes. And if there's any mismatch in the mean state between models and observations, that's going to be picked up there. So I just think it's so nice, Lettie, what you showed, just to bring in, the SST, the sea ice, I mean, lots of things, so that we're not just wondering about these very localized patterns. So I guess I would push the community for looking at spatial patterns of internal variability versus trends, and how to interpret trends. And in the large ensembles, at least we can know if we're looking at the force component or not, but really delving into the patterns. Maybe, I think there's a lot to be learned there. Yeah, I was sort of curious. I wonder if, if you looked at each model simulation, if you somehow controlled for the particular sequence of El Nino and La Nina events, and you controlled for that in some, maybe regression format, what would it look like compared to the real world with that same control? I just think there are ways forward, perhaps, to, really grapple with these patterns of internal variability.
It's okay. If there are any comments, we can move on, but if you have
Oh,
something, go ahead.
yeah, great points. Thank you. One of the things that I would like to do is try and see if we can modify the nudging, so that instead of just imposing the whole wind field, we're maybe imposing different modes, and see what that does into the model.
It's Will Hobbs again. I guess it kind of follows on from what Clara was saying, is that question of one of the reasons why detection and attribution is so difficult in climate environments is the same polar amplification that acts on the force response also acts on the internal variability. So it comes down to the question of, is internal variability a source of information, or is it a challenge that we've got to filter out with a large ensemble? Do we expect the amplification to be the same in response to, for example, ANSO, as Clara was saying, or is it different in response to anthropogenic climate change?
Yeah, I think in most cases, at least from my perspective, in terms of trying to constrain a future change metric or sensitivity, ideally you'd want to measure the force response in the historical period over some sort of trend or whatever, rather than internal variability. So the way I would do that, well, there's some recent work in this force MIP project where they're trying to better extract the forced response using various statistical methods. Potentially there's some relevant work that's been done with that we could apply. But I think in terms of what we've shown today is a lot of emphasis on, if you're looking at trends, you kind of need to just use a lot of different model realizations to try and extract that forced trend, which should be more representative of what you expect under a warming climate in the future.
Caution, trends over short intervals of several decades are not to be interpreted as solely forced. And if you're going to combine, single realizations of different models, you're kind of muddying the waters because you don't know.
I'm saying minimum of like at least 5 realizations, probably 10, to get an accurate measure of something that better resembles the force response than using one realization. So not just saying that just taking the average is the force response, but saying that is more representative of the future change you'd expect than if you only use one model. Yeah, because I agree that one realization, and if you just take a couple, it's like, okay, they might give you completely different answers on what the trend is. So yeah, you need a sufficient sample size as well.
But I think just quickly going on that, so I think what I heard you say is that really ideally, to answer Will's question, it was, is internal variability a source of information, or is it just getting in the way? And what I heard you say is it's just getting in the way. If we could have the forced response, if we knew that perfectly, then that's all we need. But so I'll ask the question again. Do you think there's knowledge to be gained from understanding the processes involved in internal variability, or are we just really trying to get it out of the way so we can see what the force response is underneath?
It depends on the purpose. So in the case of what I was trying to do, which is constrain the future response, I think the internal variability is getting in the way. If you're looking at better understanding recent past, then it's super important to understand, like the internal variability signal tells you so much. And I think in that case, if your research question has to do with understanding past changes, then it's definitely has valuable information, especially in a large ensemble context, to understand things like El Nino's role on Antarctic ice and so on. So yeah, I think depending on your research focus, it has a different meaning and relevance.
Alice?
I was going to say along the lines of what Lettie and Clara were talking about, that Ian Baxter and Xinghua have done some experiments in the Arctic where they were looking at optimal atmospheric modes that would enhance sea ice loss or not, where they nudged and used the same, I think, mode over and over. I haven't seen anything like that for the Antarctic, where it would be like, and then a La Nina or something like that. But maybe, Clara, what you were saying about trying to find whether in the, in the PI control or something like that, and use that mode and do some sort of nudging of the sea surface temperature and the winds from that mode and repeat that and see if that leads to similar sorts of, extremes in the observed, as we've seen, could be useful.
I have a question about kind of the detectability space. Which is that if we're thinking in a signal to noise context in the Arctic, the noise is really large, so we're not really able to gain detection relative to the global. But if we're thinking about internal variability and removing it, do we actually gain detectability if we move into kind of the framework of using something like a dynamical adjustment or some approach to remove the internal variability from a single member? So do we gain detectable power in the polar regions over the global, if we're able to kind of apply those techniques successfully?
Yeah, you mentioned the Arctic. I think dynamical adjustment's one potential way to better understand the role of internal variability and how that might be impacting the trend that you see. I think a good example, when you look at trend-based analysis and the role of dynamical adjustment, Nick Seiler had a paper a few years ago looking at snowpack trends in the Western US. And when you dynamically adjust, basically shows that internal variability has muted the response that you'd expect. So it's potential, there's definitely potential to use that in an Arctic context. I think Clara might know more if it's already been done or not. I can't think of it when it comes to trends in ice off the top of my head.
Yeah, Alex Jan stepped out, but I thought that she and Mark England had a paper trying to do dynamical adjustment of Arctic sea ice. Dynamical adjustment is great, but it is it's not end all. And when the sea ice has, time lags in it, it has memory. And dynamical adjustment is best suited to, at least the way that we've applied it on a kind of simultaneous monthly basis, it's best suited to quantities that don't have much inertia. But I think, yeah, it would be worth exploring. I don't know if there is a paper on it from Mark England or not. I just don't remember.
So I think I'm going to close this session. But first, I think, we're coming, a lot of what I heard about this, trying to pull apart the role of internal variability versus the force response, it's important. But I think one thing, that this workshop that I think has been the focus is bringing together both the Arctic and Antarctic. And I think there are questions like Alice was alluding to, there have been some model simulations that have been run for the Arctic, maybe not for the Antarctic. So I think maybe, in asking these questions about internal variability at the two poles and how it's represented in models differently, maybe there's something to learn there by comparing how the models behave at the two poles against one another. So I think I've taken some notes. I'm sure Heiss has taken some notes, but around those lines, I think there's definitely some things that we can think about and keep discussing as we move throughout the day and throughout the rest of the workshop. So with that, let's thank our speakers again, Lettie, Chad, and Stephanie. And now we have a 30-minute break. Thanks. Coffee's in the atrium.
Okay, so we're doing session 2, causes of polar amplification and asymmetries. So of course, we don't just want to know that polar amplification is happening, but we want to understand why it's happening. And here what we mean by asymmetries is both seasonally, right? We have greater warming in the winter than in the summertime. And also the Arctic warms more than the Antarctic. So we're gonna have 3 talks by Lily Hahn, Po-Chun Chung, David Clemens-Sewall. And first is our invited talk. Our own Lily Hahn is going to be talking about understanding seasonal asymmetry in Arctic climate change.
Great. Okay. Thanks. I'm very excited for this session and workshop. I'm a NOAA Climate and Global Change postdoc at Scripps, and Lettie gave a great overview of some hemispheric asymmetry in polar climate change. Now I'm going to focus on seasonal asymmetry and focusing on the Arctic. And this is work, I'm going to include some work that I did as part of my PhD at University of Washington, working with Kyle Armour and Aaron Donohoe, who are here, and also David Battisti, CC Bitts, and others. So starting with some historical temperature trends in the air interim reanalysis and SIMIP6 models in the Arctic. We know that the Arctic has warmed most near the surface and in wintertime. So one key question here is what drives this pattern of peak winter warming? And another question I'll look at is how is Arctic warming in wintertime and also year-round impacted by atmospheric heating in different seasons? This warming that we've seen historically, this pattern has also been found under CO2 forcing in the future. And here I'm showing near surface temperature over non-land surfaces north of 90 in the CESM2 model. Here we're looking at a pre-industrial control run, but I'll also show different periods for a 1% CO2 experiment where CO2 concentrations are increased by 1% per year up to a quadrupling of CO2. And we'll look in the bottom panel at the near surface warming in comparison to that pre-industrial control run. So we can see for this doubling of CO2 that there's, again, stronger warming in early winter compared to summer. And specifically, this peak warming in winter is happening in early winter, early on. As we continue to increase forcing and Arctic warming, we can see that that peak warming is shifting to later winter with greater warming. And this feature has been found not only in CESM2, but also across other SIMIP6 models and across several single model initial condition large ensembles. So here I'm showing a result from Holland and Landrum in 2021, looking at some of those different large ensembles. And we're looking at 20-year running trends under RCP 8.5 forcing in the future. So we're looking at the seasonal pattern of warming over time. And we can see across these different models that this peak warming that starts out in early winter, later on is shifting to late winter. And this has also been found in these other studies. So we'd like to understand what drives this pattern of Arctic warming. Some potential mechanisms that have been proposed so far are seasonal ocean heat storage, where when we add CO2, sea ice melt in summer increases solar input, which warms the ocean, and then that energy gets released back to the atmosphere in winter through increased turbulent heat fluxes when the atmosphere is colder. This goes hand in hand with ice insulation effects, where the idea is that there's increased conductive heat flux through thinner ice. And because you have both cold temperatures and thinner ice in early winter, this would produce a peak early winter warming. Others have proposed that long wave cloud and temperature feedbacks that peak in winter are contributing to this winter peak in Arctic warming. And so here I'm showing a schematic for the lapse rate feedback where in the Arctic in winter time, we start out with these really stable near surface temperature inversions that prevent vertical mixing, so that for an initial warming, that warming is trapped near the surface. And as a result, the extra outgoing long wave radiation to space is really inefficient because it gets more attenuated by greenhouse gases and clouds than if it were a uniform warming throughout the atmosphere. And so this produces extra surface warming and a positive lapse rate feedback. And the idea is that these winter peaking feedbacks could produce a winter peak in Arctic warming. Lastly, today I'll focus on this mechanism of increasing effective heat capacity of the surface layer in the Arctic. And so the idea here is that we start with frozen sea ice in early winter in the Arctic that acts like land and that it's really quick to warm up and cool down seasonally. And it has a really small effective heat capacity. When we transition to open ocean with CO2 forcing, we're now coupling a deep ocean mix layer with surface heat fluxes. And so this ocean mix layer has a larger effective heat capacity, and it's much slower to warm up and cool down seasonally. And as a result of having a slower cool down in early winter, there's a relative warming in that period that's producing this peak early winter warming in the Arctic. It's really difficult to pick apart these different mechanisms in comprehensive climate model experiments. So today I'll also show some idealized experiments in a single column sea ice model to try to isolate some of these mechanisms. So I'm going to use the Eisenman and Whitlow 2009 single column sea ice model. And this model involves the surface enthalpy, which for enthalpy less than 0, there's sea ice in this model, and this represents the latent energy of sea ice. For enthalpy greater than 0, this represents the sensible heat of the ocean mixed layer. And this is evolved in response to the surface energy budget. So there's absorbed solar radiation, outgoing long-wave radiation, a constant basal heat flux, an ice export term that's proportional to the enthalpy. And then we can also add a forcing term that we increase from 0 to represent increased CO2 forcing in the Arctic. Just to note that the albedo is a function of the enthalpy and varies smoothly from a ice to ocean albedo. So how is the surface temperature calculated in this model? So there are 3 different regimes. When the enthalpy is less than 0 in this first regime, when there's frozen ice, the temperature is calculated from a balance of the surface energy fluxes and conductive heat flux through the ice. But if that balance would give you temperatures above 0, when you still have ice, the temperature is set to 0 while the ice melts in this melting ice regime. And then lastly, once the enthalpy is greater than 0, temperature is just calculated proportionally to the enthalpy divided by the effective heat capacity of the ocean mix layer. So because we want to explore seasonality in this model, it's important to know what it includes that could impact seasonality and warming. So it does include some seasonally varying climate feedbacks. It has changes in ice insulation and conductive heat flux as sea ice thins. And it also has changes in surface effective heat capacity as sea ice melts and exposes open ocean. But it doesn't include a lot of other climate feedbacks in the Arctic or changes in polar heat transport. So we would expect for a given forcing to have less warming in this idealized model, just because we're missing a lot of positive feedbacks that contribute to warming in a more comprehensive climate model. So how does this model do in comparison to comprehensive model? Here I'm again showing surface temperatures for that 1% CO2 experiment in CSM2 compared to in different periods of that experiment compared to the pre-industrial control to get this surface warming at the bottom. And this is similar to what I showed before, but here I'm just focusing on 90 degrees north for better comparison with a single column model, which is using parameters from the Central Arctic. And so when we look at the single column model for a range of forcings to represent different states from having frozen ice to open ocean, we can see that despite missing a lot of the feedbacks that are included in this more comprehensive model, the single column model still produces this pattern of peak early winter warming that shifts to a peak in late winter with increased forcing. So it looks like this will be a useful tool to try to pick apart different mechanisms that are contributing to this warming pattern in the Arctic. The first thing I did was get rid of seasonality and feedbacks in this model by using an annual mean Planck feedback and constant ice albedo. And we can see that even without any seasonality and feedbacks, we still get this seasonal warming pattern of peak winter warming. And part of, just as a reminder, for temperatures less than 0, that's where you have frozen ice in this model. And so over frozen ice, part of this extra warming could be coming from conductive heat flux through the ice, increasing as the sea ice thins. So to test that, I used a constant ice depth in the conductive heat flux. And then we can see over frozen ice in these green boxes that we get less warming and constant warming over frozen ice. So we do see a role for conductive heat flux supporting peak early winter warming over frozen ice. But interestingly, even with constant warming over frozen ice, just the transition from frozen ice to open ocean gives us this peak early winter warming in this model. And then as that transition from frozen ice to open ocean happens later in winter, this shifts to a late winter peak in warming. And so this suggests that there's something fundamental from transitioning from frozen ice to open ocean that's producing this pattern of warming in the Arctic, which is consistent with the idea that the increasing effective heat capacity is producing this pattern of warming. Yeah, so the next thing I did was to explicitly try to model these changes in effective heat capacity by using an even simpler version of the single column model, where we have no sea ice and only an ocean mixed layer. And then we can control the effective heat capacity by changing the mixed layer depth. I've again gotten rid of other things that could contribute to seasonality and warming by using annual mean Planck feedback and constant ice albedo, and there's no conductive heat flux here. So that I'll show experiments with a shallow mixed layer depth representing the small effective heat capacity of frozen ice with this symbol here. And then also an experiment with a deeper mixed layer depth representing the large effective heat capacity of open ocean. And lastly, an experiment that represents the transition from the shallow mixed layer depth for frozen ice to a larger mixed layer depth for enthalpy greater than 0 for open ocean. So what do we see for the shallow mixed layer depth? We can see for a variety of forcings that we have pretty fast warming and cooling seasonally. If we have a larger mixed layer depth, we slow the rate of seasonal warming and cooling. But we can see for both of these that the pattern of warming for each of these forcing experiments compared to the 0 forcing experiment is seasonally constant. So what happens when we allow for a transition from this small effective heat capacity representing frozen ice to the larger effective heat capacity of open ocean? We can see that we get a much slower seasonal warming and cooling over open ocean compared to frozen ice. And this gives a really big difference between temperatures over open ocean and frozen ice that produces this peak early winter warming as we transition from frozen ice to open ocean with increased forcing. And then again, that warming shifts to late winter when your transition from ice to ocean is happening later on. So the main takeaway from this is that effective heat capacity changes alone can produce the seasonal pattern of Arctic warming. And others have found that this mechanism is consistent across fully coupled CMIP5 models in Sejas and Taylor 2023. We also looked at a GCM experiment to try to add some other feedbacks into the mix, which I won't talk about here, but are in this paper. Yeah, so coming back to this first question of what drives the winter peak in Arctic warming, we saw that the increasing effective heat capacity of the surface layer alone can produce this pattern, but also saw that this warming is amplified by increasing conductive heat flux over frozen ice. And in GCM experiments, we also found a role for the lapse rate feedback in amplifying this winter warming. Next, I'll talk about how this winter Arctic warming is impacted by other seasons and how, in general, this atmospheric heating in different seasons impacts Arctic warming year-round. Coming back to this plot, because of this winter peak in Arctic warming, a lot of studies have focused on the winter mechanisms that increase Arctic warming. But we also know there's a huge role for summer sea ice loss in producing Arctic warming. And we expect summer atmospheric heating to drive winter warming by melting sea ice and supporting a transition to open ocean in early winter. So a question that I'm really interested in is how does seasonality in radiative forcing, feedbacks, and heat transport impact Arctic warming? So how does a given season of radiative heating impact warming in other seasons and annually? Some work on this by Bintanya and Cricken applied an artificial long-wave forcing to Arctic surfaces in each season. And they found that the spring and summer seasons were most effective at producing annual mean the largest Arctic warming. And that was because they produced the largest ice albedo feedback and the largest change in surface net shortwave radiation. And then this also produced strong winter warming via seasonal ocean heat storage. And so I'm going to do something similar to these experiments, but I'll apply a 30 watt per meter squared long wave forcing to non-land surfaces north of 70 in each month instead of each season using the CESM sub-ocean model. And I'm also going to test the sensitivity to the mean state climate and the sign of forcing. So if we start from a pre-industrial control or starting from doubled CO2 conditions, how do our results change? And also positive or negative forcing. I also complemented this with some simpler models to try to pick apart robust physical mechanisms across the model hierarchy. But today I'll focus on these GCM results. Ooh, interesting. I think the MAC transition has done something here. But yeah, so a main result when we look at the impact of each of these monthly forcing experiments on annual Arctic warming, we find that the June forcing experiment produces the largest annual Arctic warming, about 4 times larger than forcing in October. So kind of an outsized role of early summer forcing for Arctic warming. Even if we're focused on winter warming in the Arctic, we find comparable winter warming for a June forcing compared to a forcing in wintertime. So this is suggesting that even to understand wintertime warming, we should care about processes that are happening in early summer. Another question is, why does this June forcing produce the largest annual Arctic warming? And so here we're looking at, in different colors, different forcing experiments. The June forcing experiment, July and May, and then other months. And we're looking at the monthly response of the surface net shortwave radiation compared to a pre-industrial control experiment. So we can see that the June forcing experiment gives the largest annually integrated change in surface net shortwave radiation. And that's despite having large changes in the surface albedo later on in September for most of these experiments when we have more sea ice loss. But the reason for this, like the effect of June forcing being largest, is that the insolation to start out with is peaking in June. And so when we multiply that by the albedo changes, our June forcing is having the largest effect in producing the largest change in surface net shortwave radiation and also the largest annual mean warming. Looking at some anomaly maps for our June experiment compared to the pre-industrial control, we can see that these changes in shortwave radiation at the surface are coming mainly from changes in snow fraction and less from sea ice area changes. If we look later on in September, there's much larger changes in surface albedo, snow fraction, and sea ice area, but the impact on the surface net shortwave radiation is smaller than in June, again, because we have just a larger amount of incoming sunlight in June compared to September. So this is fitting with the story of having this peak insolation in June producing this big impact of June forcing in combination with snow melt in June. Lastly, we looked at sensitivity to base state and the sign of forcing. So in addition to starting from an 1850 base state, I also started from a doubled CO2 base state, and we're looking at each forcing experiment compared to just a doubled CO2 experiment, and looking again at annual Arctic warming. And we can see that summer forcing, when we start out warmer, produces a smaller effect on annual mean Arctic warming. And there's also a shift backwards in the timing of the most effective forcing from June to May. And this is because our sea ice area is much lower in the 2 times CO2 base state in this black line compared to the 1850 base state. So there's just kind of a smaller capacity to lose sea ice and a smaller capacity to warm when we start from the doubled CO2 state. And the May forcing is now able to have a larger effect than June. So in addition to looking at the role of different base states, we also looked at the sign of forcing, sensitivity to that. And kind of a main takeaway here is that summer forcing has the biggest effect if we start from a cold base state and add a positive forcing, or if we start from a warm base state and add a negative forcing. And that fits with the story of having the largest albedo changes in those experiments and having the largest changes in absorbed shortwave radiation. So just coming back to the second question of how Arctic warming is impacted by atmospheric heating in different seasons, we saw that early summer radiative heating produces the largest annual mean Arctic warming and comparable winter warming to winter radiative heating. That's the main point. Some implications of this is that we expect early summer processes to be particularly important for future study and expect important impacts of non-winter heat transport forcing and feedbacks on winter warming. So I would be interested to see things like how the summer atmospheric heat transport to the Arctic impacts winter warming. Kind of a broader takeaway from these two parts is that we wouldn't have seen either of these if we just did kind of a traditional feedback analysis, because this type of diagnostic analysis excludes any physical process that doesn't appear in a radiative budget, such as these changes in surface heat, effective heat capacity. And it also excludes interactions between mechanisms in different seasons if we just look at feedbacks in the winter season. So yeah, we would exclude these summer feedbacks that impact winter warming. So as others have said, this kind of highlights the importance of using alternative frameworks, simpler models, and idealized experiments to try to better understand and predict polar climate change. Well, that's all I have. So hopefully we have time for questions.
Thank you for such a nice talk. I was wondering in this model, what the upper ocean stratification looks like, and does it change in the future, and is there a role then for that?
Yeah, are you thinking do you mean in the first part when we look at the role of effective heat capacity?
Or this summer to winter effect of the summer warming, if the stratification has changed in the ocean, is that also a player?
Yeah, that's a good point. Yeah, I haven't looked too much at ocean stratification in the second part, but can definitely look at that. I will say for the first part, we kind of looked at sensitivity to mixed layer depth. So I just showed results from transitioning from a 1 meter to a 50 meter ocean mixed layer. But I also looked at sensitivity to like variations in the mixed layer. But we found that the largest sensitivity is like for a transition from, like, for example, 1 meters to 10 meters, but there's less sensitivity for changes as the mixed layer depth gets larger. So it didn't, there wasn't like a huge sensitivity to mixed layer depth for these experiments. Yeah, but that's a great idea to look more at dig into ocean stratification in the second experiment too. Yeah.
Hi, Lily. Great talk. I'm wondering how the mean cloud state could impact the sensitivity in the summer. I'm thinking about how CAM4 is missing a lot of clouds, and if it's kind of a feedback related to the surface albedo. Do you think that, like, if you were to play with the cloud state, if it would kind of flatten some of that seasonal curve you showed?
Interesting. Yeah. I guess one thing that would matter is like your incoming or is just like your insolation. So if you had, I think changing cloudiness in your base state would impact that, and that like has a huge effect on how much your albedo changes matter. So yeah, I would guess just like the mean state cloudiness would impact our results through that. Like they would mediate the effect of that early summer forcing. But and then I think I may have missed like the second part of like sort of your hypothesis of how the how cloud differences would impact
Yeah,
things.
so if there are more clouds in the summer, would it flatten like the big kind of seasonal curve in the sensitivity then?
Yeah, I think so just because of through reducing your like surface insulation, I think you would have a smaller impact of the summer forcing. So yeah, I think that would flatten things out. But yeah, I guess there's also a question of like cloud changes under the forcing. Yeah, that's a great point of how, yeah, and maybe it would be good to like look across the different generations of CAM and how that like insulation changes. Yeah.
Hi, thanks for the talk. Maybe I'm jumping ahead, but I'm wondering if you've looked at in your atmospheric heating experiments, how the seasonality of the heating impacts the lower latitudes. Have you looked at those?
Yeah, no, I don't think so. But that's an interesting question of I think I had a similar question when giving this talk before of sort of the idea that maybe another reason for differences between different seasonal forcings is that they impact or like heat transport away from the Arctic responds differently depending on the season of your forcing. So I think that's also something I want to dig into. I haven't yet done like a feedback or heat transport decomposition in these experiments, but I think that would be really interesting if heat transport is responding differently to different seasons. Yeah.
So going back to the stratification, actually ranges of 10 to 50 meter mixed layer depth in the Arctic are happening currently, and they're happening seasonally. So actually your sensitivity is already taking place in the Arctic. Summer mixed layer is roughly 5-10 meters, and winter mixed layer is order of 50. And my question is that, have you considered, because you said that most of the heat capacity is represented in your simulation by varying the mixed layer depth. Given that that range that you used is already realistically present in the current nature, my question is just, have you considered looking into changing the temperature of the upper mixed layer for a fixed mixed layer depth? And the other question is, most of the heat which is accumulated through the summer is along the periphery of the ice as it's shrinking, which is happening on the marginal shelf seas. So those are shallow seas, and there's a dynamical barrier communicating the shelf water from those shelves to the deep basin. So amount of heat which is remaining into the fall in the shelves might be also dependent on the transport across the shelf break from the shelf into the deep basin. So there's other factors that might be influencing the sensitivity in terms of the heat capacity and its impact on your studies.
Yeah, that's great. Yeah, we didn't look at like the impact of like spatial variations in mixed layer depth. Like we were just using a single column model that represents like one point in space. But that's a good point that yeah, to look at. As I was saying to Clara, we found like not a huge sensitivity to differences in mixed layer depth, other than going from like this really shallow mixed layer representing frozen ice to having open ocean. There was like less of a sensitivity for like a broad range of ocean mixed layer depths, but I do think it would be interesting to look more into, there was like some sensitivity to that. So it would be interesting to also look at like how biases in mixed layer depth and climate models impact the seasonal pattern of warming. Yeah. Yeah, this is great points that there's like spatial variations to think about. Yeah.
Well, we're at about 11:15, so let's move on and save some more questions for the discussion. Next is Po-Chun Chung from UC Santa Cruz, talking on sea ice loss, water vapor increases, and their interactions with atmospheric energy transport in driving seasonal polar amplification.
I'll go back for you.
Yeah, sure. Okay, sorry. Hi, I'm Po-Chun. I'm a graduate student from UC Santa Cruz. And today I'm going to share my work about sea ice loss, water vapor increase, and their interaction with energy transport in driving seasonal polar amplification. Yeah, as we know, the polar amplification is a robust feature of global warming. And it presents a strong seasonality. Region is maxima during winter and minima in summer. And there's some popular framework attribute polar implication to ice albedo feedback and lab rate feedback. Like this figure shows the contribution to each feedback to warming. So the combined mechanism of albedo and lab rate feedback have been mentioned to explain polar implication. Other process like water vapor feedback and dry and moisture energy transport are also important. So some study emphasize the water vapor might cause the polar implication by amplifying other positive feedback in the polar region. And these positive polar feedback might decrease the polar dry energy transport. However, it is still unclear how these feedback and transport manifest and interact seasonally. So here we use a radiative transport hierarchy to an idealized GCM coupled to a thermodynamic CS model. So in this model, the thermal flux at top and base and through the CIs are read to simulate the CS activity. So including the ice albedo feedback and ice thickness change. So, and here we use the oceanic core planning with seasonal insolation and no color and no Q flux in our model. And the radius scheme is RTM, which is widely used in climate model. So by comparing the control and the frozen, which is 4 times CO2 here, we got a response to CO2, water vapor, and CS loss. And this we call it total response. And then we run the ice log simulation. So in this case, we fix the ice. So ice will not change with frozen. So by comparing A and B, we can get a response to CS loss. And we further replace the RTM with radiation scheme, which exclude the water vapor feedback. So here, by comparing B and D, we got a response to water vapor radiative effect. Okay. And finally, we run an ice fraction log. So we fix the ice fraction, and but the ice thickness still can change. So in this way, we can separate the response to CS loss into response to CS thinning and response to CS retreat. Okay, here's our model framework. Okay, so first I'm going to share some temperature response, and then we'll dive into the mechanism. So, in this way, we can separate the total response into response to CO2, water vapor radiative effect, and CS loss. And CS loss can be further decomposed into CS retreat and CS thinning. Okay, so in total response, we can find some classic warming pattern, including tropical warming in the upper troposphere and polar amplification. So the former is from water vapor radiative effect, and the polar amplification is from CS retreat. And then we move on to the seasonal surface temperature response. And the x-axis here is season, is months. So we can find that response to CO2 and water vapor, water vapor radiative effect present a weak seasonality. And the strong seasonality in total response is from CS loss. So that includes winter warming from CS retreat and winter warming and summer cooling pattern from CS thinning. And this, the CS thinning pattern is because the melting sea ice will suppress the summer warming, and the increasing conductivity flux because of thinning ice will cause the winter warming. And this pattern is consistent with previous study. I think Lily has just mentioned it. Okay. And okay, so to figure out the physical mechanism, we apply the warming contribution method. So generally speaking, the surface temperature anomaly is attributed to forcing conic feedback, dry and moist energy transport, and surface energy budget, which is the ocean term since we use aqua painting here. Okay, so then this figure shows the annual mean warming contribution to different response. Okay, so in total response, we can find the, of course, we can find the strong polar amplification, and the albedo feedback is the dominant term. And the moist transport plays a moderate role, and the water vapor feedback and the dry energy transport contribute to tropical amplification. So generally, this basically it is consistent with previous study, except for the small left feedback in our model. And then we can find that most of the dots are captured by CS retreat. So including the strong albedo feedback and the decrease in dry energy transport. And in response to water vapor radiation effect, we find that the water vapor feedback contribute to tropical amplification, and the moist transport contribute to polar amplification. So that is because the moistening in tropics will increase the meridional moisture gradient, and then increase the moist transport to the polar region. So that's why the moist transport here contribute to polar warming. And the combination of two cause a uniform warming since the black dots, the TS is close to 1-to-1 line. Okay, here we move on to the seasonal polar warming contribution. So the dots above 1-to-1 line means this feedback contribute to wintertime polar warming, and below C mean contribute to summer polar warming. And I want to start the story from CS retreat since it captured the patterns again. So we can find that the albedo feedback and the ocean and dry energy transport are the primary terms. And here you can find albedo feedback contribute to summer warming. It is balanced by ocean heat uptake. And during winter, the ocean releases the heat back to the atmosphere and cause the wintertime polar amplification. And this polar amplification further induces a decrease in dry energy transport. And in response to CS thinning, we can find that the surface energy budget leads to a winter warming and summer cooling pattern. And this summer cooling slightly increase the dry energy transport. So we'll show the seasonal dry energy transport pattern later. And yeah, here's the decomposition of seasonal surface energy budget. So during summer, when CS retreat, the ocean absorb the downward surface shore wave during summer and release the heat during winter, and cause the wintertime polar warming. And this polar warming, this winter warming, trigger the upward turbulent flux, and this is consistent with previous study. And okay, so back to this panel. So in response to water vapor radiation effect, we can find that the water vapor feedback contribute to summer warming, and the moist energy transport contribute to winter warming. This figure shows the seasonal specific humidity anomaly. So we can find that the moistening in the summer hemisphere, of course, it leads to the water vapor feedback in summer. You also increase the meridional moisture gradient in winter and trigger the moist transport in the winter hemisphere. So that's why we can find the moist transport term the blue diamond there contribute to winter warming. And again, the cancellation between water vapor feedback and moisture transport also works in seasonal polar warming, since the black dot is close to 1-to-1 line again. Okay, and to further understand the role of remote interaction with polar implication, we diagnosed the seasonal energy transport. So here shows the dry component of energy transport. So of course, the total response presents a strong seasonality, and is from CS loss. Of course, it includes the CS retreat and CS thinning. And we can find that like these patterns are highly related with the surface temperature, the seasonal temperature response. So, like for example, the winter warming causes a decrease in dry transport, and the summer cooling causes a increase in dry transport. Okay, and here we move on to the moist component of energy transport. So we can find the moist transport is stronger in winter in total response, and this seasonality is from water vapor radiative effect. And yeah, we have talked about it is because of the stronger meridional moisture gradient in winter. Okay, brief summary. We separate the effect of CO2, water vapor, CS retreat, and CS thinning to prolongation by the hierarchy of idealized models. And during summer, the ice albedo feedback trigger the ocean heat uptake. And in winter, the ocean releases heat, cause polar amplification. And the wintertime polar warming reduce the meridional temperature gradient and cause a decrease in dry energy transport. And the melting sea ice will suppress the summer warming, while the winter sea ice thinning cause the wintertime warming through the increasing conductive heat flux. And the moistening in southern hemisphere causes the summertime water vapor feedback. It will also trigger, also increase the moisture transport during winter, and they cancel the seasonality of polar warming. And finally, the change in seasonal dry energy transport seems to be a passive response to seasonal warming pattern. Okay, and our result highlight the importance of the interaction between feedback and energy transport on the seasonal polar implications. So, and hope it will improve our understanding of the mechanism. Okay, and that's it. Thanks for your attention.
All right. Thanks, everyone. Yeah, so thanks for the introduction, Aaron. David Clemens-Sewall at NCAR. Before I begin, I'd like to thank all my co-authors up here, contributed various things to this work. And I'd also like to thank everyone in the sea ice modeling community and who's been involved with these large-scale field campaigns. It takes an enormous amount of work to basically produce the raw materials, whether it's data or modeling tools, to do these kinds of studies. So I want to talk a bit about the sea ice sensitivity in the new Arctic, and maybe I should have said the new and old Arctic here, because we're gonna kind of look at a little bit at ice states going all the way back into the 50s and 60s. And so the inspiration, or why I got interested in this topic, actually comes from an observation that Ian Raphael made when comparing the atmospheric measurements at Mosaic and Sheba, which are two large ice drift experiments separated by about 25 years. 25, something like that. Yeah. And what Ian noticed was that the surface air temperature time series at the two on the two campaigns was actually very, very similar. So the middle plot here is showing the freezing degree days, so basically the cumulative sum of air temperatures below freezing for the two expeditions. And you'll notice they track each other very closely, differ by a couple percent at most. And coupled with this observation, we also noticed that the first year ice growth at the two expeditions was quite similar. There's only a Mosaic, the first year ice grew just a little bit more than Sheba. But there's a large discrepancy between the multi-year ice, which in the case of Mosaic was second year ice, and at Sheba was true multi-year ice. And so we said, okay, you know, we understand this is an ice thickness, ice growth feedback, great. And then we went and we tried to actually model it. And so what we did was we said, well, you know, the surface air temperatures are so similar, and we also don't have a Sheba forcing right on hand. We just have a Mosaic forcing on hand. Let's try to model, see if we could model the Sheba ice growth using our Mosaic atmosphere and ocean forcing, but using initial snow and ice conditions and precipitation from Sheba. And this worked great for the first year ice. For the first year ice, we were able to, you know, even just using the Mosaic forcing, we were able to more or less recreate the Sheba ice growth within about several centimeters. However, when we tried to do the same thing for the Sheba multi-year ice growth, we found a much larger discrepancy here, where now using the Mosaic forcing but the Sheba initial snow and ice conditions, we only were able to explain about half of the discrepancy in ice growth between Mosaic and Sheba. And so this is what got me thinking about this topic and what I wanted to share here today, which is a little bit of an exploration of the sea ice sensitivity to different processes is impacted by the ice state. And I think this is especially important considering the transition we've observed in the Arctic from a thick, perennial ice state into our current, more thinner, increasingly seasonal, and also going into the future. And so as I alluded to already, the methods we're going to use are data sets that were collected on the Mosaic expedition, primarily. We'll also use initial ice conditions from a few other expeditions. Probably most people are aware, but Mosaic was a really large multinational effort led by the Alfred Wegener Institute in Germany, in which we were fortunate enough to be able to freeze the German icebreaker Polarstern into the ice up in October 2019, and then we drifted with the same collection of ice flows for the better part of a year. The measurements I'll use here for this forcing were primarily collected by the Met City team, doing a lot of work along with our mass balance measurements from the stake sites. The model that I'm going to use here is called IcePack. This is the column physics component of the SICE sea ice model, which is used in about half of the CMIP6 models. And IcePack's a basically fully featured thermodynamic column physics model. So we have prognostics, temperature, and salinity profiles. We represent the ice cover with an ice thickness distribution, along with many other parameterizations. And just so everyone's sort of clear on the setup here, we're going to use IcePack in a standalone single column mode forced by atmospheric and ocean measurements. And so, like I said, the atmosphere measurements are coming from Met City. We're going to, in this case, use actually prescribed ocean conditions, but inspired by the real measurements. And then the snow and ice measurements also came from the ground. One of the reasons we're going to use this is because we've done a fair amount of work trying to validate IcePack for the Mosaic case in particular. This top plot here is showing the ice thickness evolution throughout the winter as simulated by IcePack in the solid blue line, and in observations from mass balance sites in the error bars. Originally, when I'd planned to talk about this, I'd planned to talk about winter and summer, but we're still working on getting the model to perform really well in the summer and match the observations. So I'm actually just going to focus on the winter for here. And the remaining plots here are just showing that we're also getting the major surface energy balance terms very similar to the observations. Okay, and so what I'm going to show in the remainder of the talk here are some results from these kind of idealized IcePack simulations using the mosaic forcing, but with different initial ice conditions, so that we can see how the ice evolution responds when we change parameters in the model. We're going to use 5 different ice conditions, all initialized on November 28th. And so that's going to be, we have open water, right? No ice, no snow. Ice conditions inspired by the mosaic first-year ice, which was just shy of 30 centimeters ice thickness at this point, and about 2 centimeters of snow depth. The mosaic second-year ice was about 80 centimeters in late November. Xiyue was about a meter thicker, 1.76 meters. And then finally, just to really explore kind of the transition in the Arctic ice state, I'm also going to use some observations that were made at Ice Station Charlie, which was about another meter thicker in November, about 2.78 meters. These plots in the middle here are showing the ice thickness evolution monthly as simulated over the course of the winter. And one of the things I think is kind of interesting here that we also observed in the field, simulations indicate this sort of catching up behavior between all of the mosaic cases. So open water, first-year ice, and second-year ice on mosaic, all basically by the end of the winter had more or less the same ice thickness, which was, and the model shows this as well. One other note here, I've chosen to initialize the Xiyue and Ice Station Charlie cases with the mosaic snow thickness from second-year ice, because otherwise the primary difference you would see is actually the difference in the initial snow thickness in these results. As a primarily ice scientist, I mostly think about impacts on the sea ice and the sea ice thickness, but obviously what happens in the ice in the ocean has a huge impact on the atmosphere as well. So I'm also showing on the right here the net air surface heat flux. Negative values indicate a heat flux to the atmosphere. So you can think of this as admittedly an ice-centric perspective on air surface heat flux. And those showed the trends we'd expect. We have by far the highest heat fluxes to the atmosphere are happening in the thinnest ice cases early on. And so just to keep things simple and within my time limit, I'm just going to focus on 2 changes here. One of these changes that we made is a change in our oceanic heat flux convergence. So you can think of this as the turbulent heat flux into the ocean mixed layer plus a term from advection. In the default simulations, this is at 1 watt per meter squared. And just to have a change, I wanted to see what would happen if we increase this up to 7 watts per meter squared. This is a forcing in our model setup, but of course in a fully coupled model setup, this would be a change in the ocean mixing parameterization, most likely. And we see a couple different things. First off, maybe it's a little hard to see on the screen, but the impacts in terms of the ice thickness are greatest on the thickest ice categories, which is kind of what we'd expect from first principles. The Ice Station Charlie and Ice Station Xiyue have a greater reduction in ice growth throughout the season. These plots are now showing the differences off of those base states. So red here is less thick ice. Red here is increased heat flux to the atmosphere. However, when we look at the increased heat flux to the atmosphere, we see kind of the opposite trend from the impacts on the ice thickness. We see that the biggest impacts are for the thinnest ice categories. Again, kind of what we'd expect from first principles. The ice is less insulating. There's a bigger impact on the atmosphere here. The other change that we wanted to explore is one we've talked about quite a lot, which is changing the snow thermal conductivity in the model. And so the default value in the model is about 0.3 watts per meter Kelvin. There's I think, really interesting effort being led by Ann Sled over at NOAA to compare all the different mosaic values that were measured in the field of snow thermal conductivity. 0.2 is on the low end of those values, certainly, but is not completely out of the range of plausibility. And now when we make this change, we see kind of a different set of effects. We see that the greatest impacts here are actually on the thinner ice categories, the mosaic first-year ice and second-year ice case, in terms of ice thickness. Interestingly, we actually see a slightly muted impact on the open water case, which I think is really kind of interesting because the difference between the open water and the first-year ice is only 2 centimeters of snow. And so that's, just a small amount of snow can really make a big difference in these simulations. And again, kind of similar to when we look at the impacts in the net air surface heat flux, the impacts again are kind of now most concentrated for the thinnest ice. So, whereas in the case of changing the oceanic heat flux convergence, we had this sort of difference in which ice regime we saw the biggest impacts. Now for changes in snow thermal conductivity, we see that they're both in the thinnest ice regime. And so just sort of in conclusion here, I'd like to say that the sea ice state impacts the modeled sensitivity. So as I said before, we saw that the thicker ice categories, for those, the growth was more sensitive to changing oceanic heat flux than the thinner categories, whereas the opposite pattern was observed for the changing the snow thermal conductivity. You could imagine many other changes in the parameterizations could have similar differing effects based on ice thickness. And also which metric that we use matters a lot too. So if we're imagining, tuning our model so that we get, say, a ice thickness that matches observations better, we have to be careful that we're not introducing changes that might also, cause unexpected changes in the net heat flux to the atmosphere. I'm hopeful that single column modeling can be used as a tool to help investigate these sensitivities, both for planning future measurement campaigns and also when we think about tuning. It's a lot cheaper to run single column simulations than larger scale model simulations. And it looks like maybe the wrong version I uploaded, but the last point is supposed to be that more forcing data sets would be helpful for this. So we're working on the mosaic data set right now, but it'd be great to have an Ajax and Sheba, and for future campaigns to think about putting together these forcing data sets for doing model evaluation and exploration. And so with that, thank you all very much for listening. I'd be happy to take any questions now or later.
Any question for David before we start the discussion?
Sorry, it's really tall. I don't really fit under these tables very well. So excellent talk, David. So I know I have a lot of questions, but I wanted to, this might lead us into discussion a little bit, but I was curious if you could maybe expand upon what is meant by forcing data sets and all the components of those. I think that could be helpful for the discussion to understand what observations are useful in terms of understanding these sensitivities to sea ice thickness.
Absolutely. Yeah, thanks for the question, Patrick. So it's going to depend a little bit depending on what model you're running, right? If you're running a standalone sea ice column model versus if you're running, say, a coupled atmosphere ice column model. In the case of the sea ice column model, the the forcings we need from the atmosphere are basically downwelling long wave and short wave radiation, wind speed, specific humidity, and air temperature, and kind of at some reference height in the atmosphere. The oceanic forcings we need are basically the ocean mixed layer salinity and the heat flux convergence into the mixed layer, as well as the mixed layer depth. And then another aspect that we're still working on might be some of the most complicated forcing to have is actually the lateral boundary conditions when you're, right, so if you're trying to simulate a grid cell within a climate model, the ice dynamics would cause ice to come into and out of the grid cell laterally, and figuring out how to have good observations of that for forcing these models would be really interesting. I'm not actually doing that here. I'm just using just exploring the thermodynamic changes, partially due to the challenges with the lateral boundaries.
Well, let's thank all our speakers again. And if I could have Lily and Po-Chun also step on the stage so we could get started with the discussion. Any questions for the speakers or from online?
Everyone, I can kick this off. Kyle Armour here. I'm just trying to kind of reconcile with what David was just talking about with what Chad was talking about earlier. So I think Chad showed us strong evidence that there's a correlation between climatological albedo and albedo feedbacks in the Arctic. Do we have a sense of whether the spread across models in albedo is coming from sea ice parameterizations, or is it coming from other things like snow depth or other climatological things like the cloud cover? If we can answer that, maybe we can make some progress on how to constrain feedbacks. It's kind of a question for everyone, but maybe David could sort of.
Sure. Yeah. Thanks very much for the question. I mean, I think one of the challenges with something like albedo, right, is that there are so many processes that end up impacting the summer albedo. And it's not just processes that are happening right in the summer, as Lily nicely showed. And so I guess the short version is I don't have an immediate answer to your question of like what's the driver of it, but I think it's a really important question to answer. And I think part of the way I propose we get there is really taking a close look at the albedo parameterizations in the models and comparing them with the observations in kind of as granular a manner as we can. So making sure that we do have a consistent initial snow condition between a forcing or between a model simulation and observations, and then trying to tease out those differences.
Let me respond to that quickly because I have a postdoc who's looking at this. So one of the things we've been comparing the sea ice albedo in AMIP versus CMIP versus series, right? And in AMIP, as we know, the sea ice concentrations are all the same across the models, but we find quite a spread in the surface albedo still. And so we attribute that to the snow on the sea ice and those differences in models. So the importance of precipitation on the snow is a big factor, is one of the factors, but there are many. There are many.
Isn't also the sea ice thickness is treated differently in different AMIP simulations? I think like some models, like definitely they prescribe the sea ice area, but I think they're doing different things with sea ice thickness. So yeah.
I mean, I think that's the case. That's definitely true in reanalysis, that different reanalysis products prescribe different ice thicknesses, and the way they treat snow on sea ice is also different. So, you know, the fact that the sea ice state influences the fluxes to the atmosphere leads to some uncertainty in terms of how those reanalysis products, but also AMIP runs deal with their sea ice state. Yeah, I think that's important. I just wanted to mention, I think, we've seen amazing results this morning, and I think in both sessions. And I also think this conversation we're having right now suggests that we might have some good input on how we can improve our models, right? Where are the biggest uncertainties? What might we tell modeling centers? I mean, we sit at NCAR, we develop a climate model here. What, in terms of accurately simulating polar amplification, do these models need to get right? And so I think that's something that this workshop really could help inform. And I think, it'd be interesting to hear from you guys what you think your main results are in terms of the impacts for what we need in our models, what we need them to do right.
Yeah, I would say from the seasonal forcing experiments, it was clear that getting those early summer processes right will be really important in climate models, as others have thought before. But things like melt ponds, snow melt, how that's dealt with in climate models will be important, which is maybe counterintuitive because we know the warming is greatest in winter. But yeah, I think that's a good seasonal spot to focus efforts on.
Yeah, I'll second what Lily said. I think the models are very sensitive to anything that impacts the albedo right at the start of the melt season. But the things that impact the albedo then are kind of the collection of everything that's happened over the winter, as well as the processes happening right then.
Will Hobbs. Oh, just a point maybe for people who are online, if you're asking a question, just say your name. But I have a question more for the hive mind necessarily than the panel speakers. We talk about these asymmetries in response, these seasonal asymmetries. Does anyone know what the seasonal asymmetry is for the Antarctic? I know what it is for sea ice. We see trends in the summer historically, but not winter. But I don't know about the warming or the temperature. I assume there's not much temperature change in the Southern Ocean generally. Does anyone know? Anyone online?
So I think Lettie has looked a bit at base state seasonal asymmetry in the Antarctic versus Arctic. So could talk to that. Yeah, it would be cool to do some of this seasonal warming analysis for the Antarctic too. I would expect similar results over sea ice, but then you also have the Antarctic ice sheet. So I think that'll mix things up. We looked at that a little bit in this flat Antarctica paper, I think in 2020. But I'm forgetting a little bit what we found. But yeah, I think the Antarctic ice sheet will make for some differences with the Arctic. Yeah.
I'll say that seasonally, I've looked a little bit at the sea ice thickness in the Antarctic, and it's less than in the Arctic. So exploring how the thickness itself for these processes that were explained today impact the Arctic versus Antarctic, is key. And it's probably related to the fact that the thickness is less in the Antarctic than the Arctic.
Taking a step back, the point about us knowing what models might be doing wrong, what they might need to improve, I can comment on the issues we've encountered with improving snow albedo over the Northern Hemisphere. The snow albedo feedback example we've known for almost 20 years now, and the certain modeling centers have shown big improvements, and we've looked into sort of down the lines of what Kyle was mentioning, what is actually the line of code in each model that is driving variability across an ensemble. And usually you can point to these things, but getting proper implementation of a fix can be difficult when it is such a sensitive parameter in models. So by fixing the albedo over land, we found that many models will then tinker with ice albedo to try and create some sort of balance. Not naming names of who's done that, but some of the smaller modeling centers can struggle with correcting once this analysis has been done to say, okay, what is the issue at hand? What parameterization do you need to apply or change? Oftentimes there'll be some other correction has to be made to, keep the radiative energy balance at a certain state to have a good simulation of historical temperature. So that's one difficulty we might encounter going forward when we're trying to think of one simple fix for various modeling centers. I just wanted to bring that up in relation to those points.
Well, definitely, I think one of the things that came out from these talks and the importance of it is the sea ice thickness itself, and how important it is to the conductive heat flux, how important it is because obviously if you have more sea ice thickness, it's going to be harder for it to disappear. So the transition from sea ice to ocean is affected by your sea ice thickness and therefore the effective heat capacity. So maybe you guys can talk about the role of the sea ice thickness and particularly how well are we doing? What can we do to improve that observations-wise, modeling-wise, to better capture these processes?
So the CS thing is like, I think the main difference is like you just prescribing albedo, that you cannot simulate the thermodynamic sea ice process. So you will not consider the ice thickness change that lead into a summer cooling pattern, or maybe I should say like suppress the summer warming. So I think my work and like Lily's work like just indicated like the importance of the thermodynamic sea ice, to consider the thermodynamic sea ice process. Yes. So okay, so the I think it's suppress the summer warming is like you when you fix the sea ice, when you fix sea ice in model, the temperature just goes up. But in the ice-free condition, like in normal condition, when the sea ice melt, it absorb the latent heat, so the temperature just does not goes up. So that is the role of sea ice thickness change, that it suppress the warming, and yeah, you cannot see this effect if you just do those tricks on albedo. Yeah, since the albedo simulation cannot simulate the sea ice thermodynamics. Yeah.
Coming at it from the kind of the observational side here, I think we need to have a lot of humility when thinking about measuring sea ice thickness. It is a maddeningly frustrating thing to measure, even when you are in situ in the field. And I think it's important to recognize that there's not probably going to be like one single measurement modality that's going to tell you everything you need to know or everything you want to know from a modeling perspective when it comes to measuring sea ice thickness, right? There's not like that one silver bullet satellite that's just going to go up and provide you everything. And so I think the key is to use different methods. Some of them could be in situ, some of them could be autonomous, some of them could be satellite borne, some of them could be airborne, and really to try to understand what it is that particular observational modality is measuring on the surface. So for example, there are, especially with some of the higher resolution satellites, maybe we can measure something about the changes in the level ice thickness or the level ice freeboard at least, and I look at those and separate those out from the changes in the deformed ice thickness and try to make slightly more granular model comparisons with the kinds of observations we can produce now. But we're not going to have like no one observational product is going to give us everything we wanted to know about the ice thickness distribution for comparing with models. And I think as modelers, we need to maybe be aware of that and sometimes learn just a little bit more about the observations that we're trying to compare with to validate the models, to find the most appropriate aspects of those observation modalities for the processes we're trying to study.
All right, so I might ramble a little bit, but I wanted to go back to what Marika said. So there's a lot of really good information, results here that can hopefully, I think, inform what we do with the models. But to me, I wouldn't know exactly what to tell you, Marika, as to what you should go do, because I think that there's a piece that's some missing connecting it. Like for instance, what David showed, those sensitivities are important, and we can obviously see they're important, but we don't know, like, as far as I know, the simulations haven't been run to see, like, well, if you change that sensitivity of sea ice thickness to ocean heat flux, how does that impact Arctic amplification, right? To go the whole way from this parameterization and these sensitivities to how that could affect the whole system, I think that's a really big jump. But I think, we know thickness is important, and we should try to represent it better in models, but but then going from the other side to the emergent constraint stuff, I also don't know, like, based on the emergent constraint stuff, I could tell you should shoot for that sea ice albedo feedback magnitude that Chad showed that constrains to whatever the number was, the narrower PDFs. But I wouldn't exactly know how to tell you to get there, right? But maybe that's the number we should be shooting for and tuning towards, et cetera. So maybe there's something missing in between for us to take these process levels and kind of these emergent constraint and the future climate change and the process level and try to connect them better so we understand how they all influence each other.
I just jumped in front of Will, but can I respond to that? I think I completely agree. I mean, I think the emergent constraint stuff is a great example that, so we see this effect of the seasonal amplitude of, the albedo changes, that's related to the sensitivity of the models. So where is that seasonal cycle in albedo and the discrepancies across models coming from? Is it the albedo of the surfaces? Is it how much snow they lose in the summer? Is it how much ice they lose in the summer? Those are things I think we could dig into. And if so, then we could say, oh, actually, your annual cycle of ice area looks great, but the snow on top of the sea ice looks crummy. Like that would help us in the modeling community say, okay, we really need to target snow on sea ice, right? So I agree with you. There's like threads coming out of all this work, which I think is amazing. Some of those threads are ripe for, these are things you need to improve in the model. Other things are suggestive of what we should look into further to better understand what we should improve in the models and narrow our model uncertainty, which I think would be a real benefit to all of us. So, and our understanding of, what the errors are in our models, how polar amplification works, all of those questions. I mean, we heard Lettie talk about, we need meltwater from ice sheets affecting our oceans, right? I mean, that's a target we can point to very clearly, but I think there's other things coming out of all this work that we could also point to. I'd also say, like, we have an opportunity here to inform what model and intercomparisons we should be doing. And, there's going to be another CMIP. We're putting together our next versions of CMIP models. We're planning what experiments we're going to do with those CMIP models. We could help inform what those are. So, sorry.
Thank you, Marie.
I guess I've got both a comment and a question. So the comment is referring back to the sea ice thickness and the difficulty of getting satellite retrievals. At least in the Southern Ocean, I assume it's the same in the Arctic, mixed layer salinity is a really valuable constraint on sea ice thickness. And so even if you've got no interest in the ocean at all, as a community, we should be pushing for more under ice Argo observations in both hemispheres, because I think that's a really valuable constraint, particularly if you go down the road of some kind of reanalysis of sea ice thickness. That salinity and mixed layer salinity is going to be a really valuable constraint. That was my comment. My question is, feeding back to the talk about albedo, would we expect those albedo processes, snow processes, to be the same in the Arctic and the Southern Ocean? And, you know, do we need to think about in these model intercomparisons? I've seen model intercomparisons for the Arctic sea ice and the Antarctic sea ice, but I've never seen it like, where do we do better? I suspect I know the answer, but I'd like to see it in black and white.
I'll just comment on your comment. I totally agree. We should try to get more mixed layer salinities from autonomous platforms, and just say that we can, in addition to, you know, Argo type platforms that are drifting, that can also be added to buoys and other autonomous things that are installed in the ice. So just, yeah, it's something to consider when planning the measurement campaigns.
Quickly back to Marika's point, and I guess Pat's point. I've looked at some of the, I guess you can think of it as what's driving the outlier models in terms of the simple things like why are they getting the wrong albedo climatology change over the summer. In many instances, the outlier models that barely change are models that have like August, September sea ice that's 3 meters thick. So completely unrealistic. The albedo only changes by maybe 0.15 over the whole summer. So it's basically those models, there's a number of them that are very, I'll say, resilient to warming, that are the outliers in that case. And I think part of what I was trying to do with the work that I showed earlier is create a simpler metric for modeling centers to benchmark than, say, the seasonal albedo feedback, which can be a bit more challenging to calculate than just something as simple as a climatology that might also be relevant. Because I think, yeah, that's one thing that we need to work on improving, is to create metrics that are easier to be benchmarked by the actual people running the models as they're going through development stages. So I just wanted to add that.
Have you looked at the snow depth on those anomalous models too?
I feel like I did years ago for CMIP 5. I haven't looked at it for CMIP 6. Don't remember a key takeaway. I think I was mainly limited by a lack of good observational data to say what is realistic in terms of snow on sea ice. So that tended to, you know, you just, okay, look at the sea ice thickness, where at least there's some viable data out there. I know there's some of the snow on sea ice reconstructions, but not sure how sophisticated they were when I was doing this a few years ago.
Actually, problem with observations of snow in both hemispheres is a very good example of that we're missing some critical data sets, observational data sets, to constrain models. And actually, my point was that with reference to sea ice thickness, sea ice thickness is in both hemispheres again, and just integrate all the fluxes and energy balance, and you either get ice melt or ice growth and accumulation or disappearance. For some time, at least some people in the community have been strongly arguing that we need to start collecting, in addition to core variables like temperature, salinity, humidity, we need to look and try to collect data on fluxes. Fluxes like radiative fluxes, turbulent fluxes, buoyancy fluxes, you name it. If you want to understand the changes in ice thickness and biases in particular modeling ice thickness, you need to be able to constrain that model with fluxes of energy that are contributing to the sea ice thickness.
I think kind of following that comment, and also just from the talks and seeing the importance of the conductive flux from the ocean to the sea ice surface, or maybe the snow surface, that seems like something that maybe models could output and help us understand better how it's changing and impacting the surface, whether it's snow or ice. Obviously, that's going to be impacted by the snow ice thickness. So I think that's something that could help out. And also, to David's talk, the ocean heat flux convergence, right? How it impacts sea ice thickness. Maybe obtaining a better idea of how the ocean heat flux convergence is on a more regional, smaller scale would be important to try and understand what's happening with the sea ice changes. But yeah, I think we have another one over here.
I just wanted to comment on the fluxes. Do you talk about surface fluxes or fluxes into the ice? All of them? Okay. Well, I think they're just some of the hardest things to measure at all. Right? There's an initiative to have a new satellite for air sea fluxes in the open ocean. I'm not sure what this thing does of the sea ice. I might remember that scalerometers don't measure winds over sea ice. So all winds we have are modeled winds. And then it's just imagine having a turbulent measurement on a ship in ice in cold conditions. It's like just very hard to do. Feel free to comment.
I wouldn't be the one to comment, but there's someone sitting right behind you, I think, could comment better on that.
I didn't mean to imply that it's easy, but my point is that we need that.
Yeah, and I guess one other thing is, like, as you're pointing out, like, many of these measurements are going to be made off of, right, some of them are going to be remote sensing, but like some of them are going to be made from things like Argo floats or buoys or field campaigns. I think there's a real need to figure out how to use those observations better in model comparisons and model development, because yeah, we're not going to have like a nice gridded product for some of these fluxes across, you know, the entire Arctic for decades, or Antarctic for decades.
So, you know, keep going down this. I don't know, Lettie, if you were in line, but I just wanted to keep going down this maybe a rabbit hole of surface fluxes. So is it, and I think the answer is both, right? Obviously, if we did more mosaics, we'd have more of these observations, right? And that would get at what David's mentioning, right? Let's do another one. Matt, what do you think? So, but going back to it's hard to measure these fluxes. So, you know, maybe food for thought for this afternoon's breakout or otherwise, are there like technological advances or things coming down the line that we can start, you know, some of the outputs from this workshop, there's going to be a report, like Nicole mentioned, it's going to be read by agency managers. Maybe there are some investments that agencies need to make in technology development that will enable us to make some of these observations that we need. So if there are thoughts around, you know, are there technological advances in particular that show a lot of promise? We need to know what those are so they can get into the report so we can start getting that there. Because, you know, if the answer is we have the technology we need, the answer is just do more mosaics, we can do that. But also maybe we can figure out better ways to get more accuracy or larger spatial coverage or things like that.
Let me hand it over to Heiss to introduce our next session.
All right, good morning, everyone. I hope you were able to enjoy the relatively warm weather. I don't think it's going to be quite as nice this evening, but hopefully you were able to get outside last night. So I'm Heiss from the University of Colorado, for those that haven't met yet. And together with Nicole, I'm chairing the session on the roles of atmospheric and oceanic transport in polar amplification. We've got 3 presentations as we did yesterday. First an invited presentation and then 2 additional ones. And that'll be followed by some open discussion, so please keep your comments and questions so that we can have a lively discussion afterward. So our first presenter is Brian Rose, who will be talking about the drivers of observed Antarctic sea ice trends and variability. Okay, he will not be talking about that.
So thank you to the organizers for having me here. Yeah, the title that's listed in the program is somebody else's title, and that's probably all my fault for not submitting a title in advance. But I want to say I was I was invited to give a kind of broad overview of atmospheric and oceanic heat transport and their role in all of the polar amplification processes that we're talking about in this workshop. So I set out to give a very comprehensive overview summarizing the state of knowledge on these topics, and then quickly realized that's completely intractable. So instead, a kind of a grab bag of my own thoughts and opinions and themes that I've seen in the literature over the years. There's going to be a bias in this talk. Do I have the right button? Let's see. A bias toward the Arctic. I'm going to talk mostly about Arctic amplification in this talk, based mostly on my own kind of knowledge and interests. So let me just start off by making a basic point here, probably familiar to a lot of people in the room, but one thing that's very special about polar regions is that if you think about the energy budget as a function of latitude, there are two places in the world where the column receives more energy from transports than from the sun, and that's highlighted in, trying to figure out this pointer, excuse me, highlighted in the yellow regions. It's the two poles. So the two poles are regions where the dominant energy balance is between convergence of heat transport and the radiative loss of that heat to space. And so this has been described as radiative advective equilibrium. The polar caps are places where the energy transport is really the dominant term in their energy budget. And that basic fact kind of can be held up as a good a reason as any to think that it might be important to think about heat transport in the climate of the polar regions and how that might change under a changing climate. So I was thinking about this talk, and I kind of wrote down my own opinion to take on bullets of things that we think we know pretty well at this point about polar amplification or Arctic amplification in particular. One, it's highly seasonal. Two, sea ice loss and seasonal heat storage in the ocean are a key part of that seasonality. Poleward moisture transport increases under global warming. Feedbacks in the Arctic, including but not limited to surface albedo feedback, tend to be more positive than in other regions, and that's a contributing factor to Arctic amplification. Lapse rate feedback in the Arctic is positive, but this is not actually a mechanism. It's kind of a consequence of all other mechanisms that set the lapse rate and how it changes under climate change. Feedbacks are not actually independent of each other. This point has been touched on already this morning. They're very coupled to changes in circulation and heat transport. And then finally, nature seems to be on the high end of our model-based Arctic amplification distribution, so there's some questions about what the models may be missing. I drew up that list, and then I looked at this nice review from Pat Taylor and co-authors, and I was happy to find more or less the same bullet points showing up in this summary slide, so I won't repeat them all. But this is a nice graphic because it illustrates this seasonality, polar day and polar night, the role of the ocean in transferring information essentially from positive feedbacks that operate in the sunlit season to provide warming in the winter season, and the role of the stable stratification, which manifests as that positive lapse rate feedback at giving surface amplified warming and so on. So I think it's a nice graphic that summarizes things we think we know pretty well. There's a bunch of stuff that's not in this graphic that I'll kind of say more words about. And yes, this is a Taylor Swift reference because I do have teenage daughters. Okay, I'm going to bias this talk toward older rather than newer papers, but because I'd like to take a historical view on science in general, and I think it's interesting to see how old some of these themes and ideas really are. This is Manabe and Weatherall, 1975. This is kind of the first, I think this is the first published example of something that you would describe as polar amplification in response to CO2 forcing in a GCM. It's a very primitive GCM, obviously. It looks like this. It's one hemisphere. It's very idealized, but some of the things that we still talk about today are evident in these simulations, like Here in this panel, this is the Arctic, or the pole in this one hemisphere model. This is bottom trapped Arctic amplified warming, if you like, in this simulation. There are some graphics of the energy transports in this simulation, and some things we still talk a lot about today are evident here, like offsetting changes in the dry and moist components of the poleward energy transport appear in this simulation, for example. If you've never gone back and read some of Manabe's old work on the early GCMs and their application to understanding climate change, I think you should. I think they're amazingly clear, and it's really interesting to see how some of the things we're still talking about today are laid out so clearly. So here, the tropospheric warming is most pronounced in the lower troposphere in high latitudes. This large warming is associated with the decrease in the area of snow or ice cover, which has a much larger albedo than the soil surface. The warming in high latitudes is confined within a relatively shallow layer next to the Earth's surface because the vertical mixing by turbulence is suppressed in the stable layer of the troposphere in polar regions. In short, the effects of suppression of vertical mixing together, those of snowmelt, are responsible for the large warming in the polar region. Okay, so that was kind of laid out nicely, although it's obviously very idealized, and we moved on from there. Seasonality, this is a beautiful paper. This is 1980, Manabe and Stouffer. This is the first example of a GCM with a seasonal cycle that is driven by a CO2 increase. So they did a 4-time CO2 experiment in a model with a seasonal cycle and with a much more realistic geography. So there's a southern hemisphere and a northern hemisphere and so on. So here's the surface temperature anomaly broken down by season in response to 4-time CO2, and you can see here the early winter peak in the Arctic amplification that's very evident here. You can see seasonality of the sea ice thickness in this model, in the control and in the 4-time CO2. And the text lays out beautifully their understanding of the source of this seasonality in the amplification. So the warming, owing to the quadrupling of CO2 concentration in high latitudes, is generally larger and varies markedly with season, particularly in the northern hemisphere. The warming is at a maximum in early winter and is small in summer. And I won't read all the text, but the gist of it is that they went in some detail into the energy budget diagnostics of their simulation and really understood that the source of this seasonal asymmetry really is the loss of sea ice in summer in the sunlit season, the gain in the thermal inertia by exposing a lot of seawater to sunlight, and the seasonal heat storage that results from that gets released in the cold season and in the presence of strong stratification. The ideas are laid out beautifully, and I think that's still kind of our leading order understanding of the main source of the seasonal asymmetry in Arctic amplification. Okay, so those are things that are fairly well known. What is not as well known or as well agreed upon? I mean, I could add more bullets to this list, but these are some things I'm going to touch on in the rest of the talk here. So physical mechanisms and causality. In the links between AHT and these slides is going to be atmospheric heat transport, if I don't spell that out, and feedbacks. What about the time dimension? What role might kind of high frequency variability in the atmosphere play in these causal links between heat transport, feedbacks, and amplification? And then also on this list, and missing from Pat's summary diagram, is basically almost everything related to the ocean, the heat transport by the ocean, and the interaction between the ocean and sea ice. And so let's take a look at that first. Okay, ocean heat transport and Arctic amplification. What do we know and don't know? So again, biasing toward old results. So this is Holland and Bitts 2003. This is from back when CMIP was just CMIP and there was no numbers in front of it. But here you see a bunch of Arctic amplification in models, right? This is the North Pole in these models, and this is the surface temperature increase in response to 2 times CO2. So coupled, is there something missing from this slide? I don't know, I think a graphic fell off the slide. Okay, so this was supposed to show that coupled models tend to predict an increase in ocean heat transport into the Arctic, or into the high latitudes associated with ice loss and Arctic amplification. So it's tempting to kind of ascribe some causality to that. It's not always true. Unfortunately, the slide missing something, but let's go to a more recent slide. This is work from Hansi Singh, just as an example that shows more of the seasonality. There's a very tight connection typically between the convergence of ocean heat transport and the ice edge, and how the ice edge changes under global warming. What you're looking at here are seasonal pictures from the two polar regions, and the colors here are convergence of ocean heat transport. Changes in convergence of ocean heat transport under a CO2 forced scenario, superimposed on changes in the sea ice concentration. And the point here is just that the hot spots of the colors and the contours kind of lie on top of each other. So regions where there's significant ice loss are also regions where you see a significant increase in convergence of ocean heat transport. And that's something you can find all over the place in literature. And it's true in both hemispheres. Here's a graph that actually does show some changes in ocean heat transport from pole to pole, broken down by season. And you do indeed find, for example, in the annual mean, this increase in ocean heat transport into the Arctic. This black curve is slightly above zero in that region. Okay. But the causality is not necessarily clear. There's a close relationship between changes in redistributions in where heat is converging in the ocean and loss of sea ice, but there's a kind of a two-way street of causal reasons. This is an example, another old paper. This is Cecilia Perralta-Ferriz, 2006, and what we're doing here is we're taking a GCM and comparing the response to CO2 forcing to the response you get just by darkening the sea ice. So we lose some sea ice for a reason that has nothing to do with greenhouse gases, just to see how the coupled climate responds just to a loss of sea ice. And so the loss of sea ice experiment is on this side, the 2 times CO2 response is here. So we see a lot of Arctic amplified warming and a lot of kind of remote impacts of that in response to darkening the sea ice. What I want to point out here on this side is that in dashed curve here, this is the ocean heat transport change just in response to losing ice. Okay, so this is getting at the kind of non-trivial causality between changes in the ocean circulation and loss of sea ice. In the dashed curve, the sea ice loss is kind of imposed on the model. The model responds by moving more heat into the regions that are exposed. So causality is hard. Other points that have been made, and this is not the only example of this, but this is the same paper by Hansi Singh, is that changes in ocean heat transport also induce changes in atmospheric feedback processes in a number of ways. So what was done in this paper is you go into a coupled model and you diagnose the changes in the ocean heat transport convergence. That's the panel I already showed you. And you can then impose that in a slab ocean version of the model where you get to dictate exactly what the ocean heat transport convergence is and see how the atmosphere and the rest of the model responds to that. And the point that was made in this paper is that these are cross sections of the atmosphere. These are anomalies in potential temperature in the atmosphere in the colors superimposed on contours of the climatological potential temperature surfaces. The point that was made here is that the change in ocean heat transport from the coupled model moves some heat from the mid-latitudes to the high latitudes, and the response you get in the atmosphere from that is a warming at the surface in the Arctic and a cooling in the mid-troposphere, which can be attributed to the mid-latitude cooling effect being sort of transported along these isentropic surfaces. So the ocean heat transport is kind of directly modifying the lapse rate of the Arctic, and that has radiative implications that would show up in a feedback analysis in that lapse rate feedback term, kind of a hidden effect of the ocean. There's other papers that have looked at how changes in ocean heat transport modify cloud feedbacks, and so there's a number of different ways we can kind of trace indirect impacts of ocean heat transport changes on some of the factors that affect Arctic amplification. Okay, so I talked to this guy about his thoughts on where we're at with this problem. I think, and I'm not trying to knock the heroes who develop and validate the ocean models. It's just a fundamentally harder problem just because of the vastly less well-observed state of the ocean relative to the atmosphere, as well as just the spatial scales of the relevant physics in the ocean being much smaller. And so because of this, I think it's likely that there are kind of more surprises lurking in the ocean than we might be currently aware of. And as we go to higher resolution and models that resolve more of the dynamics of the ocean, we might learn some new lessons that we weren't expecting. And some of these points have already been made this morning, which is great. I just wanted to highlight one such example. This is coming out of the IHESP project led by Ping Chang. This is an effort to do ensembles of very high resolution simulations with the CESM. High resolution here means a tenth of a degree in the ocean, a quarter of a degree in the atmosphere. This is a preprint that's online right now. I think it's a very interesting result. When you compare the high resolution version of the model to the low resolution version under a CO2 forced scenario, you find that suddenly resolving the circulation through the Bering Strait better leads to, surprisingly, a substantially stronger Arctic amplification. What's plotted here is sea surface temperature anomalies in the, excuse me, I don't have the right scale on here. Sea surface temperature in observations in the high resolution model, in the low resolution model, and in a kind of CMIP multi-model mean. The low resolution model is kind of equivalent to CMIP class models. So there's clearly some issues comparing CMIP to the observations. Clearly the high resolution model gets things a little bit better. The heat transport through the Bering Strait is what's plotted in this panel here. The high resolution model seems to capture reality quite a bit better, both in the kind of seasonality of this flux as well as in the time variability. A consequence of this seems to be that you get more Arctic amplification. And what's plotted here is in a kind of transient RCP 8.5 scenario. This is change in surface temperature across the Arctic. This is the black is the CMIP 5 multi-model mean, and the red is what we get from this high resolution model, which is substantially higher. And then some information about the spatial structure of those differences down here. So this final panel is the warming rate in the high resolution minus the low resolution version of the model. Okay, so it's just an example. We go to higher resolution, we better capture some relevant processes. And in some cases, that's going to mean we get a little bit closer to observations, not always. But it's not always anticipated what those results will be, and we're going to have to do more of this high resolution work to map some of that out. Okay, so let's jump into the atmosphere. Okay, so things models disagree and agree on. So I'm going back to PhD work from Yinting Huang here. Models tend to disagree about changes in total atmospheric heat transport, but agree that the moist part of that transport goes up. That's consistent with the idea that's been around a long time that moisture transport, which goes up robustly with warming, might be a driver of polar amplification. I put too many plots on this slide, but let's just say this is spaghettis of disagreement of heat transport across models. This is zooming into the higher northern latitudes and showing the breakdown between the total atmospheric transport, breaking it down into moist and dry. The moist part here is the solid curve. That's where the models tend to agree. The dry part goes in the other direction, and the models disagree more, and so on. And this paper from 2010 is a nice example of how we can capture this tendency of the moist transport to go up really elegantly with a very simple diffusive model that acts on gradients of moist static energy. And this has become a whole cottage industry unto itself, kind of using the moist EBM to reckon with interactions between feedbacks and transports. Okay, so this idea that moisture transport is a contributing factor to Arctic amplification has been around a long time. It's still being discussed. This is recent work. It's a paper by Hahn et al. Using this idea of using the local energy budget of the Arctic to do attribution. And so, the equation for this kind of study looks like this. I think it's been on the screen already at this workshop. But we can sort of, in this linear framework, we can attempt to break down partial warming contributions due to various processes, and we can think of the what did I want to say here? One original contribution of this particular study was to separate out the moist and dry components of the atmospheric heat transport into the Arctic. So this is the moist part here, and if you're familiar with seeing these plots, you kind of look at where it lies on this axis of tropical warming versus Arctic warming to reckon with its contribution to Arctic amplification. And indeed, the moisture transport shows up as a contributing factor, so that's nice. But there is a serious limitation to what we can do with this kind of energy budget diagnostic. And so I'm going back now to Ting Huang's work. Atmospheric heat transport changes in models tend to be anti-correlated with Arctic amplification, which suggests an opposite interpretation. Rather than transport being a driver of amplification, transport may be a response to amplification. So this is emphasized in this 2011 paper. The scatter plot here is looking at changes in atmospheric transport across 70 North, plotted against polar amplification in a number of GCMs. So there's this negative correlation here. Models that have a higher degree of polar amplification tend to have negative changes in the heat flux into the Arctic. And this is just some text copied from that paper. Model spread in atmospheric energy transport cannot explain model spread in polar amplification. Models with greater amplification must instead have stronger local feedbacks, because local feedbacks affect temperature gradients. Coupling between energy transports and Arctic feedbacks cannot be neglected when studying Arctic amplification. So this point is pretty widely acknowledged, but how to correctly reckon with the implications of this and really dig deeper into the causality is something we're still working on. Okay, so I'm going to throw out one path forward that comes from some of the work my group has done. Disentangling causality requires, among other things, thinking about the spatial and temporal structure of energy transports. So in the last part of my talk, I'm going to give some results from work that my PhD student Chris Cardinelli led, and I'll motivate this just by this figure here is, whoops, this figure is calculated from the CESM large ensemble, and we're looking at changes in components of the heat transport into the Arctic under a global warming scenario as captured by this large ensemble. And this model predicts, consistent with what I was saying in the previous slide, a decrease in the convergence of atmospheric heat transport in the Arctic, which is consistent with the relatively high Arctic amplification in this model. We lose 10 watts per meter squared, and we're looking at winter season only here as we go from the control climate to the warmer climate. And so that would suggest that these changes in atmospheric heat transport are a kind of a damping factor on Arctic amplification rather than a driver. And the punchline of this work is that's not true. It's because it's not the right way to look at the impact, the effects of the atmospheric heat transport on the warming. we tried to advance this kind of temporal framework for thinking about this idea. So what you're seeing here is a time series of one winter. The blue curve are anomalies in the convergence of heating into the Arctic through the atmosphere. So there's a lot of time structure. You see these big peaks associated with times when the atmosphere, through the outbreak of various storms, is dumping a lot of excess heat into the Arctic. These are all kind of with respect to what's the long-term seasonal climatology of the model. So anything above zero is an episode where there's excess heating arriving into the Arctic. So what happens in the time dimension in response to one of these surges of excess energy? Well, the first thing that has to happen is the air column has to become warmer and moister. And then what? That was interesting. Then somehow we've got to dispose of that excess energy. Was that a 1 minute? Okay, sorry, I wasn't seeing the. So let me accelerate. So we've got to deal with that excess energy somehow, and the idea is some of it can be lost upward to space and be lost, and some of it can be absorbed by the surface and help keep the surface warm through the winter. And what we tried to do was kind of come up with a way of quantifying that ratio of what's lost to what's gained. We called it efficiency. It's really just a fraction of how much excess energy you get in a certain event to how much goes into the surface, or the other way around. And so let's just say we figured out a way to do this. It requires high time frequency data because you've got to look at these individual synoptic scale events. The median value is something close to a half, so you get about half of the energy into the surface on average. But there's a big spread, and we can kind of look at how high, medium, and low efficiency events differ from each other. But the main point I want to emphasize here, and you're just going to have to go and read the paper to find out more about the details, I guess, is that the number of high versus low efficiency events is changing over time. This is taken from reanalysis data, and the idea here is that as we've gone over about 40 years of reanalysis, the relative occurrence through each winter of high efficiency events versus low has been going up. So each event on average is having a stronger impact on keeping the surface warm in the winter. And that's in reanalysis. It's also true and even more obvious in the simulation. So we can do the same analysis in the large ensemble, comparing historical to next century scenarios. And we find this very robust signal of an increase in high efficiency events in the frequency of their occurrence through the winter and a decrease in the frequency of occurrence of low efficiency events. So the upshot of that is that that 10 watts per meter squared of total integrated energy that we're losing as we go from control to warmer climate is kind of not the right way to look at how the changes in the atmospheric circulation are actually impacting the surface. It turns out we can quibble about the best way to do this, but we can try to separate out the impact on the surface energy budget of this increase in per event efficiency versus the decrease in the total amount of energy that actually arrives in the Arctic. And it's kind of a wash in this large ensemble. It turns out that we get a slightly positive answer here. So rather than minus 10 watts per meter squared, we get something positive. Okay, so since I'm out of time, let me put up my kind of overview summary slide. What are some paths forward? Maybe looking at changes in climatological energy budgets isn't going to help us do anything further in terms of really understanding some of the causality involved in amplification. So a priority does need to be working on causality, and a lot of these points have been raised this morning from the breakout groups, which I think is fantastic. So I'm just going to stop there. I personally think going to high frequencies in the atmosphere is a necessary part of this work because it's in the time dimension that causality becomes more clear. A consequence of that, I just want to highlight this one point, is that we can't do that kind of work without having access to that synoptic scale output from models, and that is kind of expensive, data intensive, but necessary in my opinion. I will stop there and thank you very much.
Thank you very much, Brian. That was great. Are there any very quick questions or comments in response to Brian's presentation? I think there was a lot there that fascinated me, particularly at the end that you had to rush through, but we can talk more about that later on. Any quick comments? Okay, yeah.
I know you're focusing on the Arctic, but thinking about the comparison with the Antarctic, the expectation is that the Northern Hemisphere jet stream weakens with climate change, and the Southern Hemisphere jet stream accelerates because of the temperature difference. I guess that's not really a question, it's more an interesting comparison between the two hemispheres and how it responds to atmospheric heat transport.
Well, I think the overarching question is, and I think Aaron Donohoe is going to talk about this later today, is, which way does that information travel? Is the heat transport responding to climate change, or is the climate change responding to heat transport? Is that even knowable? I don't think we have good answers to that, even despite thinking about this for so long. I'm trying to set up Aaron's talk.
Well, let's save the rest of the questions for the discussion. We'll be able to continue some of these themes there. Our next presenter is Pengfei Zhang from Pennsylvania State University, who will hopefully be talking about the impact of atmospheric rivers on sea ice.
Good morning, everyone. I'm Pengfei Zhang from Penn State University. I'm very happy to share our recent work with our Polar Climate Committee. Today, my topic is about the atmospheric rivers in the Arctic in past 4 decades. And this work is in collaboration with scientists from UCLA, Columbia University, and Pengfei. Today, my presentation is a part of the result of my recent work published in Nature Climate Change. Many of you may be very familiar with the atmospheric rivers. They are long, narrow, synoptic jet of water vapor transport. ARs account up to 90% polar world moisture transport in the mid-latitude. In recent years, it has been found that the ARs can penetrate into the deep polar regions. Several studies have found that when AR reaches the polar regions, they can exert strong melting effects on cryosphere, including the ice sheet melt in Greenland and the West Antarctic. Sorry. I don't know how to show the indicator. Oh, it's okay. Oh, it's fine. Okay. The figure on the left, shows that the ice sheet melt in Greenland, and the middle one shows that in the West Antarctic. On the right is a polar events induced by AR events in the Weddell Sea, and another study by Hedgie and Taylor. They report that the record low Arctic sea ice in the winter of 2016 to 17. Actually, the concept that moisture transport can lead to sea ice decline is not totally novel. This idea can trace back to 8 years ago by several studies. Since then, I have been troubled by a related question. So, to what extent the atmospheric heat or moisture transport can explain the ice decline. So expired by those AR studies, especially by the Xiyue and the Taiwan. In this study, we are trying to reply the question to what extent the AR activities can explain the rapid decline of Arctic sea ice. Okay, the first part, let's see. What's the AR melting effect on the Arctic sea ice? We firstly analyzed all of the AR cases in the November, December, January in the past 42 years. We only focus November, December, January because this period is the ice growing season. And the figure A here shows the sea ice concentration anomaly associated with those AR activities. It's obvious that the ARs can induce a significant sea ice negative anomaly over the marginal seas and slightly contributed to the ice growing in the central Arctic. If we show those negative values in the percentage of the climatological values at that point, at that grid, as shown by the figure on the right, we can see that there are up to 60% of the sea ice melt when AR approaching the ice cover, especially near the ice edge area. So that's because near the ice edge, the newly formed ice cover usually is thinner and fragile. Okay, so next is about the long-term trend in the ARs. The figure on the right shows the long-term trend in the AR frequency in ERA 5. We can see that there is a significant trend in the AR frequency around the North Barents Current Sea and the Central Arctic to its north, highlighted by the red sectors. And this significant trend is robust among three reanalysis data, as shown by the figure B on the right. This increasing trend in ARs coincide with the local sea ice area decline. So, okay, so let's try to reply the key question I just mentioned in the introduction. To what extent we can, to what extent the AR's melting effect can explain the rapid decline of the in the sea ice area. So here we employed a new variable, sea ice area growth. This variable is actually is a tendency of the sea ice area. It's based on the day-to-day change. And then we accumulate this day-to-day change during the early winter, as shown by the black line here. In the black line, there is a positive trend. So that means the sea ice seasonal growing rate is become faster. So that's because in current climate, the surface temperature in the Arctic is generally still below the freezing point. So that requires the open water freezing in the early winter. So more sea ice lose in summer, faster sea ice grows in the early winter. Okay, the black line can be further separated into two parts. One is the sea ice area growth during the AR days, as shown by the red line here. And another one is sea ice area growth during the no AR days, as shown by the blue line. The values in the red line is negative, that indicates the melting effect of ARs, and there is a significant trend in the red line. It suggests the enhancement of AR's melting effect. If we exclude the AR activities, as shown by the blue lines, it shows that the AR growth, the sea ice area growth rate could be even faster. So, so this figure suggests that the frequent AR activities prevent the sea ice from growing to the extent allowed by the freezing surface and air temperature. Okay, based on red line here, we can simply estimate the sea ice area change corresponding to 1% AR frequency change, and then we project this ratio to the observed AR frequency trend. We can get the AR frequency change induced sea ice area change. And finally, we compare the result to the total sea ice area decline in the past 4 decades. At last, we estimated that the enhancement of the AR melting effect accounts for at least 1/3 of the total sea ice area decline in November, December in past 4 decades. Okay, the last part is about drivers of the AR frequency change in the high latitude. We are wondering if the AR change is a result of anthropogenic forcing or internal variability. So to reach this end, we employed a series of model example simulations provided by CVCWG group at NCAR. All of those simulations is conducted by using the CEISM2. The first one is GOGA2, which is the AGCM run. It's forced by the historical SST and radiative forcing, as shown by the figure A. Despite the excessive AR increasing in the Pacific side, the AGCM run generally captured the observed AR changes and its pattern. Well, the result is quite different in the coupled run, as shown by the figure B. This result get from the large sample 2. Well, this coupled run only forced by the historical radiative forcing. It shows a uniform AR frequency increasing with a maximum in the inland area of Eurasian. So the spatial pattern is quite different to that in the AGCM run and observations. So it indicates that the anthropogenic forcing cannot explain the observed AR patterns, the pattern in the AR changes. So there are several previous studies suggest that the internal variability from the tropical Pacific, usually named as the interdecadal Pacific oscillation, IPO, contributed to the polar climate change. So we're wondering if this internal variability also contributed to the AR changes in the Arctic. So we checked the results in the third simulation, which is a pacemaker run. This is a coupled simulation, same as the large ZAML run, except the tropical Pacific SST anomaly has been enlarged to that in the observation, so that we can include the internal variability from the tropical Pacific. As shown by the figure C, we can see that compared to that in the large sample simulations, the spatial pattern of the AR trends has been much improved. In our climate community, usually we assume that the impact of anthropogenic forcing and internal variability could be largely additive. So with this assumption, we can calculate the difference between the pacemaker run and the large sample run and get the contribution of the tropical Pacific variabilities, as shown by the figure D on the bottom right, bottom left, sorry. Well, we can see that the tropical Pacific variability modulates the spatial pattern of the AR changes in the high latitude regions. Well, the bar chart, the figure E, is about the magnitude of the AR changes in the region of interest. The circles denote the value in among 3 renaissance data. The green bar shows that in the AGCM run, we can see that the AGCM run generally captures the the observed value. In contrast, neither anthropogenic warming nor tropical Pacific variability alone can explain the observed value. Instead, the observed AR changes in the region of interest might be the combined result of anthropogenic forcing and the tropical Pacific variability. Okay, here is the conclusion remarks. So we found in this study, we found that ARs indeed exert a pronounced melting effects on Arctic sea ice, and more frequent ARs has been observed. Well, the increasing in AR frequency account for at least 1/3 of sea ice area decline trend. This also indicates that the atmospheric processes contribution to the sea ice decline should be higher than this value. And the last one is about the tropical Pacific variability is essential for generating the observed pattern of AR changes in the highlighted. Thank you.
Thank you, Pengfei. I have a quick comment from Visa.
Comment and question. On the first bullet about the Arctic atmospheric rivers melting sea ice, have you looked at whatever results? Because I'm not clear when you were analyzing the ice growth tendencies. Those are model results, right?
The dashed line denotes the.
What is the data here?
The dashed line is the results in the model simulation. The solid line indicates is the observation based on the NSIDC satellite data. Satellite observation.
I'm confused whether you can get ice growth tendency from satellite, but my
and calculate the tendency by
that's
myself.
fine. My main point is that have you considered, in terms of analyzing your atmospheric river input or contribution to melting, that actually atmospheric rivers commonly are associated with the southerly winds,
yes,
which in marginal zone will push your ice to the north,
yes,
reducing the ice area. At the same time, the southerly winds will push or advect the more warm water from the Atlantic and the Pacific side, which might be relating the melt in the sea ice marginal zones to the ice-ocean interactions, not the melt from the surface.
Yes. Okay. For a specific grid, that's correct. However, here we calculate a very area average for a very large area, as shown by the figure here. So the ice drift, I mean, only the ice drifts maybe does not change the sea ice area in this large area. So we also, we have been commented by this question for many times. I just want to clarify that. So for a specific grid, of course, the strong wind can push the ice force to elsewhere. So, but for a very large area, so it does not change the total sea ice area.
All right, I think we need to move on to our last presentation, but we can continue this discussion both here in the session and beyond. So our last presenter this morning for the session 3 is Cecilia Perralta-Ferriz from UW-APL, who will be talking about increasing Pacific inflow into the Arctic through the Bering Strait. Please go ahead. Sorry, we can't hear you at the moment. You may be muted or microphone may not be working.
Sorry, I was muted. And yes, this we'll be talking about the drivers of the increasing Pacific inflow to the Arctic through the Bering Strait. I'll provide some insights from gravity and altimetry data and possible reasons why models fail to simulate the increasing flow. And this is work that I've done with my colleague, Rebecca Woodgate, but I would also like to acknowledge the important discussions with Ann Wynn and David Weiss, Jamie Morrison, Ron Kwok, and Jenny Bonin, who helped us in the competition with this work. And that now is published in the past 3 weeks or so. And so the Bering Strait is the only Arctic Pacific Oceanic gateway, and the flow through the strait represents about 1/3 of the total freshwater content in the Arctic. the ocean heat onsets seasonal western Arctic sea ice melt, and this water also provides a major source of nutrients to the Arctic. So changes in the flow through the strait will alter the ocean properties within the Chukchi Sea and eventually to the Arctic proper and potentially beyond. And we're zooming here into the Bering Strait, and we can see the location of 4 different moorings where we have in situ data as part of the Bering Strait program run by the University of Washington. And these observations have been happening since the 1990s and no longer have observations here in the Russian side, but we continue the observations from A2, A3, and A4 currently. We have the mooring A3 that we consider the climate site, which provides a good representation or a good average of what the whole properties across the Bering Strait, which is about 80 kilometers wide, have. And the time series from this mooring shows that as per the pictures on the right, they have a significant warming. The ocean has been frequently warmed. It's been freshening, and the flow has been also increasing. Now, the forcings of the flow have been generally well accepted to be 2 types. One is the local wind forcing, and the other is the far field forcing, often referred to as the pressure head forcing, or the sea surface height difference between the Arctic and the Pacific. Now, the local wind forcing is very well understood. It refers to a nearly northward wind, which sets up a geostrophic ocean flow current going northward. This flow is dominant during winter, but it does not show a long-term trend within this 30-year period. On the other hand, we can obtain a portion of the pressure head term by using this expression, in which we can decompose the total meridional northward flow from the observations into that component that is associated with the northward wind, the local wind, in this case using NCEP winds, and the residual will be the pH term. And we have made some breakthrough advances in a recent paper with Rebecca as well in 2017, in which we used ocean bottom pressure observations from the Gravity Recovery and Climate Experiment, or GRACE satellite. And we found that low ocean bottom pressure in the East Siberian Sea is what drives this pressure head term. And this pH term is dominant during the summer, and this term does show a long-term trend. The low East Siberian Sea bottom pressure is driven by westward winds along the Siberian shelves, and these winds set up a surface Ekman transport that pushes the water to the central Arctic away from the shelves, and then that lowers the ocean bottom pressure. Now, the figures on the plot on the left show the year-round trends, the time series of the V velocity, the total observed meridional velocity, and the middle panel shows the pH term, and the lower panel shows the wind term, the local wind term. And we are going to select a period, a smaller period from 2003 to 2014, because for these 11 years, we have a very clean set of GRACE ocean bottom pressure data. And we also have a product of dynamic ocean topography from a combination of the altimetry ENVISAT and Cryosat. And this is a product by Armitage in 2016. And we are going to use this period to identify what are the causes of these pH term changes, the trends. We also take the average of these 2 products, the ocean bottom pressure and the dot, and we show this on the panel to the right. And because we know it actually is the average of these 2 quantities, what is the direct driver of the flow, as given by this expression in the lower right, which is the delta T being the change in the transport, ocean transport, given by this average. But what I wanted to show here in these plots is that I was actually looking forward to see a trend in which the ocean bottom pressure goes down here in the East Siberian Sea, to be able to see, yes, the trend is explained in the same type of forcing as we have found before in 2017. But to my disappointment, it actually is not that easy. DOT does show a little bit of the low in here in the East Siberian Sea, but the average is not showing anything. And this is not a surprise if we look at the year-round trend also for this 2003 to 2014 period. The atmospheric forcing is not such that we would expect what we see from the lower here. There's some indication of the westward winds here, but it's not even significant. However, if we look at these trends in a seasonal fashion, and we separate them in stations like January, February, March, April, May, June, July, August, September, and October, November, December, and we compute the trends for this period, we find that as given by the big dots, they are going to be those that are actually significant. And we see that for the summer and the fall, there is significant trends in the V velocity and also in the pH term, but not in the wind term. And the plots on the right show the case for the summer, ocean bottom pressure on the top, dot in the middle, and the average of these two in the bottom. And we find that the sea level pressure has this actual, apologies, the main feature that we find for the summer is now a decline in ocean bottom pressure in this area, in the Siberian Sea, not only in the East Siberian Sea, but actually in the entire Siberian shelf. And dot also shows this, and the average as well shows the decline. And the sea level pressure shows a high trend, significant trend in the central Arctic, which leads to a westward winds along the periphery of the Arctic. So this is good news. This is exciting. This is what we knew about before. And this shows that the summer trends of the pH term is driven from the Arctic and given by the low ESS, driven by the winds. The fall story is different, and it actually shows an increase in ocean bottom pressure around the Bering Strait, north and south. Dot is similar, and dot, unfortunately, the product only goes down to 60 north, so we cannot see what happens a little below south from there. But we do see that the sea level pressure has an increasing significant trend high in right on top of the Bering Strait, and that will lead to anticyclonic winds that will converge ocean mass within the center. But of course, that would not be the trigger of the flow. What would be the trigger of the flow to go inward, northward, would be the westward winds associated with this high here. So this blue line here is showing westward winds that are significant in the trend. So now we know that the fall is actually, the trend of the pH term during the fall is actually driven from the Bering Sea. And one way to know how much of the pH term is actually driven from these type of forcings, to do that, we create response maps. And this panel is only showing for the summer case. On the top, I'm going to look at the relationship between the average product of dot and ocean bottom pressure and its correlation with the pH term in the Bering Strait. And we see that this correlation is also, again, not surprising, strongly in the Siberian shelves, much more in the East Siberian Sea, as we knew before. We create a regression coefficient map, and it's given by the contours behind. And on top of it, we add the dots that will be representing the significant trends of the averaged product. The multiplication of this trend with the regression coefficient will provide us with a response map to the right that will give us the magnitude of the pH term that is given at force from any area. And the observed pH term trend is about 0.6 centimeters per second per year. And this average over the East Siberian Sea from our theory and satellite observations, we find that the change is about 0.4. So we are able to explain this change within errors. Now, we know that the East Siberian Sea change happens because of the atmospheric forcing, and because we think of this as an Ekman transport, it has to be mostly due to the wind stress. Now, NCEP product of the wind stress does not take into account the presence of the sea ice or the contribution of the sea ice to the stress. So we call this, instead of wind stress, we call it surface stress. And this is given by this tau. And what we are plotting here is the correlation between the wind stress, zonal wind stress, and the pH term. And we find that it's strongly in this region. No surprising again, this is the summer. And we do the same exercise here. We create a regression coefficient map in which the contours are also the regression coefficient, and the dots are the trends of the surface stress. And the multiplication of these two provides us with a response map, and that shows that in all these regions, the change of the wind stress, the trend of the wind stress, is giving us a change in the pH term. And it can explain it, but again, the errors are pretty big, but within errors, we are able to explain at least part of it. And I'm going to repeat this of the surface stress on the bottom in the summer. It's the same as this one in the top here, but I'm going to add the fall in the bottom. So the fall, we remember it's a different story, but now it's the correlation coefficient on the left between the wind stress and surface stress, and the pH term. And the one in the middle is the regression coefficient, and on top of it are the dots that are the trends of the surface stress, and the multiplication will again give us the response map. And we highlight here this area that provides us with a measure of the pH term trend that would be of about 0.3 centimeters per second per year. It's significant, and it again is within the errors of the observed pH term. So it's a little disappointing that it's lower, but again, we are talking about very noisy products, and we believe that there is good reason to believe this is explaining most of this trend. Now, that was for the summer and that was for the fall, but if we go back to the year-round differences, remember that the ocean bottom pressure and the altimetry dot were also looking very different. And the only way to reconcile these differences are due to a change in the density field. So ocean bottom pressure is the sum of the sea surface height and atmospheric height. And in the Arctic Ocean, because of the cold temperatures, remember that the density portion will be dominated by the salinity. So using this expression here, we can create a salinity trend map just using satellite data, and we'll find that this trend is that these differences in bottom pressure and dot will lead to a strong salinization in the East Siberian Sea, and of the magnitude of 0.17 PSU per year. So we went to do some back of the envelope calculations, trying to identify the potential sources of the ESS salinization. And we consider sea ice formation, we consider precipitation minus evaporation, we consider upwelling of deep salty waters into the East Siberian Sea, and the most plausible reason that we found is the advection of Pacific water into the ESS. All the other terms are too small to explain the salinization, but for the advection of Pacific water into this region would only require about a 5% increase of the flow that already comes through the long strait here. And here I'm giving a plot of the geostrophic velocity trend given from the altimetry dot, and it shows also arrows pointing westward. So it is not hard to see that we could be able to see this Bering Strait water coming into the Siberian Sea, which is not usually well accepted, or we don't talk about that. There's no much talk about that. On the other side, there's also no in situ satellite data, salinity data over this period to confirm all of this, unfortunately. There's some indication of later satellite data of salinization, suggesting that indeed the East Siberian Sea has salinized, but it's still not for the period that we are interested. And one strong impact of the salinity changes into the models is how well they can represent the flow. The salinification in the East Siberian Sea is very sensitive to the GRACE data version used. And here I'm plotting different versions of GRACE. From the left, trends in ocean bottom pressure from GRACE. Left are the oldest versions, and to the right I'm going towards newer versions. And this one to the right is the one that I use for this project. But what this shows is that for each of these ocean bottom pressure products, we have a different salinization, and therefore we will have a different flow. So models assimilating or tuned to older GRACE data will be missing a vital forcing of the flow. And also Pacific water enters the ESS region. So accurate representation of the salinity in the Bering Strait waters is also vital to getting the trend in the flow correct. And just to summarize, we have seen that since the 1990s, the Bering Strait oceanic flow has been increasing, warming, and freshening. The increasing flow is due to increasing pH forcing. The satellite data shows that the drivers of the increasing flow are from the Arctic East Siberian Sea during the summer and from the Bering Sea during the fall. The difference in ocean bottom pressure and dot trend imply a salinization in the East Siberian Sea, likely due to the inflow of Pacific waters in the region. And finally, the salinization in the East Siberian Sea is sensitive to the Grace version, and models assimilating all the Grace data or getting the salinity of the straight flow wrong will be missing an important forcing of the flow. And I wrap up with that. Thank you so much.
Thank you very much, Cecilia. Are there any immediate reactions to this presentation? Any thoughts? All right, not seeing any. I think we'll transition to the broader discussion. We have about 20 minutes or so for discussion. And I wonder whether there are any comments about transports, ocean atmosphere transports. We would like to invite the speakers back up to the stage. So for those who are in the room, Brian and Pengfei, if you'd like to come up to the stage, that would be great.
And one thing I'd like to add quickly is we said this yesterday and we didn't really enforce it, but we'd love to hear from an early career scientist first, if possible, just to promote that.
Yeah, that would be great. And I will also encourage people to continue to introduce themselves when they make comments, just so that people learn to know each other a little bit. Yeah, go ahead. You can use the microphone right there.
Hi, everyone. I'm Lei. I'm from Purdue University. I'm really excited to hear all the exciting talks from all of you. I have a question for Brian. I think the efficiency you mentioned is very important, and my understanding that's from the observation. So my question is that does the model, climate model, able to reproduce that high efficiency, low efficiency at all, or how about the trend? Do we get a trend?
Is this on? It seems to only be on if I hold my finger on it. Okay, so I'll hold my finger. Thanks for the question. The short answer is, well, first of all, by observations, we should be clear, it's reanalysis, and there are definite, because the diagnostic that work is based on is almost entirely, or uses the surface energy budget in the reanalysis as a key piece of information. That is not observations, and I think we have to keep that in mind as a caveat. There are issues with the quality of the surface energy fluxes in reanalysis data, so that's a limitation. But to the extent you believe what's in the reanalysis, the short answer is yes. You can show that the model and the reanalysis behave similarly in that respect. Is that a satisfying answer?
Yeah, I am also curious about the specific process associated with those high efficiency events. So if you were to imagine, maybe atmospheric river or maybe blocking or whatever specific phenomena. So what are these?
Yeah, thanks. That's a great question. And I of course I could have given a whole other talk on that, and I had time for just a couple slides. There's some things we know and a lot we don't know about how to answer your question. Things that are in the papers that I'd be happy to point you toward include a lot of the analysis was really based on kind of zonal average view, and so there's some limitations there. But from compositing across large numbers of events, we get some idea of what makes a low and high efficiency event different. And one of the slides I jumped very quickly over and didn't mention at all is if you look at the structure in the vertical of the heat fluxes across a line like 70 degrees north, high efficiency events are characterized by a kind of bottom heavy profile. So more of the energy that's fluxing across that line is occurring at lower levels, and in some ways that's a signature of moisture. The moisture content of the flows into the Arctic is is down near the bottom of the profile. So all else being equal, if you have the same amount of energy in some anomalous heating event, the same amount of energy in an event that is moister versus drier, you're going to get that bottom heavier profile. So an atmospheric river would be a great example of that. That is a characteristic of high efficiency events. That's one thing we learned from those composites. Another thing we learned from the composites is that the pre-existing conditions across the Arctic seem to be very important. So when you look across the time dimension, what did the Arctic look like in anomaly from its usual seasonal cycle, let's say the week before the event occurred? The answer to that question is that if the events play out as high efficiency, the Arctic was usually in a state of relatively low sea ice and relatively weak stratification. Again, this is kind of a zonal average view. We have some maps in the papers that give a little more spatial information about where the low sea ice anomalies tend to be in the composite view. But beyond that, in terms of understanding the meteorology of it, we haven't got very far, and I think that's a great path forward.
Thank you.
Great, thank you. Wilbert, do you have a comment, or Brian? Yep. Go ahead, Kyle.
Thanks. Kyle Armour here, early mid-career scientist. I get to go before Wilbur. The question I have is, I guess, a quick comment on kind of heat transport. I think what we learned today and what we've learned over the last, say, 10 years is that not all heat transport is created equal. So if you have compensation between atmosphere and ocean that perfectly compensate, that doesn't mean no effect on the Arctic. Same between moist and dry. And so I was wondering if all the speakers could kind of comment on the ranking of kind of what makes heat transport important. So is the ocean heat transport per unit petawatt more important than atmospheric heat transport? Is moist more important than dry? Or do we need to dig into kind of the vertical structure of the heat transport? Can we start thinking about as a community what characteristic of heat transport and then maybe attach an efficacy to it or something like that as a way forward? So maybe this is following directly on what Brian was just talking about, but I was thinking about it before your comment, so I went for it anyway. Thanks.
I can do that first. Okay, thanks for the question. Actually, I just mentioned a little bit in the introduction, to what extent the atmospheric transport can explain the sea ice decline. From another ways, to what extent the ocean heat transport can explain the sea ice decline. I have traveled by this question for many years. So according to, I'm not familiar with the ocean part. According to a paper from Tokyo University, published about 1 year ago, they suggest that the ocean heat transport maybe contribute to 54%, I guess. Yeah, that's their conclusion. So from my work, the contribution from AR activities might be 1/3. And the atmospheric, the total contribution from the atmospheric processes should be larger than this value. But compared to the conclusion from the Tokyo University's conclusion, I think personally, I think maybe the ocean should play a more important role. Thank you.
Yeah, I mean, I think, Kyle, you're asking a great question. I think we need to talk more as a community about the right way to frame, how to measure the importance of heat transport. I think it's clear in many ways that just thinking about the energy budget of the whole column and comparing heat transports, so many petawatts against so many petawatts doesn't get to the relevant physics. We need to think about spatial structures, time structures, think about the processes by which that heating actually plays out. We've tried to do that, one little piece of that through this Arctic efficiency work with these that I alluded to. I would love to talk more about how to extend that framework in a more systematic way. So we can kind of agree on the right metrics I think we've got there.
Thanks. I just want to encourage Cecilia, if you have any thoughts along the way, to speak up
Yeah.
whenever you'd like.
Thank you. I wanted to add a little bit to Kyle's question or comment. Yeah, which would be more important? That's a little hard to answer, or how can we understand all of these aspects? But one thing that occurs to me is, as soon as, thinking on the side of the Bering Strait only, as soon as we have this warmer water entering the Arctic, and we can start seeing that the sea ice melt according to where this water is actually reaching, so giving some of the shape of this onset of the melt. As soon as that happens, then we expose, when there's no ice, and we expose this water to the heating of the ocean, because now we're talking about the summer. And so there's all this interconnection in the boundary layer that I think also becomes much more important at times and not at other times. And I don't know, Anne Wynne will know better, that I don't know, and Wiesel also will know better, how well this transition of open water or closed water and the heat exchange between the ocean and the atmosphere happens in the boundary layer, how well we can understand that and get that. And maybe that's not important all year round, but I think that, yes, that has to be a huge element of these interconnectivities within the layers. Whether one is more important than the other, I don't know, but this interconnection, I think it's key. That's what I have.
Yeah, no, any earlier career scientist than me, not online or so. This is a question that's not quite directly related to the presentations, but there was some mention of paleoclimate work. I'm quite familiar with the paleo work that's being done for the Atlantic overturning circulation, but I'm blissfully unaware of what's been going on in the Arctic. And I was wondering if anybody here in the audience can comment on what kind of proxies are being used and what kind of efforts are going on to understand the paleoclimate of the Arctic.
And if the answer to that is, Ruslan knows. I was going to say, if the answer to that is nobody knows, then it's a good thing to think about.
So I'm not the expert, I'm not paleo, but I'm familiar with quite actually extensive activities in the Arctic paleo community. There's an institute here in Boulder, and they have been co-leading, I guess, a lot of this type of research, in particular to the sediments in the Arctic Ocean relevant to, well, not relevant, but associated with a different type of circulation where you spread different sediments from rivers and continental shelf and the biological productivity in those regions. This is some proxy data that can be used for diagnosing this type of efforts. And I have a question.
Yeah, they're ahead of you, so you have to wait. So we have one hand up online. And then I don't know what's in response to what anymore, but let's go online and then I'll get to Kevin. Is your comment in response to this thread? Okay. All right, so let's go to the paleo comment and then we'll go online and then Rudra and David, and I think then we'll be close to the break.
Hi, early career scientist. My name is Kevin Rosmerick. I'm at the Instar Stable Isotope Lab, and we do high resolution measurements of water isotopes and ice cores, as well as some other Arctic atmosphere related things. High resolution, meaning sub-annual ice core measurements of isotopes, is a relatively new thing. And we're trying to tease out how that affects on sea ice. And the biggest connection and the biggest tell connection that we've been able to find with these high resolution stuff is it mostly has to do with the ice sheet configuration. And that's a non-unique solution, and we quite haven't figured it out yet. So if anyone knows it or has some familiarity with how that works with sea ice, I'd be happy to talk with you about it. I think it's a super interesting topic, but the paleo connection has not really been quite figured out yet in this subject.
Thanks, Kevin. And we have one other quick paleo comment.
Yes, go ahead, Melissa Gervais. You can unmute.
Actually, it sounds like in the room, maybe there's another paleo comment. Should I wait?
Yeah, one very quick one, Melissa, and then we'll get to you.
Hello, everyone. This is Jiang Zhu from the Paleoclimate Group at NCAR. I want to add a quick comment about Arctic work. One work we know is that for the past warm climate, the ocean straits matter a lot. For example, if you open some straits, we have ocean heat transport, and in the model you see a greater Arctic warming, and that tend to agree better with proxy SST records. So this, I think, stress the important role of ocean heat transport.
Thank you. All right, let's go to online now.
Yeah, so I had a question or a comment or discussion point. We've been talking a lot about warm transport into the Arctic, but do we ever think about the opposite side of changes in transport of cold out of the Arctic as the flip side? And, you know, do we maybe think that they're not equal? Because when you think about transport into the Arctic, you're talking about warm, moist, bottom heavy, as Brian was just talking about, versus the opposite for cold out. And one of the reasons I'm thinking about this, my poster, which I didn't get to present because I didn't get to come in person in the end due to weather, was looking at changes in, from a synoptic perspective, decrease in export out of the Arctic in certain patterns that normally would be associated with a lot of cold air advection, but due to both thermodynamic and dynamic impacts, we see a decrease in that with sea ice loss. So I was just curious, this is actually really, I think, for Brian, do you think there's a lot of value in looking at, from this kind of more holistic way for the budget for the Arctic, kind of these cold events?
I mean, yes. I'm not sure I have a very intelligent response to your question / comment other than to say, you know, we have to conserve mass, so if there's air going in and we're interested in the properties of the air going in, there's got to be also air going out, and it stands to reason that there's useful information about all of these causal questions in looking at the properties of the fluxes out of the Arctic as well. You know, I'll probably stop there because I'm not going to say anything that's going to change your mind. But sure, yes, let's look at in and out. I'm with you.
Thanks, Brian. Rudra, do you have a question or comment?
Hello, Rudra Thacker, from graduate student at University of Wisconsin-Madison. Great talk, everyone. My question is to all the panelists, so all the speakers, that there was very interesting talks about how the heat transport is changing. I wonder if you have any comments and insights about what mechanism is changing that. So is it the Hadley cell circulation changing, or the transient eddies changing, or whether breaking it down to extremes like atmospheric rivers makes sense for further investigation or not? Thank you.
Well, I would say in the slides that I was showing, you know, there were many changes in many many things were going on all at once in the things that I covered. So what's causing heat transport to change? The answer to that depends a lot on where and when you look. You know, the one thing that I tried to emphasize in my talk is that we get this fairly robust signal from climate models that moisture transports, polar moisture transports, always go up with warming. There's a very nice reason to expect that, which is just that the gradients in saturation specific humidity go up as you warm the climate, and basically every model sort of agrees on that basic physics and so gets the same result. Beyond that, you tend to get a lot of disagreements, and there's a lot of interesting questions about the kind of cause and effect between changes in the changes in gradients as climate changes versus changes in energy transport and what's causing what. You know, if you go across papers and try to see, well, who's arguing which aspect of the transport change is most important, you tend to find that the answer depends on details of where you look. You know, are Hadley cells important? Sure, if you're looking at the Hadley cells. You know, are changes in mid-latitude baroclinic eddy flux is important? Yes, if you're looking there. You know, so I think it's important to bear in mind that you know, the atmosphere communicates information across all latitudes it's you know, everything has to change simultaneously to maintain some balances, and it's important to keep that holistic perspective in mind. Beyond that, I'm not sure I have a very good answer to your question.
Yeah, I'd like to add one more point about the eddy feedback in the circulation feedback. So in a changing climate, since the basic state of the jet, like jet, is changed, and the eddy feedback also changed. So in the mid-latitude or the hard latitude you just mentioned, so in a warming climate, the eddy feedback also contributed to the total response. We have ever simply estimated the contribution from the contributions of eddy feedback is about from 1/3 to almost half of the jet response, the circulation response, like that.
Thanks. We have 2 more questions, and then it's going to be time for the break. So I'd like to make sure that we have a break before the 10:50 session starts. So David and Anne, and then we will move on. So David, go ahead.
Yeah, thanks for a lot of great talks. And one thing that struck me about all of these talks is how important the reanalysis data is for these analyses. I was wondering if you or others in the room could comment on kind of the state of the reanalysis data for doing this, and what are the priorities for improvements, what's the feasibility of making those improvements. I know we have limited time, so maybe just highest priority perhaps.
I'm not an expert on this part of the question. I mean, it's absolutely true that reanalysis data is invaluable for trying to characterize what's been going on out there. From my perspective, top priorities are a better understanding the quality and limitations of the surface energy budget terms in reanalysis, especially in the polar regions and where ice is involved. That's where we have some of the biggest questions, I think, about quality of the data, and where, you know, the work I was talking about, where that can be a serious limitation. So I don't know how to make it better, but that's where I would want to invest effort.
According to my own experience, yes, indeed, there are large discrepancies among the reanalysis data. Yeah, I didn't mention that details in my figure, although the trend is consistent, but they do have some difference in some individual years. That's because we do not have enough observations in the polar regions. That's very common. So, but currently we have no choice. The simple way is that we use all of the reanalysis data to test the robustness of the results. Yeah.
Thank you. One last comment, Anne?
I'm just making a quick comment on it. I think just in particular with reanalysis, obviously more data in is better. But if we can prove the physics, that would be helpful. But I think like the simplest thing, my understanding of it, if we could get more radiosondes in places where we don't have them in the Central Arctic, like obviously nobody lives there, but that's like the kind of the simple, you know, temperature, humidity, wind kind of profiles that are assimilated into reanalysis. Like we could figure out a way to get those. That would make, you know, would be really, really helpful.
Yeah, actually, I wanted to, sorry, this is Ann Wynn. I'm doing data simulation in the Arctic Ocean and sea ice modeling. But I want to actually address very quick the question on reanalysis. There was a CLIVAR session just, I think, a year ago, specifically on the state of knowledge of reanalysis, particularly in the Arctic and the Southern Ocean. And actually, that is where you have the largest errors, because there's almost zero observation or very, very limited observation. So you have to think of them as essentially just forward models. And then when there are data, then you have to worry about nudging effects. That actually, if you are to do budget analysis, then you have to be quite careful about, because, you know, nudging doesn't necessarily close budget at all. And so that's a very important question. I wanted to ask very quick to Cecilia. Thanks a lot for the really interesting talk. the data, as we know, is very important in the high latitudes because we have emphasized so much about lack of observation. But actually what you're highlighting is quite of concerning, I would wonder, because different the same data product, different releases seem to actually yield quite large differences. And I wonder whether you have heard from the developers or the people who develop the data products for GRACE, what that might be and what is the consequence of high latitude versus low latitude differences in that. And another quick question on the whether you have also used the sea surface salinity data in any way to constrain some of that. And I know you didn't actually give a talk on it, but can you say some note very quick about the relation of the heat transport across the Bering Strait? Because I know your talk is about the volume transport, but yep, thanks.
Thanks, Anne. Yeah, so the GRACE makers, they are aware of this, and I was back and forth with them discussing about this, and they keep improving their products, but they have made changes that go from improving their post-glacial isostatic rebound model. And that was a huge change that led from the version 5 to version 6. And on top of that, there's been other model adjustments and decisions in the post-processing data that they have been doing. And I think they are moving to the right direction, but again, it's still not perfect, but I think they are aware of these consequences and how, yeah, we really need the best observations that they can get them. But it still depends on other various models, not just purely the satellite common data. And yeah, I did not touch, in the second question, I did not touch about the actual temperature and heat coming into. It was mostly about the salinity, because that's what I believe is what's the major problem in getting the flow, or what we think based on what we found, because if the salinity changes in the Siberian Sea, whether it comes from the model or where it comes from the observations, that's going to be counteracting the actual flow into the strait, because then we will no longer have this pH forcing that we have there. But that said, Brian had mentioned about the, he had an image about this. I guess I should contact him, in which I think there will be a really, really good way to tie up the heat transport and the salinity transport that I was talking about in how we can respond and how that can potentially lead to amplification. But I have to wrap my head around that, but I have that slide and I'm going to contact Brian about it, and then I will get back to you.
Well, just to be clear, that was not my work, but I'd be happy to point you to the right people to talk to about it.
Okay. Thanks.
All right, thank you. Thanks, everybody. I'm getting flashed the orange sign from the back of the room. I will say quickly, in the spirit of this workshop, so one, thank you for the great discussion, and two, we heard very little about the Southern Hemisphere in this session, and I think either that means that large-scale transport doesn't matter in the Southern Hemisphere, or we were just biased in our speakers, but something to keep in mind for the afternoon breakouts is transports in their connection to Antarctica. So I'm going to pass it back to Alyssa, and we can go to break.
Okay, good morning, everyone, again. Welcome back to the session on the drivers on observed Antarctic sea ice variability. I am Marilyn Raphael, and along with Kyle Armour, who you've seen already over there, we're chairing this session. And we'll begin right away with our invited speaker, Dr. Will Hobbs, who will speak on drivers and constraints on Antarctic sea ice variability.
Thanks, Marilyn. Thanks to the committee for inviting me. I feel a certain amount of pressure to make sure you get your money's worth. So this is a slight change in the title, Drivers and Constraints. And the reason why is because I think in terms of polar amplification in the Southern Ocean, the constraints are perhaps the more useful and interesting conversation. The drivers are relatively easy. Short-term sea ice variability is absolutely dominated by the atmosphere, and the Southern Ocean, polar Southern Ocean, is one of the most synoptically variable places on the planet. Easy, talk's done. Now let's get on with the constraints. So I'm sure many of you have seen some version of this plot over the last year. So it's the Antarctic sea ice area monthly anomalies. And this is actually normalized, so the units are, hang on, let me see. there we go. The units are standard deviations. But the key point is, as I'm sure everybody's aware, there was a long-term increasing positive trend up to around 2014, a very sudden drop in 2016, and then these sustained low, and including extreme events in recent years. But on that record, as well as the mean state, there are some more subtle statistical indicators that are really important and really important for polar amplification. So as well as 2016, Ari and Purik recently published a paper using a change point detection analysis and showed that as well as 2016, 2006 is also a change point in this record. Not because of a change in the mean state, but for some other things. If we have a look at the earlier period, and you can see the fluctuations all kind of more or less stay within that 2 standard deviation range. The 2 standard deviation range is these dashed lines here, excuse me. Whereas if you look in the later period, we get much bigger peaks and troughs. Not just negatives, but positives as well. The variability is increased, and we can formally show that the standard deviation has more than doubled over that time period. And that is a fairly significant change. The other thing you can see is in this early part of the record, those fluctuations kind of revert back to normality pretty quickly. You know, they stick around for a few months at most. Whereas in the latter part of the period, you can see these long, persistent changes. And again, we can formally show that change in persistence. I'm showing here the 6 months lagged autocorrelation. For Antarctic sea ice, which has very little multi-year ice, 6 months is quite a long time. But you can see in the earlier part of the period, there is no autocorrelation. In the latter part of the period, it's 0.64. That's a really high autocorrelation in this business. And so what we're seeing is more variability and more persistence. Now, those are both indicators of a change in how this works as a feedback system, which is very interesting from the point of view of polar amplification. But they're also known in dynamical systems theory as early warning indicators of abrupt critical transition. Now, we can argue how robust those early warning indicators are, but we can also think about what happened in the last year, where, as many of you will know, Antarctic sea ice was at a very, very extreme low in the winter. Depending on what climatology you use, it was a 7 standard deviation anomaly, far outside any previous record. And as I'll argue later, the seasonality of that event over winter is what's really worrying to us who work in the Southern Ocean. So I'm going to focus on those metrics of change, the change in variability, the change in persistence, and what's driving or not driving them. Now, if we think about drivers, as I already said in my introduction, the first pass indicator is always to look at the atmosphere for Antarctic sea ice. If you look at any paper on Antarctic sea ice over the last 2 decades, 90% of them are going to look something like this, including my own, hands on the head. It's going to be some map of winds and some map of sea ice response. And it could be, I can't even remember what paper this was from or what it's about. I think it's a trend, I can't remember. It's one of my papers, so I should know. But basically, it doesn't matter whether you look at trends, anomalies, or a correlation with the southern annular mode or something. You will see a very, very strong response in Antarctic sea ice to changes in the winds. And we've known this, and that's really dominated, it's dominated the sea ice, but it's also dominated the sea ice research. And so our first pass indicator is then, if we're seeing an increase in variability, we might see an increase in variability in the atmosphere. But we don't see that, so I apologize for the slightly busy slide, but for the start, just focus on the left-hand side, which is the observational side of things. So what we're looking at on this figure here on the left here are running 10-year standard deviations of the sea ice, or particularly the summer sea ice in the black line, and we can see that ramp up of variability that I've already talked about. And then the colored lines are various atmospheric indices or indices of atmospheric that we know are very strongly correlated with historic sea ice area, sea ice concentration variability. And we just don't see that same ramp up in variance. So whatever we're seeing is not a direct linear response to atmospheric forcing. Even if it's forced by the atmosphere, there's something else that's changing the response. If we look on the right-hand side, the right-hand side, this is evidence from a model. This is sea ice area, the Antarctic sea ice area, in the black line from the observations or from NSIDC, and in the colored lines, it's from an ocean sea ice model. It's Access OM2, our Australian model, forced by different reanalyses products. And the key point here is that in the early part of the record, the sea ice is really slavish to whatever reanalysis we force it with, and we can tell ourselves, our model's great because it really matches the obs awesomely well. But when we look at this latter part of the period, particularly after 2016, the fluctuations are still there, the interannual fluctuations are still there, but it gets nowhere near the persistent loss. And in fact, it's not quite on here yet because I don't have the up-to-date data, but it didn't get last winter at all. And I notice, interestingly, this is just from our model, but Lettie Roach had a paper published just a few weeks ago where they were nudging the winds and had a similar thing where the slavishness to the atmosphere kind of seems to have broken down in the last few years. So the atmosphere, although incredibly important for interannual variability, is not telling us the whole story about what's happened recently. And so what I'm going to do for the rest of the talk is talk about those constraints, and because I'm an oceanographer, there is going to be an ocean bias, because I think that's, if it's not the atmosphere, it's probably the ocean. And I'm going to go through the life cycle of a bit of sea ice. So if we're going to freeze the ocean and melt it. But before we freeze it, the first thing we need to do is we're going to cool the ocean. For sea ice to exist in thermal equilibrium, we have to be able to maintain the surface temperature at freezing, about -1.81 in the Southern Ocean. If we can't maintain a freezing temperature at the surface, the sea ice is going to melt within days. Now that sounds really trivial, but actually there's some really, really useful insights here. Okay, I apologize for those of you who aren't an oceanographer, but hey, this is a schematic of a typical density profile in the ocean, and particularly the Southern Ocean. The surface is at the top. It gets more dense as you go deeper, just like stability in the atmosphere. You have a mixed layer and then some kind of transition called the picnic line, or the bottom of the mixed layer, into some deeper water. Now, let's say I take a parcel of water at the surface and I get it down to freezing temperature. Now, most of the planet's ocean, this density profile is dominated by the temperature. And freezing is obviously the coldest temperature that water can be at. So if I take that parcel of surface water down to freezing, it's going to get heavy and it's going to sink, and the surface is going to be replaced by some other parcel of water that will have to freeze. The implication is, because this is the densest water it'll be, I'm going to have to cool the entire water column before I get any sea ice. Now, on the continental shelf, where it's sort of 400, 600 meters deep, that's perhaps feasible. But in the open Southern Ocean, where it's 4,500 meters deep, that's clearly not possible. And the key point, if you're not a polar oceanographer, is this. A key feature of polar oceans on both hemispheres is that the density profile is dominated not by temperature, but by salinity. And you don't get sea ice unless you have this. So now what's going to happen is I take that parcel of surface water and it does down to freezing and it does get denser, but it's not sinking all the way to the bottom of the ocean. It's sinking to some depth that's prescribed by what the salinity profile looks like. By the way, those terms, minty and spicy, I didn't make them up. They are actually oceanographic terms. But it means that the Southern Ocean, or the polar oceans generally, can maintain a temperature inversion with cold, fresh water at the surface, cold enough to maintain sea ice, and warmer but saltier water at depth. And I can actually use the salinity profile to actually estimate how deep this surface parcel will sink. And I'm not very imaginative, so I called it the critical depth, but I'm sure there's a better term. But what the implication is, this is the layer of water that I now need to cool down to the freezing temperature, not the whole water column. That's actually kind of interesting and useful because I can map it out as long as I've got TNS profiles. This is from a model, but you could do the same with Argo data or anything as long as you've got enough profiles. So what we're looking at is that critical depth mapped out from a model. And you can see a very, very sudden transition where that critical depth gets very, very deep and it saturates my color bar, but it actually goes really, really deep. And that's that transition from what we call a beta regime, where salinity is dominating that density profile, to a more sort of regular temperature dominated regime. Now the magenta line here is actually the maximum ice edge extent, and the cyan line is in the model the most northern limit of any freezing in the model, even just like a day or two in the model. The key point is you can see that really clear relationship between the edge of that salinity-dominated regime and the ice edge. And this is also true in observations. Okay, so I'm an oceanographer. I'm nerdy enough to be really interested in this. But what does this mean for polar amplification? So what we're looking at here is the climatology from observations of Antarctic sea ice. The black line is the mean, and the magenta line is the standard deviation. The key point is that in winter, there we go, in winter, even though there's about 8 times as much sea ice, the standard deviation, the variance, is less than in winter. Now, in the Arctic, you know that when the ice goes out far enough, it hits the land and it can't get any bigger. The implication is the Southern Ocean has a similar limit. It's not land, but hey, guess what? It's that beta regime. It's that salinity dominance. The ice always gets out to that point. It can't really go very much further without a lot of work, and that is a limit. And that's why historically we see trends in sea ice in the warmer months, but not in winter. Now, we might at a first pass just assume that it's because when you go too far north, it just gets too warm. And that's not strictly true. This is the annual mean cooling rate. Blue is cooling, red is warming. From a reanalysis product, I think it's error 5, but you could use any reanalysis. It's going to show more or less the same thing. And you can see, even though I'm not just looking at the winter here, I'm looking at the annual mean, there is plenty of cooling, particularly in the Pacific. The ice could be way further north if it was just down to the atmosphere, but it's not. It's this limit from the ocean that provides a hard limit. And that means, from the polar amplification point of view, it means that sea ice area is constrained, and it can't change too much unless you significantly change the ocean hydrography, or you change the winter cooling rate so much that it never gets quite out to that limit. I'm hoping we don't get that far. But the key point is that that salinity dominance is a prerequisite for sea ice. And that's a limit in the Southern Ocean that provides a geophysical barrier, if you like. And of course, that has real implications when we're thinking about 2023, because that huge anomaly last year was in winter. Does that mean that the cooling rate wasn't enough to get out to the edge? Or does that mean that the Southern Ocean has changed? I don't yet know. We're working on it. But it is something, this is why Southern Ocean people are really, really concerned about the timing of last year's event. All right, we're about halfway through the talk, and I haven't even done any sea ice yet. So it's time to freeze the ocean. So we've got our water down to freezing temperature. It's time to freeze some ice. And what's the biggest constraint on freezing sea ice? It's sea ice. Because we have to cool the ocean, mostly by long-wave radiation, a little bit by sensible heat. But of course, sea ice is a very effective insulator. It's an even more effective insulator when you've even got a thin covering of snow on it, which in the Southern Ocean you almost always have. But if I can move that sea ice flow out of the way, if I can just jog it aside somewhat, I've got some open ocean, and now it can freeze nice and easily. And that's why the dynamics, and that's why the wind is really important, is because you've got this really strong relationship between the thermodynamics and the dynamics. So what we're looking at is sea ice volume tendencies. It's again from our model. You can do sea ice area tendencies from OBS, but not volume. And red basically means you're losing ice, blue means you're gaining ice, and this is for the early freeze season, April to June. And so the net tendency for the sea ice is to move in the Southern Ocean is to move away from the coast and into this outer pack. So you're pushing ice away from the coast into the outer pack. And by moving it away from the coast, obviously you've got some divergence, you've got some open ocean, and then you can really intensify the freeze rate around the coast. Now the ultimate expression of that is a polynya, very localized. It's very important for deep ocean water formation. I'm not going to talk about that today, but that's a really extreme metric. But this relationship between the dynamics and the thermodynamics does not just happen in polynyas. It's overall really important. Now, a lot of papers in the past have tried to differentiate, is the dynamics or thermodynamics more important for trends? And I've done those papers myself. My thinking now is that they're so intimately linked, it's kind of a wrong-headed way to do it. They're almost the same thing. Well, not the same thing, but they're so intimately related. Now, that's not just true of the mean state, it's also true of the anomalies. Now, I apologize for how busy this figure is, but if we just focus on the middle panels, which is the winter, what this is the correlation between the dynamic and the thermodynamic tendencies, the same tendencies that I was showing in the previous plot, for sea ice area and for volume. You do your best to avoid spelling mistakes, but never mind. The key point is you can see that really strong negative correlation. You move ice out of the way, that's a negative dynamic term, you get refreezing. And you see that both in the volume and the area. But there's some really interesting stuff here. First of all, for the sea ice area, it's really dominant. It's a really high correlation. It's like 0.9 everywhere within the ice pack. Now remember, when we're looking at sea ice area in the sea ice in the Southern Ocean, we're almost always looking at sea ice concentration because that's what we've got OBS for. But sea ice volume, which we generally don't think about, has a much weaker relationship within the sea ice pack. There's other stuff going on, there's mechanical rafting and ridging, less so in the Southern Ocean actually than in the Arctic, but so there's some other constraint. So the key points are, there is a really important relationship between the dynamics and the thermodynamics, but it's probably not as strong for volume as it is for area. And so in our thinking, based on observations, we might have been a little biased. But what's this other constraint on volume within the sea ice pack? Well, I'm an oceanographer, so you can guess where I'm probably going with this. But it's actually, I'm going to argue, the ocean. So this schematic is basically something that I've already talked about. So we've got this beta regime with cold, fresh water at the surface that can maintain sea ice, and warm, salty water at depth. And I guess somewhere along the way, the text boxes have messed up, but don't worry about it. And then they're separated by a picnic line. Now, what I'm going to talk about now is really sort of work following on from Doug Martinson, but it's kind of, I think it's really useful for what we're thinking about right now. So when we freeze that sea ice, we're going to get some brine rejection. About 2/3 of the salt in the surface ocean is going to be purged. That surface layer is going to become very salty, and of course then it's going to become very dense, and it's going to sink. And initially it'll probably sink to the bottom of this mixed layer down here, but eventually the mixed layer is going to become salty enough that brine rejected water is just going to plow through the base of the mixed layer and entrain this deep water into the surface. And it's warm, so it's a virtual heat flux. It's going to melt some of the ice that we already formed. And so you can have this ratio. For every kilogram of sea ice that you form, you will melt some fraction, 200 grams or something. That ratio places a limit on how much sea ice volume you can grow over the winter. And just to show that I didn't just make that up, models show the same thing. These are freeze and melt tendencies integrated over the Southern Ocean, again from Access OM2, but pretty much any size model will do the same thing. The blue line is the freeze rate, and it's nice and geometrically symmetric, and it basically follows the solar cycle. But if we look at the net term in the black, it's quite asymmetric. And the reason why it's asymmetric is because of this melt term, and particularly the basal melt, which is the orange line, which is largely covered by the REL. So in the early part of the season, we ramp up the freezing rate, but we've also got this basal melt that's caused by that entrainment of deep water. And as we ramp up the freezing rate, that entrainment rate goes up. We're making more sea ice, there's more entrainment, more melt. The ratio don't really change very much. But even after we hit the peak freezing rate, this basal melt stays the same or even increases, because we've made the mixed layer so salty now that for every kilogram of ice, we're now basically just entraining circumpolar deep water. And eventually you get to a point where this ratio is about 1:1. And so you've got this limit on sea ice. Now, again, I'm nerdy, I think this is really cool, but it's also really useful to understand polar amplification, because it means that the Antarctic system is a negative feedback system. You can have a year with really intense early cooling, and it's just going to hit that limit earlier, but it's still going to hit that limit. You can have a year with really weak cooling, and it'll probably eventually get close to that limit. So you've got a negative feedback system where the variability is controlled, both in the area by the presence of that salinity regime and by the volume by how strong that salinity regime is. That entrainment is also a limit on the persistence, on the memory of the sea ice, because not only is that deep water warm, it's also really old. Circumpolar deep water, some of it hasn't seen the surface for 1,000 years. The memory of the sea ice, the thermal memory, what happened in the last few months, whether it was receiving sunlight, whether there was a bunch of sea ice, whether there was a bunch of sea ice formation, the memory is all in the thermal state of this mixed layer. But by rinsing out that mixed layer and replacing it with really, really old water, we've actually wiped out the memory of the system. And that's why initially, when I showed that plot of the autocorrelation, initially it's almost 0. So this is work from a, oh, excuse me, no, hang on. Oh, okay, I guess I've lost a slide, but never mind. But basically, oh, excuse me, basically what it means is that there is a winter predictability barrier. The system always resets in midwinter. And so when we're seeing that change in correlation, 6-month correlation, it implies a change in this winter predictability barrier, and it implies a change in this ratio between freeze and melt. Or we're just not making enough sea ice to ever hit that limit, kind of like we were with the area. So let's have a look at what is driving that and whether we see changes in the ocean. Basically, this is salinity anomalies from the Argo data, so this is observations. Now the under ice Argo program doesn't have a whole lot near the coast yet, so we're looking at the kind of northern half of the ice pack, so 55 to 65. And what we can see on here is that if we look at the surface, we see the surface getting fresher. That implies a bigger salinity difference between the surface and the deep ocean, so a more stratified regime. That implies less of that negative feedback, right? Because we're entraining less heat for each kilogram of sea ice that we're mating. And that's kind of really consistent up to 2014. It's consistent with an increase in persistence because we're shutting down that wipeout of the memory, and an increase in sea ice, which is what we saw up to under 2014. After 2016, things start getting a little more complicated. The mixed layer becomes more salty, and we kind of expect that because if you have less sea ice, your mixed layer will become more salty. It means that your relationship between the surface and the deep ocean is now stronger because it's more weakly stratified, and so that's consistent with a loss of sea ice. Again, that's exactly what we see. But it also implies a massive loss of persistence, and that is not what we see. So this is as far as I'm going to get about this part, but the key point is that these relationships, these limits on variability and persistence are really key to understanding what's going on, but we clearly have some kinks to iron out before we have a full understanding. All right, so I've cooled the ocean, I've frozen some ice, I've moved it around a bit, I've done the jiggy, but now we're going to melt the ice. And melt's going to become really useful because remember, we're basically looking for some change where we've moved from a negative feedback, possibly to a positive one. And melt's really valuable because then we start talking about sea ice albedo feedbacks, and that's a positive feedback. And so, hey, maybe, we got some answers here. So obviously the sea ice albedo feedback, everybody kind of understands it. It's really important in the Southern Ocean. It's important to point out that even in summer, almost all the melt of the sea ice is basal melt. That's not because it's driven by the ocean, but that's because but that's because the open ocean collects the sunlight, warms up, and melts the ice from underneath. And kind of that's why we get a delayed melt season a little bit in the Southern Ocean. So that ice albedo feedback is a positive feedback. If we get less sea ice, we're going to have more heat, it's going to melt the sea ice, it's a positive feedback, and so it may be really helpful in understanding what's going on. But again, that persistent story is what kind of gives us pause for thought. So again, this is work on reemergence, but basically what we're looking at here are profiles of temperature and salinity. But the key point is, once we start melting the sea ice, the surface gets really fresh and very statically stable. And of course, it gets even more stable over summer because the surface warms up. But the memory of the previous autumn, or fall if you're American, is now down here, right? It's not at the surface, it's shut away from the sea ice. So what we expect to see is that the memory of previous autumn kind of disappears in summer. And Marika Holland's written papers and various other people about this. It does reemerge later, but from the important point is that we don't expect to see a correlation between autumn and summer. But of course, now we do. I suspect, yes, my figure for that has disappeared, but never mind. So the key point here is that, again, we're seeing a change here. We've got a positive feedback that helps us explain a sustained loss of sea ice, but it doesn't help us sustain the persistence, at least not on its own. Again, we've got some kinks to work out about what's going on. So I'm going to wrap things up there. But the key point is that historically, Antarctic sea ice is a negative feedback system constrained by the ocean and dominated by some of the highest synoptic variability on the planet. The observational record is showing significant changes in variance and persistence. They're indicators of a change in the feedback systems, but they're also indicators of an abrupt critical transition, which 8 months ago reviewers were having problems with. I think that's getting harder and harder to argue now. That change behavior isn't readily explained by atmospheric drivers. Are we seeing a flip? Are we just seeing a blip that we've never seen before in our satellite record? I don't know. Thank you.
Uh-oh, how do I go back? There we go. Okay, thanks everyone for being here. So the title of my talk is Do Changes in Polar and Atmospheric Heat Transport Force or Respond to Polar Amplification? That was a pretty aspirational title that I don't think I'll answer today, but I want to give you some thoughts The inspiration for this talk was this image right here on the bottom, which is a water vapor image associated with the Antarctic heat wave of March of 2022. This was a 39 degrees Celsius surface temperature anomaly, the largest heat wave in the observational record anywhere. And we think that the advection of water vapor from Australia played a really important role in this event, as seen in this image. That water vapor rained out over the coast of Antarctica, condensationally heating the atmosphere, which gave rise to this large temperature anomaly. And you would think that in a warming world, events like this would become stronger or more frequent and would lead to polar amplification. Yet, when we look at diagnostics of the role of atmospheric heat transport in polar amplification, that role is near neutral. So here I'm throwing Pippin and Martin in the top panel there. The atmospheric heat transport is there. It's near neutral, nearly zero. I think Lily and Po-Chun gave some really nice updates to this figure yesterday, that if you consider the moist and dry transports independently, the moisture is driving polar amplification, whereas the dry heat transports are responding to it. And I'll get to that in the next slide. This lack of a change in atmospheric heat transport with global warming is more general. Here I'm switching gears and instead showing the total heat transport, combined atmosphere plus ocean heat transport in 3 different states, the last glacial maximum, 4 times CO2, and a pre-industrial. This is an ensemble of different models. And what you see is there's nearly no change in total heat transport with climate change. So what I want to think about in this presentation is that invariance of total heat transport indicative that heat transport does not play a role in polar amplification. So to start thinking about that, I'm going to propose a thought experiment where the only cause of polar amplification is heat transport. So we'll say that radiative forcing is spatially homogeneous, the radiative feedbacks are spatially homogeneous, and there's no ocean heat transport. And I'm going to frame this in the context of diffusion of moist static energy within the atmospheric column. So here I'm showing you a plot of the mean state. The colors are showing you the temperature gradient with the global mean removed at each altitude, and then the blue contours are showing you the moisture gradient at the same levels, and they have the same contour interval. So the reason I like plotting it this way is if you believe in the diffusion of moist static energy, you can visualize the relative role of moisture and temperature gradients in moving the atmospheric energy by the gradients in those 2 colors and contours, respectively. What that amounts to in the mean state, if we put a division at 60 degrees north, you've got almost 3 petawatts of heat transport in the atmosphere into the Arctic region, and that amounts to about 85 watts per meter squared of heating in the mean state, about an order of magnitude more heat transport than occurs in the ocean. That is, of course, balanced by the net radiative deficit over the polar cap. And the thought experiment I want to do is, what if we just increase temperatures everywhere by 10 degrees Kelvin? Again, spatially homogeneous. So by construction, the temperature gradient isn't going to change in this plot here. But if we assume fixed relative humidity, we're going to ramp up the gradient in the moisture there in the blue contours. And then in order to do that, if we assume that the diffusivity of the atmosphere is unchanged, you're going to bring more energy into the Arctic. That amounts to an additional heating of the Arctic by about 21 watts per meter squared. Now, this system is not in equilibrium. The Arctic has to find a way to deal with that excess energy, and it does so by warming up. So here I'm showing you the case where it's warmed up, and as it warms up, it has to continue to warm up until it gets rid of that energy. It gets rid of that energy by the combination of radiating more energy to space and by increasing the heat transport out of the region. I think what we've learned by a lot of hard work from people in this room is that the dynamic feedback, that change in atmospheric heat transport, is more efficient than the radiative feedback by approximately a factor of 2, which says that the counteracting atmospheric heat transport equatorward is going to be about 2/3 of the initial perturbation in atmospheric heat transport, with the remaining 1/3 going to radiation back to space. The key point here is that in this equilibrated state, the change in atmospheric heat transport is pretty small, even though we imposed as a thought experiment that the only thing contributing to polar amplification is an intensification of the heat transport. The Arctic is a pretty unique place in that as we melt sea ice, we invoke a positive radiative feedback, which counteracts that Planck feedback, meaning the net radiative changes are even smaller than we anticipated from the first point. And therefore, the compensation of this return atmospheric heat transport is going to be larger than we would have without that positive feedback. Okay, so the key point here is that the expected Arctic energetic response to an increase in atmospheric heat transport is a reduction of that atmospheric heat transport, which kind of seems like a silly statement, but says that this invariance of heat transport is not necessarily indicative of the what's causing the polar amplification. And that result holds because dynamic feedbacks are stronger than radiative feedbacks. Okay, so that was a lot of hand waving. How do we actually see this in some simulations? And I'm going to Brian set me up really well for this. I'm going to turn to high frequency variability of sea ice in a model context. So I'll take you through the technique here. Here we're only thinking about wintertime anomalies in sea ice. And what I do here is I divide the Arctic into 5 different sectors, which are demarcated by those lines. I'm looking at the variability in each sector independently. I'm just plotting them together in these plots to show you more comprehensive maps. So what we do in each of these sectors, we pick a central point where the sea ice variability is pretty large, and then we're going to composite around the time series at that central point. So I'll take you through the sea ice first. This is 10 days before the maximum anomaly in sea ice. This is a sea ice loss event. And then as I step forward, you'll see this is 6 days before, going all the way to 0 days. So this is maximized on the maximum sea ice anomaly, and you see those sea ice anomalies popping up in the contours in each of those sectors. Again, those sectors are independent. I'm just plotting them on the same map for visual purposes. And then that sea ice anomaly is gradually fading with time as we go to 10 days after the sea ice anomaly. Okay, so now I'm going to do the same thing. I'm still compositing on the sea ice anomalies, but I'm plotting the atmospheric heat transport anomalies. And for visual purposes, I'm not going to step through the temporal evolution of the sea ice anomalies. I'm just going to show you maps of the maximum sea ice anomaly in each of those sectors. So the colors are showing you atmospheric heat transport in watts per meter squared. Red is a convergence of energy into the area. Blue is going to be a divergence, so a removal of energy. So what we see as we step forward, this is 6 days before, right before the event, and stepping into 4 days before, we see in each of these sectors there's a convergence of energy over the area of sea ice loss. And this isn't saying that the only reason the sea ice is retreating is because of the heat transport. I think a lot of work has shown that sea ice anomalies are in part due to wind anomalies blowing the sea ice around. But what we're saying here is that on average, that comes along with atmospheric heat transport anomalies. Okay, so as we go to concurrent with the sea ice anomaly, now the atmospheric heat transport has kind of faded to more neutral. And the really important part is that if we go to times after the sea ice anomaly, we now see blues, or a divergence of energy through the atmospheric heat transport. The way I think about this is we've opened up the sea ice, we're putting a lot of energy into the atmosphere via the turbulent energy fluxes. The way the atmosphere responds to that is to get rid of the energy. And then that gradually subsides going to 10 days afterwards. Okay, so to summarize that main result, we have 2 different panels here. First, looking at the change in atmospheric heat transport prior to the event. This is like 2 to 4 days before the event. There's a convergence of energy above the sea ice. And then after the event, there's a divergence of energy over the same region. If we average over the area of sea ice loss within each of these sectors, we get time series that are shown here. The upper one is showing you the temporal evolution of the sea ice anomaly. By construction, those are going to minimize right at time 0. The more important point I want to make is this temporal dipole of the atmospheric heat transport associated with these events, that there's a convergence of energy prior to the event and then a divergence of energy after the event. Okay, so the key point is if we zoom in on this dipole, if we think about this dipole, if we time average the net effect, you have almost 0 change in atmospheric heat transport, even though we think that the pulsing of this heat transport and the subsequent removal of that energy is an important process for sea ice loss. And I think it's important to ask, can we use this as an analog for long-term climate change? And in that regard, some of the physics are the same, some of the physics are different. One thing I didn't show is that the vast majority of this convergence of atmospheric energy goes into storage within the atmospheric column. So that the atmospheric column doesn't have a large heat capacity, but on short time scales, the atmosphere has no problem storing hundreds of watts per meter squared of energy. That same process does not occur on long-term climate change. With that said, the commonality of the physics is that on long time scales, the convergence of energy has to be balanced either by a response by the atmosphere or radiative feedback, and we would think that the majority of that is going to be seen in the response of the atmospheric heat transport itself. Okay, so I'll step forward. That was in a model context. One of my goals for this conference was to try to do the same thing in an observational context. This slide is mostly a placeholder to say that when we do these calculations in a model, we do the atmospheric heat transport from the residual of the top of the atmosphere and the surface heat flux minus the storage in the column. We can't do that same calculation in observations because we don't have reliable surface heat fluxes. So instead what we do is we take the vertical integral of the flux of moist static energy in the atmosphere. We've done that in ER5 reanalysis, so we have that product at 6-hourly resolution. I'm happy to share that product with anyone in the room. I think it's a really cool product. So here I'm showing you that same result. We've coupled that with NSI-DC sea ice data, and we've looked at composites. Due to discontinuities in the sea ice data, we've composited along the tendency of the sea ice concentration as opposed to the sea ice concentration anomaly. And this is a very preliminary result. What we see is this same convergence of energy prior to the sea ice loss event. But we don't really see this subsequent removal of energy by the atmosphere. I think this has to do with the way we're dealing with the data, and I'm pretty confident that we'll see kind of the same result we saw in the model if we treat it in a self-consistent way. Okay, with that, I'll move on. About how much time do I have? 3 minutes, perfect, cool. So I wanted to talk briefly about trends in atmospheric heat transport in the reanalysis. This is work that's been led by Tyler Cox. What he's done is he's calculated trends in atmospheric heat transport over 4 different sets of atmospheric reanalysis. And what I'm showing you is the average of all those different calculations. So a 40-year change in atmospheric heat transport. Those shading is showing you the 2 standard deviations of the mean. And then the solid lines are telling you where those are statistically significant. So what we see, the area I've shaded out is the tropics. We see really big changes in the tropics, which we don't trust. We think these are artifacts of unrealistic trends in precipitation in the tropics. So I won't really talk about them in part because this is a polar theme. The more robust changes we see is we see an increase in atmospheric heat transport, polar atmospheric heat transport in the Southern Ocean, right here. And then we see a modest decrease in atmospheric heat transport, which is marginally significant going into the Arctic. And I've shown that kind of in this diagram below here, and I'm saying that that's qualitatively consistent with the diffusion of energy down the anomalous temperature gradient. So we see polar amplification in the northern hemisphere, followed by a reduction of heat transport, and we see delayed Southern Ocean in the southern hemisphere, forcing more atmospheric heat transport into the region. Okay, just to not hide how different the different pieces of reanalysis are in this calculation, these are the 4 different sets of reanalysis. So there's some regions of consistency between the reanalysis, but there really are some regions where those are different. Mera seems to be a pretty strong outlier relative to the other reanalysis. The first question we're going to ask is, do models replicate these trends in atmospheric heat transport? Here I'm showing you the result for 2 different classes of models. Fully coupled models, which are forced by historical forcings in blue, and then prescribed SST models, so AMIP-only models in green. And the storyline there is that if we look, especially in the Southern Ocean, the models that are fully coupled have problems trying to replicate that change in atmospheric heat transport. Our interpretation is that the models have trouble getting the trends in SST gradients right, therefore they don't quite get the trends in atmospheric heat transport right. But if you impose that SST gradient, they're kind of getting you the right atmospheric heat transport trend, painting the picture that the atmospheric heat transport is a response to the SST change. Okay, the last thing I'll get into very briefly, I think it was asked earlier, is how is this change in atmospheric heat transport accomplished by the atmosphere? This is a busy slide, but what we do is we decompose the atmospheric heat transport basically into 2 components. One is the overturning circulation of the atmosphere, so the Hadley cells in the low latitudes, the thermally indirect Ferrel cells transporting energy equatorward in the mid latitudes, and the other contribution is eddies, so zonal anomalies in winds and more static energy. We generally decompose that into transient and stationary eddies. I'll not consider that. I'll just consider eddies more broadly in this plot here. The only place I want to focus the result is in the Southern Ocean. We saw the total heat transport change is an increase in polar heat transport. And what we see there is that that's actually accomplished almost entirely by the eddies. In fact, the eddy heat transport change is bigger than the total heat transport change. And the reason that happens is there's a compensating change in the equatorward heat transport by the Ferrel cell. We don't think this is accidental. We generally think of the Ferrel cell heat transport as being driven by the eddy heat transports. If you increase the eddy heat transport, you drive upward motion on the poleward flank of the storm track, and this results in a compensating equatorward flow. So I think this is an important consideration going forward, thinking about the eddy heat transports might not be indicative of the total heat transport. It's also a mechanism by which the total heat transport remains fairly invariant, even though the components contributing may be changing more. And we also see that in models. The degree of compensation between the eddies and the Ferrel cell is different in models compared to observations. Okay, with that, I think I'll just show up my conclusions, and thank you.
Thank you, Aaron. Now I'll invite the other two speakers, Will and Chen, to come up front. And I know you have a lot of questions, the audience. I'm sorry if my back is to you. Do you have any questions? Who would be first? Yes.
I have a question for Will. So I really like seeing the kind of increase in variance of the sea ice plot, and you put all these different atmospheric drivers there. And I think I agree with you that the persistence is probably due to the ocean, but curiously you didn't put the ENSO time series on there. And I was wondering if you think that maybe the increase in variance in ENSO over the past few decades has played a role in setting the stage of the increase in sea ice variance in the Southern Ocean.
So I think I showed a plot which had the running 10-year standard deviations, and that did include the Southern Oscillation Index on there. Okay. And it probably just didn't pop out because the increase in variance is so small compared to the sea ice extent anomaly.
But your take is that it's not driven by, it's not an atmospheric increase, it's really just some oceanic driver increasing that variability?
I think it's hard to argue that, unless it's something to do with synoptic variability that isn't captured by those indices. Although even there, something like the Southern Annular Mode is very closely correlated with synoptic. I mean, we've had a brief look, but we don't really see, I mean, there is an increase in synoptic variability, but we don't think it's that. If it is a response to the atmosphere, there is something else about the response to atmospheric forcing. The response function must have changed. It's not a simple linear relationship.
Thank you. You can use that one.
Also, a quick question to Will. I don't remember you showing any spatial distribution of the sea ice changes, and usually it's kind of expanding in one region, declining in the other region. Can you comment on that for this these last couple of years events?
Yeah, so for the online people, could you just say your name, sorry?
Sorry, Will Budweier, Los Alamos National Laboratory.
It's true for the purposes of this talk. I like to I deliberately kept things simple and in a bulk sense. And you're true that it's correct that spatial variability historically has always been really important. There's some interesting things about spatial variability, because one of the things I didn't show today is that spatial variance is actually reduced. Whereas, as you say, in the past, you see sort of dipole mechanisms in response to the SAM or the ENSO, an increase in one region and a decrease in the other. What we've seen recently is just sea ice loss everywhere, and that's part of the reason why these extremes have been so big. There's a paper last year by Serena Schroeder that formally shows this. Interestingly, increased spatial coherence is another early warning indicator of an abrupt critical transition. So I haven't covered the spatial stuff, but there is some really interesting stuff in there.
Thank you. Well, there are some questions online, and I'll first ask Tim Carlson. How do we facilitate?
Thank you. Tim Carlson from University of Oslo. I'm not an oceanographer at all, and thanks a lot to all three of you for like 3 great talks. I have a question to both Will and Chen. I noticed in Chan's talk that the GIS model reproduced the seasonality, but not the magnitude of the sea ice extent compared to the observations. So I was wondering, having heard what Will has shown earlier, if this is either due to the surface temperature constraint or the constraint on this critical depth that we've seen? And maybe connected to that, is this critical depth something that is or could be prescribed in a model?
That is a really good point. I'm not exactly sure, but based on the conference I attended for the Geese Ocean Modeling Group, I think this salinity, the sea ice salinity, probably have some bias, so causing that magnitude is not right. So I'm not exactly sure about this.
So most coupled models have SST bias, and that's to do with clouds, and there's too much incoming solar radiation. But also in terms of the, and that feeds in, a lot of models, CMIP class models, really have no sea ice in summer. It's a, and probably if you're interested, Lettie Roach has a paper from, what, 2021? Comparing those. You're nodding, shaking your head, I know. In terms of whether you could prescribe that salinity dominance, well, the dirty little secret of all ocean sea ice models is that we use salinity restoring to keep things, you know, sensible. And so I guess, yeah, you could probably use that salinity restoring to just put a bit more fresh water into, you know, wherever you wanted. And actually, in coupled models, Arian Purik and various other people have tweaked the surface fresh water, and you do get a sea ice response. So you can do that kind of thing, and people have done it, and it's, yeah, I mean, it gets you a sea ice response.
Okay, thank you.
Okay, thank you. There is there are two other people lined up online, and then I'll come back to the general. Caroline Holmes.
I have a few questions, but let's start with a non-atmospheric one for Will. So if we were seeing this kind of change to a positive feedback system, is there anything, so given that you said it's, you know, it's constrained by these salinity profiles, is there anything that we could observe in the Southern Ocean? Not necessarily we practically can, but ideally, is there anything we can observe in the Southern Ocean that might give us a handle on whether we're entering that kind of positive feedback regime?
Well, retrospectively, it's a little difficult because, you know, we really want to see those temperature and salinity changes. I'm going to take the opportunity to make a point that came out at one of the earlier discussion groups, is we could be observing TNS profiles under the sea ice almost everywhere. It's not a technical problem. The under ice Argo technology is well established. We know that we can do airborne deployments. And if you want to get really fancy, you can even put in sonar moorings so that you know where the floats are. The German program did that in the Weddell Sea. It's not a technical challenge, it's a funding and a logistic challenge. So yeah, we could be looking at those TNS profiles everywhere, if we really wanted.
Thank you. Any other comment there? No? Okay. Nguyen Wang, who's also online.
In one of the slides you showed is a sea ice area versus sea ice volume. But I don't know if we have the same definition for sea ice volume, because my understanding sea ice volume is an integral of the ice thickness and the area and the concentration. So how come it has a spatial definition for the ice volume instead of time series?
You mean, why can you have a map of sea ice volume?
Correct.
Well, just like you can have sea ice area within a grid box, and we call it, you know, I'm sorry, yeah, I guess for clarification, that's sea ice volume in terms of what some people call effective sea ice thickness.
Okay.
Which is, yeah, that's kind of a technical question, but yeah, that's probably what I mean, yeah.
Okay, yeah, that makes sense.
Does that answer your question?
Yeah, I think that's probably the ice thickness instead of a real the volume, because volume is the integral of the thickness and the concentration over the area. Thanks.
Thank you for that clarification. I saw some hands going up over there. Aaron, can you talk loud or pop to the mic for the benefit of people on screen? online.
Hi, this is Brian Rose. I've got a question to direct to Aaron. You showed in your composites on ice anomalies, you showed, preceding ice anomalies, a convergence of atmospheric heating, and then subsequently the divergence. Real nice story. But you mentioned, I guess my question is, how much do you think you know about whether the heat transport convergence is kind of causal in those events, as opposed to sort of incidental to like wind events that are in more a dynamic sense, like driving the ice anomalies? And how knowable is that, and what's the path forward there?
Yeah, thanks. I don't know that I'm the best person in the room to answer that. I think other work has shown that the dynamic tendency in sea ice, so associated with the sea ice drift, is bigger than the thermodynamic in sea ice loss events. I guess one thing I kind of hid there is that the anomalies in atmospheric heat transport associated with sea ice loss are not huge in a standard deviation sense. The anomalies in atmospheric heat transport at 6 hourly timescales and observations are of order 1,000 watts per meter squared, and we're seeing kind of like 1/5 of that in a 1 standard deviation composite. So that implies to me, we haven't quite figured this out, that there are larger atmospheric heat transport events that are not melting sea ice. So I think there's a lot of diversity in what's going on throughout those composites, where the heat transport is definitely not the only story.
Thanks.
Will?
I actually have a question for Aaron. So on your opening slide there, you showed that really famous Southern Antarctic atmospheric river event. And it was really kind of a main line from the Tasman Sea direct to Antarctica. Now the Tasman Sea, which is, for those of you who don't know, it's the bit between Australia and New Zealand, it's one of the fastest warming SST areas on the planet. And it strikes me, we're talking about atmosphere versus ocean heat transport. But are they kind of working in concert? So you have the East Australian current, for example, warming the Tasman, and then the atmosphere finishes the job off. And I could see something with the Gulf Stream in the Northern Hemisphere. Is that something people are thinking about, or am I completely off base, or what?
Yeah, so Ed Blanchard has a really nice paper where he looks at that event in the context of nudging the winds to the observed winds, and then he can basically replicate that event, that 39 degrees Celsius surface warming event, which does not happen in a coupled model context. So the model never taps into that type of atmospheric variability to give you that event, but if you give it the winds, the model has no problem getting that event. And then he went back and he said, what's the role of the SST variability in long-term trends? And my recollection is that he found that the interannual variability of SST contributed very little to that event. But as you move forward to like a 2100 type world where SSTs are warmer, you get an amplification of that event, not only by the time mean local warming, but amplified in addition to that. And my thought is that, if the moisture advection is a really important part of this, that what sets the magnitude of that warming and that event is the moist static energy at the source, which is obviously going to change both non-linearly, and if there's spatial variability in the SST change, that will also matter.
Good. Caroline has another question. Oh, wait. Caroline, hang on a minute so that we can get a few more people in on the discussion. Clara, go ahead.
Desser Enkar. I had a question for the woman from MIT. Sorry, don't remember your name. You focused on the DJF SAM, and I just wanted to hear your rationale for doing that. And do we have to think about other seasons? Is it because it's a zonally, symmetric mode? Is that the important thing? Yeah, just want to understand that a little bit better. And how it impacts this, how it produces this decadal variability in particular.
Yeah, that's a really good question. The reason why I look at the summer SAM is because, as I mentioned earlier, the SAM shows a strong trend, and that trend is strongest during the summer season. So that's the motivation, but it's always good to look at other seasons. And another question for the, sorry, I forgot, for decadal variability.
Yeah. Right, I'm thinking, I like the paradigm of the white noise producing this decadal variability because of that residual eddy heat transport. And that's where I want to understand why why you're focusing just on the DJF.
Well, for that decadal variability, actually, it doesn't focus on the summertime. I just showing the index there. The point here is that the SAM is just like a white noise. Right. So the atmospheric memory is very short, fast. But in the ocean, the eddy heat flux that part of the ocean has a long memory. So it may have the decadal variability contribute to the sea ice extent change.
I think that's a really key insight, or I haven't seen that before. And is it because the SAM is a zonally symmetric mode? Is that the important piece spatially for this mechanism?
Yeah, in this study, I only look at the zonal mean since the residual theory is based on the zonal mean. But of course, some other parts like amiso-silo, some other region will contribute to that, the spatial distribution. Yeah. Thank you.
Caroline, you're up now.
Cool, thanks. Yeah, so this is a question for Will and Chen, I guess. So in terms of the atmosphere sea ice relationships or breakdown of, so the first question I guess is, do we have a sense as to whether these relationships between atmosphere and sea ice are consistent in kind of these different ice domains? So I guess the question for Chan is, have you looked at whether those SAM sea ice relationships are the same in like your positive and negative states? And I guess the related question for Will is just, do we have a sense as to whether in that later period the atmosphere sea ice relationships are essentially the same but just kind of offset because we've got less sea ice, or is there anything fundamentally kind of different? I mean, I know we've seen, for example, this year that there was a breakdown in the SAM sea ice relationship that we would have expected, or sorry, last year. But is that something we see more broadly, or is it just kind of an offset and that we're in a lower ice regime?
So in terms of that breakdown of the atmosphere ice relationship, so certainly in summer that has changed, and the reason why the relationship between ENSO and SAM and sea ice has changed in summer specifically is because that correlation is really strong in the Amundsen-Bellingshausen Sea, and in summer now we just don't have very much ice, and if you've got no variability, you've got no covariability. It's just as simple as that. Generally, I don't think it has broken down, and I think the model results I show that. The fluctuations are still captured and still driven by the wind, but it's just this more bias. There's something else additive. The way I think about it is, for any 1 month, you've got the previous month's sea ice plus some fluctuation, and I think that fluctuation is still driven by the atmosphere, but there's some bigger carryover. That's the way I think about it. I don't know if it's right, but that's what's in my head.
For my case, I know that in recent studies, when people look at SAM, it doesn't in recent decades doesn't look like the zonal symmetric, more like some wave pattern. But for my study, I look at more on the ocean's view for longer time scale. For example, seasonality is based on the climatology and also the decadal variability. So I'm not quite sure about the atmospheric from that point of view, how it influenced the sea ice.
Yeah, I guess just my question then was, you know, the SAM, the relationship you showed in the GISS model of between the SAM and the sea ice, that kind of lagged composite, do you still get that in the different phases of your PI control?
You are talking about the natural variability?
Yeah.
Yeah. Oh, yeah. The way I look at it is the difference, but I also look at the positive and negative case. and they share a similar pattern magnitude. So I do the difference between them. I think that's answer your question.
Yeah, I think so.
Okay, good. Yeah, I do look at that positive and negative separately. Yeah.
And I guess just a tiny little follow-on for Will, which I hope is just a yes or no. So I know the variability of the atmosphere hasn't changed. So you showed that. Is there any sense in which the persistence, because I know we've had, for example, 3 La Niñas on the trot. Have you looked at whether the persistence of the atmosphere has changed in any material way? I would assume the answer is no, but as in that it hasn't.
Yeah, just a quick clarification. We don't see much change in the variance of those indices, but we do know there are various papers showing there's more synoptic variability, especially in the Weddell-C. How far that's related to what we're seeing, I don't know. In terms of the persistence, that's a really good point. I think maybe way back in the 18 months ago and before a lot of crazy stuff happened, I think I did have a look at that autocorrelation, but I'd have to dig it up. But it's a good point. It's probably something I need to be a bit more explicit and clear about.
Cool, thanks.
We have another question.
I'll say something. I don't know if it's how useful it is, but so Aaron, this is mostly for you, but I've been thinking about this when I was sitting there and you showed the after your events, right? That kind of the divergence of atmospheric heat transport from the areas, and haven't really thought about it in quite that way. So a lot of one of the mechanisms for polar amplification, particularly in the Arctic, that has been written a lot about lately is understanding the role of these air mass transformations, right? After you put that energy in the Arctic, eventually over time, it's going to transform and become kind of polar air. And a lot of, I've thought about that more from surface energy budget radiation perspective and also what clouds are doing in terms of that. But so I was curious, is in that kind of context of air mass modification and transforming to kind of polar air, what, could you put those, the atmospheric heat transport or the getting rid of that energy by the atmospheric circulation into that context?
Yeah, I think in an ideal world, you could kind of, we're taking an Eulerian view, obviously. We're looking at, the heat transport divergence into a given region. You could do it Lagrangian, and it would be really cool to link those two perspectives. Like ultimately, the zonal mean heat transport through the polar cap has to be equal to the air mass transformation, the rate of the rate of flux and the surface heat fluxes over the Lagrangian pathway between entering and being removed from the region. I think Robert Faber might be the only one who's kind of thinking along linking those two terms, but I think in the context of what I talked about versus your kind of more long-term, for short-term variability, there's not enough time for air mass transformation, right? Like there is a little bit, but the dominant balance is just the advective in and the advection out. The radiative processes are much weaker than just the movement of the air mass than the tendencies in the column. So this might be a place where the short-term variability, high-frequency variability does not inform the long-term behavior.
Thank you. Any other question? I keep looking over to my left, but I don't want to leave other people to my right. You want to go again?
I don't know. Sorry, Patrick Taylor and Nessa Langley. So this is more of me trying to figure out, learn more about the Antarctic. But so one thing that we've looked at in the Arctic before, and so this kind of builds off sort of what you made me think of, Aaron, is that from the Lagrangian perspective, we looked at, if we can track these sea ice parcels, Lagrangian, we can, in a Lagrangian sense, we can track how the surface energy budget is changing. We could do this from satellite, but obviously, as you mentioned, we don't have the best data on how the surface energy budget evolves. I was just curious, is there, from the southern, in Antarctic sea ice perspective, could you track sea ice parcels in a way, and would it be as meaningful and useful as it is in the Arctic?
Well, I know Ted Scamboss some years ago, they'd had a drift station out of the Weddell-C measuring, they basically camped on an ice floe and waited until they had to be airlifted off. So people do those things, and there are also ice drift buoys that you can put on the ice, and it sort of stays on there and measures ocean and fluxes. So there are ways of doing that. Whether it's useful or not, I don't think we know because we've done it a bit, but not a whole lot. Yeah, I can't really answer that because my perspective is sort of under the ice, and so I don't feel especially well qualified.
Thank you. And any other question? This is your moment. Yeah, we have one more.
David Clemens-Sewall at NCAR. So I'm primarily Arctic focused, so this is a very naive question. But from my understanding of the field campaigns in the Antarctic, they found that about somewhere on the order of a quarter of the ice mass actually comes from snow ice due to submergence and flooding. And I was wondering, in any of your work, have you looked at potential changes to that process, or any speculations even on whether there'd be changes to that?
Yeah, I deliberately didn't talk about snow ice formation because I don't quite know how it fits in with the polar amplification question. But you're absolutely right. In terms of variability, snow ice formation is a very, very important process for sea ice thickening in the Southern Ocean, much more so than the Arctic. When I've played around with it and stuff, the biggest constraint on snow ice formation is actually the sea ice thickness. Because, for those of anybody who doesn't know what snow ice formation is, if you accumulate enough snow on an ice flow, eventually it kind of sinks below the surface, it floods, and that flooding refreezes. And so obviously the thicker the ice is, the harder it is to do that, right? You need more ice to freeze it. So it tends to be dominated. The other issue is that you're reliant on snowfall from reanalysis or models. And yeah, I mean, you know, that's, you know, precipitation generally is one of the hardest things. And you've got the added issue then is that snow gets redistributed. About, I think from Rob Masson's work, it's like 30 to 50% of the snow just ends up being blown into leads or whatever and not accumulating on the ice. So, and obviously that's not in a reanalysis. We've got no representation of that in a model. I guess that's a long rambling response, but it is incredibly important. I don't know how it would fit into the polar amplification question. And as important it is, it's really, really hard to do. But I think as a community, there is a recognition that snow on sea ice problem is really critical. It's also really critical to getting sea ice thickness measurements correct.
Okay, thank you. That brings us to the close of this session. I am expecting that a lot of what has been discussed and presented in this session is going to form part of our discussion in the breakout sessions this afternoon. At this moment, Alyssa will come and moderate the lightning talks.
Okay. Good morning, everyone. So we'll start session 3 this morning on the role of atmospheric and oceanic transport in polar amplification. Sorry, am I right? No, sorry about that. We're starting session 5, rather, on non-local effect on polar amplification. Yes, oh, I got it. All right. And our first speaker will be Sally Zhang, and she will give us a talk on non-local impacts of observed and projected high-latitude climate change.
Thank you for the invitation to be here. I'm Sally Zhang. I just started an assistant professor position at the University of Nevada in Reno. So today I will give an overview talk on the non-local impacts of observed and projected high-latitude climate change. I didn't say polar amplification because, as I'll show later, for the Southern Hemisphere, at least in the observed period, we don't really see amplification yet. So in the past few days, we already have seen a lot of great talks and posters showing us the observed high latitude climate change signals. And here is just a zonal mean near surface temperature trends from 1979 to 2014. And the dashed line is the observed temperature trends. And we can really see that in the two polar regions, the Arctic has a very high positive near surface temperature warming. And the colors are showing the spread across CMIP6 models with their ensemble mean in the orange line. And you can see that it actually agrees quite well with the observed trends over this period. And by the way, the solid line is showing the reanalysis. But it's very different in the Southern Hemisphere, where we see very weak trends in the observed near surface temperature, and the models tend to overestimate these trends. A lot of the models show a trend that is more positive than observed. And along with these temperature trends, in the Arctic, we also have observed a very large amount of sea ice loss. And on the right, I'm just showing the spatial pattern of the observed temperature, the observed warming. And then for the other hemisphere, you can see that the surface temperature map looks very different from the Arctic, where we have cooling over the Southern Ocean that is not spatially uniform, but also some cooling over Antarctica as well. And at the same time, the sea ice trends over Antarctica has very minimal trends. And at the same time, we also have an estimate of a very large loss of the ice mass over Antarctica, which is shown by this purple line. So into the future, we also know that both poles are projected to show amplification. And if we look at the multi-model mean from the CMIP6 models, in one of their forcing scenarios in the nearer future, so the mid-21st century, the Arctic is projected to show a lot of warming, more than anywhere else around the globe. Whereas the further you are into the future, the more warming is showing up over Antarctica. We also know that the Arctic is potentially becoming ice-free, depending on the scenario and the model, and some models show as early as the mid-century to have an ice-free Arctic in September. For Antarctica, in addition of projected sea ice loss, a lot of models also suggest that we'll have increased melting from ice shelves and ice sheets on the continent, and depending on the scenario, the amount of meltwater input will also vary with time. But I think all scenarios project that there will be an increase. So there are a lot of teleconnection pathways to communicate the anomalies or perturbations in the high latitudes into the lower latitudes. And if you think about teleconnection, perhaps you're more familiar with the other direction where the tropics influence the high latitudes. But it also works the other way around through many different processes. And here I'm just highlighting a few in this really nice review paper by Liu and Alexander 2007. So in the atmosphere, a lot of circulation changes due to changes in the meridional temperature gradient can propagate these anomalies from the high latitudes to the lower latitudes, as well as troposphere-stratosphere interaction. And then in terms of air-sea coupling, processes such as wind evaporation SST feedback can also move these signals from the high latitudes to the lower latitudes. These are via changes in the near surface winds and latent heat flux, which then feeds back to the original SST perturbations. The seasonal footprinting mechanism is another way that can communicate anomalies in the atmosphere into the lower latitude SSTs. And then in the ocean, we have both the deep overturning circulation that operates on much longer timescales, as well as the shallow circulation such as the gyre or the subtropical cells, that can communicate anomalies and perturbations from the high latitudes to the lower latitudes. There's also equatorward ventilation, as well as ocean waves that can very efficiently move perturbations from the polar regions equatorward. So first, I will focus on the Arctic, and again, these are just some observed climate change signals in the Arctic. It's just a different view of showing the warming in the past few decades, verified by various different reanalysis data set. And I also want to point out the spatial pattern, again, of the temperature trends that has a very strong warming over the Barents and Kara Sea. And on the right shows the sea ice anomalies along with its seasonal evolution. And you can really see that a lot of ice loss is happening in the fall season. So a lot of the studies that look at the teleconnection between the Arctic and the lower latitudes focus on these Arctic mid-latitude weather linkages. And these studies perhaps originated from observational studies looking at data and reanalysis. And so this is just one study that I'm trying to highlight, and by Kretschmer et al., which uses a causal inference method to look at the interactions and relationships between different processes. So this is a statistical method that really tries to robustly identify relationships between processes along with their time delays. So what's shown here is that they have identified a few different players in this mid-latitude, Arctic mid-latitude linkage, and then look at the causal relationships between them. So for example, here you can see the Barents-Kara Sea sea ice concentration, as well as the AO index and the Ural sea level pressure, and the vertical wave propagation and the strength of the polar vortex. And when you see an arrow is showing the direction of the causality, and the numbers are showing the time delays. So what they've seen from these studies that, for example, the Barents-Kara Sea sea ice can cause a positive change of the AO index with a time delay of 2 months. So what this graph really highlights is that there are a lot of different processes and lead-lag relationships that go on. So it's not a very simple image. And the fact that these colors are showing the magnitude of the correlation, a lot of these lines are very light in color, which means the correlation coefficients are not very high. So it's another way of showing that perhaps these relationships are statistically significant, but they're relatively weak. So when we look at observational studies, we know that inferring causality from observation or reanalysis is quite challenging, and especially to decouple this linkage from internal atmospheric variability is particularly difficult. Therefore, a lot of studies use climate models to study these relationships, and the short, so basically these studies are also not conclusive. So this is a diagram I took from the IPCC highlighting different pathways and plausible mechanisms of this linkage, and the bottom line is that there's very low confidence in the impact of warming Arctic and sea ice loss on the mid-latitude climate. And I also want to point out that models do have biases. For example, they can underestimate the observed eddy feedback strength. At the same time, different modeling protocols and setup can lead to different conclusions. So that also makes addressing this problem difficult. But looking into the future and studying the impact of projected sea ice loss on mid-latitude, whether a lot of people have already mentioned the PA MIMP, but perhaps some people haven't really seen the results from these experiments yet. So this is just from one of their papers highlighting that they do see a robust response, but there's still a lot of model disagreement. So here I'm showing you the sea ice forcing in these PA-MIP. So all models have this prescribed sea ice loss in blue, and where the area becomes ice-free, they will use the future SST in those regions. So the response from the models, so I forgot to mention, this is really a large coordinated modeling effort from 16 different models. And each model has a large ensemble because we know this region has a lot of internal variabilities. So they have ensemble size of 98 to 300 members, and these are also just atmospheric only models. So in terms of the results from the sea ice loss, the middle panel is showing the air surface temperature, and we see warming over regions where there's prescribed ice loss, and there's a lot of agreement between models, which is highlighted in these black stars. So if it's a black star, it means all models have the same sign. So that's great, but what we're more interested in is the sea level pressure on the right, and I'm zooming in here. So at the regions of the ice loss, we have negative sea level pressure anomalies, and a lot of models do agree. You can see that the black stars show those agreement, and that's consistent with the near surface warming. However, we also have regions of positive sea level pressure anomalies. And these regions, we don't really see these stars showing up. And a gray star means 90% of the models agree on the sign. And so a lack of stars basically show that there's a large agreement between models still on the sign of the response over Eurasia. So just to summarize the Arctic part, I really enjoy this paper by Barnes and Screen, where they frame this question slightly differently to ask if the Arctic warming and sea ice loss can impact the mid-latitude weather, or has it, or will it? And for can it, they have suggested that modeling studies suggest there is a connection, yet there's a disagreement, which is consistent with what the PA-MIP has shown. Has it? So these uses observational studies, and the bottom line is that these signals are small compared to internal atmospheric variability. And looking into the future, Arctic amplification is one of the many factors that kind of impact the mid-latitude weather. So consistently, the IPCC has also suggested there is low confidence in the relative contribution of Arctic warming to mid-latitude atmospheric changes compared to other drivers. So next, I will move to the other hemisphere, and before doing that, I again want to highlight the difference between observed temperature trends between the Arctic and Antarctica, and in particular, if you look at the multi-model mean, and these are only from the CMIP5, but the multi-model mean does not simulate these observed cooling over the Southern Ocean. So this disagreement is alarming, because we also want to know if these observed trends are forced, or it's just part of internal variability, or whether models can capture these changes. So to study the impact of the Southern Ocean cooling, again, here is showing the evolution of the Southern Ocean average SST anomalies on the left. So it's a time series plotted against the global mean temperature. And the period that I have focused on earlier is these 1979 to 2013, where the trend is against the global mean warming. I also want to mention that earlier, and day one, actually, we've also seen time series showing that before this period, the Southern Ocean perhaps has warmed more than the global mean. So first, let's focus on the cooling period. And on the right is a map showing in the background the SST trends, and in the contours, the sea ice trends. So the blue is showing a positive sea ice trend and red is negative. So a lot of regions have seen a positive sea ice trends over this time. So to study the impact of Southern Ocean cooling, we have conducted a Southern Ocean pacemaker experiment. And if you're not familiar with this concept, basically we use a fully coupled model. And for the SST of a region of interest, we nudge it to the observed evolution. So here in particular, we nudge it towards the observed anomalies over the Southern Ocean. And we also run it as a large ensemble setup. So on the left, this map is showing the ensemble mean response, so SST trends, after including the observed Southern Ocean cooling using CESM1. And you can see the cooling that's being included in this modeling framework. And because it's a historical simulation, it also includes the radiative forcing. So we want to remove that in order to isolate the impact of Southern Ocean-driven response. So the middle panel is showing the radiatively forced response, and the right panel is the Southern Ocean-driven response. And you can see that the cooling, it doesn't really only stay over the Southern Ocean. We see some cooling in the Southeast Pacific, but also in the Atlantic, we actually see quite a bit of cooling that extends into the tropical Atlantic. There seems to be some cooling over the North Atlantic as well in this period, driven by Southern Ocean cooling. So this was the original Southern Ocean pacemaker, and later Sarah Kane has led the same experimental setup, but for the later version of CESM, so CESM2, and the same format that I'm showing here. So the full response and then the radiatively forced response. And what we want to focus on is the Southern Ocean-driven response. And can see a pretty significant change between CESM2 and 1, where in the Pacific sector, there's now more extensive and stronger cooling driven by Southern Ocean cooling. I would say it still gives a significant cooling over the South Atlantic region as well. So to identify the differences between these two models' response, we have found that it's really the stronger subtropical low cloud feedback that leads to a stronger Southern Ocean-driven tropical response. So again, I'm comparing CESM1 and 2, and the top panels are showing the Southern Ocean-driven SST in the tropical region. And you can see that using CESM2, there's a much stronger cooling over the southeast tropical Eastern Pacific. And if you compare the shortwave component of the surface, the net shortwave for the surface heat budget, you can also see a very large difference between the response in CESM1 and CESM2, where CESM2 produces a much stronger shortwave induced cooling over the region where we see a stronger influence from the Southern Ocean. So again, I've shown you that the Southern Ocean cooling can produce a sizable impact on the tropics in both the Atlantic and the Pacific, yet the Pacific response is dependent on the model sensitivity, in particular in low clouds. And so this is just another view of the Southern Ocean cooling-driven response. And here I also want to show you the response from the earlier period where the Southern Ocean has warmed more than the global mean, or faster than the global mean. And this is the Southern Ocean warming-driven response, and where there are stipplings, it's showing a statistically significant response, which is the case for the tropical, the South Atlantic. But in the earlier phase, we even see warming that extends into the deep tropics in the Pacific, as well as having a spatial zonal asymmetry in the North Pacific as a result of the Southern Ocean warming. So The reason that we're interested in the earlier period is also has been hinted earlier that perhaps the Southern Ocean has gone into a different state. And this has been shown multiple times already by different talks, and I apologize for, this is Purick and Doddridge. But basically in the last 7 years, we have 3 record-breaking low sea ice summers. And these are also accompanied by warming over the Southern Ocean, not just at the surface, but also at depth. So perhaps the warming over the Southern Ocean and the sea ice loss would continue into the future. And if that's the case, then we do want to know the impact of that on the lower latitude. And studies have looked at the projected Antarctic sea ice loss on the lower latitudes, and much fewer studies have done this compared to the Arctic. And here I'm showing 2 studies led by Mark England, and on the left is the response in an atmospheric-only simulation. And on the right is the fully coupled, and I had to stretch the panel because the right figure includes the Northern Hemisphere response as well, whereas the left panel only includes the Southern Hemisphere. Where if you use the atmospheric-only simulation, the response is really localized. We see warming over Antarctica mostly, where if you use a fully coupled model, the warming extends into the upper troposphere in the tropics, but you also see Arctic amplification as a result of Antarctic sea ice loss. So this is just another view of showing that response in the Arctic. A lot of the response seems to be in the Pacific sector of the Arctic, and this warming seems to be mitigated by the warming in the tropics, which you can see that shows up, that propagates from the Southern Ocean into the deep tropics. What I also want to highlight is that the response to Arctic sea ice loss and Antarctic sea ice loss doesn't seem to be exactly symmetric. And in particular, if you focus on the tropics, Antarctic sea ice loss seems to promote a stronger warming over the deep tropics in both, actually in all ocean basins. So last but not least, I also want to touch on the impact of the projected Antarctic meltwater input. A lot of people have already mentioned the SOFIA project, and they have a nice schematic showing the potential effect of adding meltwater into the climate system, including some global teleconnections, for example, the northward shift of the ITCZ, as well as northward shift of the Southern Hemisphere jet. And this has already been shown earlier that when you add meltwater into the climate system, you see cooling that is not localized over the Southern Ocean, but you pretty much induce a global cooling pattern that extends as far as the Arctic region. So the SOFIA forcing scenarios not only includes this very idealized constant forcing, freshwater forcing, but I think they also have some more sophisticated time-varying scenarios in their later experiments. Yeah, so to summarize, so the observed and projected changes in the Southern Ocean and Antarctica are weaker and sometimes opposite to the Arctic changes. So I've shown that Southern Ocean surface cooling in recent decades can partially contribute to the observed tropical Pacific cooling, and Antarctic sea ice loss can lead to warming that reaches as far as the Arctic, and Antarctic meltwater can induce extensive cooling and northward circulation shift. And I think there are a lot of opportunities ahead to really look at the robustness of the response of adding meltwater and also having cooling over the Southern Ocean and its impact on the lower latitudes and beyond. So thank you.
Thank you, Sally, so much for the really nice summary of the teleconnection. I wonder whether we can just postpone all of the questions to the later discussion so that we can keep the time. Yeah. And I want to introduce the next speaker, but I'm not sure if the speaker is Jung Chen?
Hi.
She's virtual? Okay, sorry. Yeah, so Jung Chen from the National Taiwan University will give a talk on the role of mean states on atmospheric responses to high latitude thermal forcing and Arctic warming.
Oh, okay. Can you hear me?
Yes.
Okay. So good morning, everyone. I'm Yongzhen Chen from National Taiwan University, and today I will talk about our study about atmospheric response to high latitude thermal forcing and the role of mean state on it, and some implication to polar warming. So previous studies have indicated that changes in polar region ice coverage can affect the tropical climates, even climate like sea surface temperature or precipitation and tropical circulation. So we can see that in Chang and Base 2005 that mimic the ice extent in a less glacial maximum and see the tropical sea surface temperature changes. And also in England at all 2020, they remove the polar sea ice to see the tropical response and also see the precipitation changes. And in Conley 2009, they provide an energetic interpretation to explain this as a tropical to tropical teleconnection. So they suggest that an extratropical thermal warming would cause a tropical ITC shifting. This is because the energy needs to transport from the warmer hemisphere into the cooler hemisphere. And during this process, the ITC will shift into the warmer hemisphere and cause a non-local effect. And in their interpretation, the energy transport can be explained by a diffusion process by eddies. Also, with another interesting thing from King et al. To 2021, they show that the efficiency of the polar heating in perturbing the remote climate is sensitive to the altitude at which warming is imposed. So in their work, they impose warming, the sun warming at different altitude, and they calculate the meridional energy transport and local non-local radiation adjustment at the top of the atmosphere, and they found something interesting is an upper level warming would cause a stronger response of atmospheric energy transport. And also a stronger energy transport will lead to a larger ITC latitude response, or we can call that a stronger non-local response. So we think it's interesting because they impose the same warming at different at latitude, but cause different atmospheric energy transport. So we guess that maybe we can provide some dynamic interpretation to explain this this teleconnection, why they have different efficiency when the warming is imposed at different latitude at latitudes. And also another thing is when we talk about the polar amplification, especially about Arctic temperature, we can see that in the winter and in summer, the warming structure is is quite different. In the winter, the warming is more trapped near the surface, and in the summer, the peak of the warming locates at a higher latitude. So we guess that maybe the different seasonality of warming structure will cause the different efficiency of the non-local effect on lower latitude. So now here is our method. We use the GFDLO-AN2 aquaplanet version and coupled with a mislayer or slab ocean, and it is also used in Kang et al. 2009. Then we impose an polar warming in the extratropics, and also because we would like to know the different season may cause different efficiency of teleconnection, we construct to perpetuate control climates. So our way is to expose warming and cooling in the extratropics to mimic the seasonal like background state. So we have two control climate, and one is the astral summer like climate, and another is an astral winter like climate. So we can see in the summer like climate there is an clockwise cross equatorial hemisphere and a weaker subtropical jet in the southern hemisphere. And also the thermodynamic state in the summer-like state, the southern hemisphere is more unstable. And in the winter-like case, there is an counterclockwise cross-equatorial hemisphere, a stronger subtropical jet, and more stable atmosphere in the southern polar region. So next we can see, we would like to see the warming structure in response to a mislayer warming. So here, this two plot is the contour means the anomalous potential temperature in summer-like case and in winter-like case. We can see in the summer-like case, the warming structure is quite different to that in winter-like case. The warming is vertical extending in summer-like case, and in the surface, in the winter-like case, the warming is trapped near the surface. So we would like to know this very distinctive warming structure may cause different mid-latitude eddy response. So next we apply the Ellison-Plum flux to check to analysis the mid-latitude eddy response. So here we show the definition of Ellison-Plum flux is it have two components. The horizontal component is the eddy momentum flux, and the vertical component is the eddy heat flux over stability term. Then here shows the topical climatology of EP flux. One can see that the transient eddy will generate near the mid-latitude surface and propagate outward. Then in the upper level, it will propagate horizontally into the subtropics and in the polar region. So next we can see, here we show the EP flux response in these two different cases. So the contour is the same in the last slide, but the shading means the anomalous vertical component of Ellison-Plum flux, and the vector is anomalous EP flux. So we can see the wave activity response is very different in the summer-like case and in the winter-like case. In the summer-like case, the eddy response is more stronger, and we would like to. So we guess it's things like the warming structure can explain how the magnitude of eddy response. Then we would like to further analyze it. So we decompose the vertical component of Ellison-Plum flux. So it is decomposed by Chen rule. So one can decompose the vertical component into two different terms. The first one is the eddy heat flux term. It means that when a warming is imposed, warming happens in the polar region, it will decrease the meridional temperature gradient and then cause a decreased eddy heat flux. So the decreased eddy heat flux will cause a decline EP flux. This is their effect of the eddy heat flux term. And the second one is stability term is something special because it's seldom been mentioned in previous study. So in a physical interpretation, one can imagine when we have a surface trap warming, the warming near the surface. Honestly, it will make the atmosphere more unstable, and the more unstable atmosphere will enhance the wave generation. So So the stability term will cause a negative contribution to vertical component of Ellison-Plum flux. So next step, we would like to see the decomposition of the EP-fast response in these two cases. So first, we see in the summer-like case, we can see that the shading means the eddy heat fast turn and stability turn. So the first row, the shading in first row equals to the second row at plus the third row. We can see in the summer-like case, the decreased meridional temperature gradient will lead to a decrease eddy heat flux and cause a wave generation decrease. And in the stability term, its contribution is very small. This is because the warming extends vertically, so it could not cause a strong stability changes. So finally, because the strong eddy heat flux contribution, it will cause it would suppress the wave generation in the summer-like case. However, when we see the result in the winter-like case, we can find that the eddy heat flux turn still can decrease the wave generation. However, because the warming is strongly trapped near the surface in the winter-like case, the stability turn contributes largely to the wave activity flux response. It means that this very strong trap warming makes the atmosphere more unstable and to enhance the wave generation. So in the winter-like case, these two competing effects will make the wave mid-latitude wave response very weak. So here we suggest that the warming structure will affect the wave response. And in the next step, we will show that the wave response is important to affect the non-local effect. So we can see in this in these two cases, the summer-like case have more stronger wave activity response in the lower levels, and fewer it will cause a strong polar wall eddy activity anomalies in the upper level. And the shading is the eddy momentum flux convergence or divergence. Because the stronger polar wall eddy activity anomalies, it will cause an anomalous eddy momentum flux divergence in the mid-latitude and convergence in the subtropics. And in the winter-like case, the eddy momentum flux response is very weak due to a weak wave generation response. And next step, we see the string function. The shading and vector is the same with the last slide, but the string function upper black contour means the string function. We can see that in the summer-like case, the eddy momentum flux convergence and divergence anomaly will be balanced by the meridional wing and finally lead to a weakening of varial cell and Halley cell. And in the winter-like case, still it will have a very weak response about the scalation. So now we're back to the King et al. And we try to compare with their energetics perspective. So they suggest that upper level warming will cause a stronger atmosphere energy transport and cause a stronger non-local response. So we also calculate the meridional energy transport in our study and found a consistent result that in the summer-like case, the meridional energy transport is more stronger than in the winter-like case. And we offer a dynamical interpretation for this, is that the warming structure is very important to determine the wave response, and the wave response will cause the different magnitude of the atmosphere energy transport and non-local effect. And next, we would like to apply our understanding to a set of more realistic climate change experiments. So here we use a double CO2 experiments, and we use CS1 fully coupled model. And this model, we couple it with the slab ocean, so we isolating the ocean dynamic process. So we can see in the Arctic and Antarctic, the shading means the vertical component of wave activity. So it also can say it's a response of wave generation. One can see in the very high latitude, there is a positive anomaly, means wave generation is increased here. So we also can decompose the vertical component of wave activity here. So the second row is the eddy heat force turn. One can see that this response shape the seasonality of the wave activity response in Arctic and Antarctic. And also we can see that stability turn can contribute to the wave activity response too, and especially in winter and at very high latitude is here, yes. So here is my summary. We found that the climatological stability is important to determine the eddy response, and the eddy response can affect the efficiency of the polar to lower latitude teleconnection. And also we see our idealized experiments and more realistic experiments also both suggest that the stability term is important to consider. And thanks for your listening.
Thank you very much, Jung-Jen. So we will have the last speaker coming up, Luke Fraser Leach, and he will talk on correcting for artificial heat in sea ice perturbation experiments.
All right. So yeah, I'll be discussing using multi-parameter pattern scaling to interpret polar amplification in Earth system model experiments. Most of this is going to focus on our recent paper on using pattern scaling to correct for artificial heat in coupled sea ice perturbation experiments. Okay, so Sally touched on this a little bit, but I'm going to be focusing on imposed sea ice loss in coupled models. So this is the way you do this. There's multiple methods, one of which is so they range from like simple methods like the albedo modification method, in which you darken sea ice and that melts it, to more sophisticated methods like the one developed by Alexandre Laudet, this hybrid nudging method. And these allow you to constrain sea ice to a target state in a model without any greenhouse forcing, which allows you to study the response to sea ice loss in isolation. But this recent paper by Mark England et al. Points out that these coupled perturbation methods add artificial heat to the climate system. And so I'll focus on using multi-parameter pattern scaling to apply like a first order correction to this issue. So the idea behind multi-parameter pattern scaling is kind of an extension of the traditional one-parameter pattern scaling idea, which assumes that the response of some field Z to greenhouse forcing, if you just ignore the sum in this equation here, is some spatial pattern that scales linearly with some internal climate variable, usually global mean surface temperature. Multi-parameter pattern scaling just extends this to n different forcings. So if you have capital N different experiments, you can decompose those n different experiments into partial responses to n different internal scaling variables. And throughout this presentation, n will be equal to 2, and the scaling variables will be some measure of direct greenhouse forcing and some measure of the effect of sea ice loss. So the first study to do this was led by Russell Blackport. He decomposed the response in the RCP 8.5 simulation in the CESM large ensemble using an albedo modification method. And you get partial responses in this bottom row here, so a partial response to low latitude warming, which is the part that scales with tropical SSTs, and then that's supposed to represent the direct response to greenhouse forcing, and then a partial response to sea ice loss. And so these two bottom panels add to the top left one. And one of the notable things that they found was that it reinforces the idea of a tug of war over the mid-latitude jet between direct greenhouse forcing and sea ice loss. And this has been found in subsequent studies. For example, this multi-model comparison led by Stephanie Hay. So again, we see this tug of war over the mid-latitude jet. But a cancellation between these two partial responses is kind of a more general feature of multi-parameter pattern scaling when applied to these perturbation methods. And in some cases, they're not as well physically motivated as the mid-latitude jet. For example, it's not clear why you would expect an Arctic cooling in the partial response to low latitude warming, which is supposed to represent the direct greenhouse forcing. Yeah, so there's these negative pattern correlations that often pop up, so you get large cancellations between the partial responses. So that's multi-parameter pattern scaling. To discuss artificial heat, I'm going to first focus on the energy balance model used by Englund et al. So this is a fairly standard energy balance model with a balance of incoming shortwave, outgoing long wave, and diffusive heat transport. In this graphic, it's diffusing temperature or dry static energy, but I'll be using a version that diffuses moist static energy to represent poleward latent heat transport. And it has a simple representation of a simple thermodynamic sea ice representation, which allows you to impose these sea ice perturbation methods in this model. But the nice thing about it is that in the global mean, this thermodynamic sea ice model averages out, and you just get a classic energy balance model where the response to some greenhouse forcing is the outgoing long wave response that balances the forcing and the sea ice albedo feedback. And here I've just taken annual and global means to simplify things. And so the true effect of sea ice loss in this model is just the sea ice albedo feedback. That's the part of this equation that depends on sea ice. And so this is what Englund et al. Did, is they compared this response, the true sea ice loss effect, to the temperature response in artificial heat, or in sea ice perturbation experiments. And for all three, they find significantly more warming in the perturbation experiments than in compared to the true effect of sea ice loss. And the reason for this is not some detail of one of the perturbation methods. It's kind of a general feature of constraining a sea ice model to a state that it's not in equilibrium with. So if you're constraining a thermodynamic sea ice model to some state that's not in thermodynamic equilibrium with the background climate, so for example, a sea ice state that corresponds to doubled CO2, while the climate has like present day or pre-industrial CO2, the sea ice will not be in thermodynamic equilibrium. If let to its own devices, it would just grow back. So you have to add some artificial heat flux to keep it in that perturbed state. And that's what all of these perturbation methods do, sometimes in a more obvious way, like for the ghost flux. It's pretty well acknowledged that the ghost flux violates conservation of energy. But in some cases, it does it in a more sneaky way. So for example, in a nudging method, the artificial heat is the heat that you've implicitly added by removing sea ice and adding fresh water. And then in the albedo modification case, the artificial heat is the short wave that's artificially absorbed because the sea ice is artificially darker, or the remaining sea ice is artificially darker. So we can learn more about this effect by applying multi-parameter pattern scaling to the global mean, annual mean of the EBM, global mean, annual mean temperature response. And we see this, that the partial response to sea ice loss contains this physical contribution from the sea ice albedo feedback, but it also contains this artifact from the perturbation method that you've used. And then because these two partial responses have to add up to the total in the greenhouse forcing experiment, there's an artificial reduction in the partial response to low latitude warming. So this suggests that sea ice loss is not, or sea ice area isn't the right variable, because in these simulations, the climate is responding not just to the sea ice reduction, but also to the artificial forcing. So it suggests instead scaling by like the total sea ice forcing, heat flux forcing, which is perturbation plus flux plus the physical contribution. When you do this, you get something more reasonable. So the global mean temperature partial response scales with inversely with the outgoing long wave parameter in this model, which is what you'd expect for the global mean response to any forcing. So it works in the global mean. We can also apply this to the output from the EBM to look at the spatial distribution. So just focusing on the top two panels, the solid curves are the original sensitivities without the correction, so the red box here. And the top panel is the true effect in the partial responses diagnosed from the true effect in the moist EBM, and then the second panel is the responses diagnosed from an albedo modification experiment. And what we see, there's significant differences, namely there's a ton of Arctic warming and Arctic amplification attributed to sea ice loss, and then there's this tropical amplification attributed to low latitude warming, and then the dashed curves show this correction, and you recover something more like the true responses, and namely both low latitude warming and sea ice loss contribute to Arctic amplification, which in the moist EBM is due to latent heat transport. And we can do something similar in a modified albedo simulation in CSM. There's no true, well, we didn't come up with a true simulation that we can compare this to, but the story is similar to as to in the moist EBM, which gives us some confidence that we're recovering similar effects. Namely, once you correct for the artificial heat, you get both sea ice loss and low latitude warming contributing to Arctic amplification. So as I mentioned, it's hard to have a true sea ice loss experiment in an ESM. That's kind of why we're in this whole mess in the first place. I won't go over this in detail, but I'll say it's even harder in non-albedo modification methods. So for example, if the perturbation method imposes a ghost flux, it's not clear that that ghost flux should be added to a top of atmosphere radiation. So we played around with the surface energy budget a little and came up with something that maybe is reasonable, but it's hard to justify. However, this work by Nicole Feldl and others from 2020 shows that the lower Arctic lapse rate feedback scales with, is highly correlated across the CIMA 5 ensemble with sea ice loss. And this has independently motivated Stephanie Hay to look at using lower Arctic lapse rate as a scaling parameter. And it turns out you get similar answers if you use lapse rate, Arctic lower tropospheric lapse rate, as if you use the sea ice forcing scaling that's motivated by the EBM. So here in the top row, I have the partial responses with the original non-corrected parameters. In the middle row is the sea ice forcing correction, and then in the bottom is the partial responses to tropical upper tropospheric lapse rate, it's a measure of direct greenhouse forcing, and then Arctic lower tropospheric lapse rate, it's a measure of the sea ice forcing of the atmosphere. And so, namely, the key thing here is that both of these have less Arctic warming than the original sensitivity, and they both have this Arctic amplification that is attributed to the direct greenhouse effect, which is not seen in the original sensitivity to low latitude warming. We find similar things in the PAMIP experiments at CSM Wacom. So there's this Arctic amplification attributed to direct greenhouse forcing. And then we've also applied this to zonal wind in the CSM Wacom experiments. So the original sensitivities do show this tug of war over the mid-latitude jet. Once you correct for the artificial heat, the tug of war is definitely still there. It's weaker, I think, by about 50% maybe. And we find a similar thing when we scale by lapse rates. So this suggests that the artificial heat may exaggerate the tug of war because in the sea ice perturbation experiment, there's this stronger forcing. Yeah, so to conclude, we've used multiple parameter pattern scaling to recover the true global mean response in an EBM. We find similar results in a comprehensive model, which suggests the sea ice forcing scaling can recover the true response in that model. However, it's difficult to justify. We don't necessarily have a true sea ice loss experiment in ESMs. And worse, for methods other than albedo modification, it's actually hard to choose a scaling parameter. However, the lapse rate scaling is physically motivated. We think it represents the sea ice forcing that the atmosphere feels, including both the contribution from the real sea ice loss and from the artificial forcing. And it gives similar answers to correcting using the sea ice forcing scaling. And the general theme of this first order correction using pattern scaling is that it's in line with the original Mark Englund study, which is that sea ice perturbation experiments overestimate the response to sea ice loss because the climate is responding not just to sea ice loss, but to this artificial forcing. And this in turn can imply exaggerated tugs of war between low latitude warming and sea ice loss. Yeah, thanks.
Much, Luke. So now I would like to invite Sally, Luke, and Jungjen, if you can join us online as well for the discussion session.
Thanks to my co-convener, Anne, for convening that session. So I think we have about half an hour for discussion among the whole group. So I'd like to invite folks up to the microphones to ask questions of the speakers or raise broad points. And let's start with Lily. Go ahead.
Okay. Yeah, thanks for the great talks. I had a question for Youngjen Chen. So I was curious if you could talk more. At the end, you showed some differences for the Arctic versus Antarctic warming and how that impacts lower latitudes. I was just thinking also in relation to Sally's talk, where she was showing that Antarctic forcing is more effective at impacting the tropics and having more of kind of a global response than Arctic forcing. I was just curious if you saw differences in your kind of non-local responses to Arctic versus Antarctic warming in your framework.
Yes, it's a good question, but because we use the double CO2 experiment to see this teleconnection, and I think we can now isolating the infused influence from the tropical upper warming. So our next step, we would like to design some experiments to only have a sea ice removed experiments to see that. And I think another interesting thing in Sally Zhang's presentation is that Southern Ocean has a very special pathway to amplify its teleconnection, as they talk about the low cloud effect. So it is very zonal asymmetry. They have a preferred pathway to cause this teleconnection. But this is something different from my study because we all see this teleconnection in a zonal mean aspect. So I think it is interesting to study this. And I'm not sure when we only see about this transient eddy aspect, the efficiency of non-local effect from Arctic or Antarctic would different. I'm not sure about that. Maybe need more experiments to analyze it. Yes, thank you.
Cool. Yeah. Thanks. Yeah. Yeah. It'd be interesting to look at because you're also looking at kind of like Hadley cell responses to both of these things. So yeah, I guess that could also be interesting to look at. Thanks.
Thanks. I'd like to just remind people to introduce yourselves when you're asking questions so folks know who you are. And I know Will will do that. So go for it.
Yeah, Will Hobbs. I got loads of questions, but I'm going to focus on one that I hope unites all three speakers. So I'm kind of interested in the time scale of these far field responses and the question of the role of atmosphere versus ocean teleconnections. And if those teleconnections are primarily shorter term atmosphere teleconnections, would we be better off just using an atmosphere only model with perturbed sea ice state, and then that overcomes the issue that Luke was highlighting with these coupled models and what that does to the energy balance? So yeah, discuss.
Yeah, I think it depends on the response you're interested in. I think, well, a lot of this coupled work was motivated by a study by Clara Dessa et al. From 2015 that show that there are pretty significant differences between the coupled atmospheric and responses. But yeah, I think if you can find something where you think the ocean doesn't make as much of a difference, it would help not to have this additional heat issue.
Yeah, I also want to point out that a lot of these processes happen at the air-sea interface. So you do sometimes need the ocean to be coupled with the atmosphere for some of these perturbations to be propagated into the lower latitudes. So with an atmospheric only model, for example, you wouldn't get the wind evaporation SST feedback. That wouldn't even happen in an atmospheric only simulation.
Yes, I think the time scale probably is important, and also I think is one thing interesting in our study is that if we involve the air-sea interaction, the signal will be amplified. So I think of the time scale between the time scale of the atmospheric process and oceanic process is quite different in my understanding, but I think it still can cause some significant phenomenon about the atmospheric process, especially when talking about seasonal dependence and the time scale in a subseasonal time scale. Yes.
Thanks. Xiyue Dong from CU Boulder. I have a question for Sally. So you show nice results of Southern Ocean pacemaker rounds. I think these simulations prescribe observed anomalies on the top of a model's mean state. So I was wondering if you have any thoughts on whether, and if so, how model mean state biases in the Southern Ocean could have any impact on the simulated trend and mean state in lower latitudes.
Yeah, that's a good question. We have never compared prescribing the anomalies versus the absolute temperatures, at least for the Southern Ocean pacemakers. And I think it would be nice to do that, but also there's a need for more models to, or have a coordinated effort where we can study how each model's mean state and their biases impact the remote response in the tropics.
Kyle Armour here. Can I just follow up very quickly just to ask the same question, but for the tropics? Do the tropical mean state biases matter? For instance, the position of ITCZ or cloud biases?
Yeah, I think it would, because the CESM 1 and 2 also have very different mean state in the tropics. We haven't specifically looked at how the response depends on that, but that's definitely an area to explore.
Yeah, Mohammed from NCAR here. I've also several questions, but just pick the comment for Will's question. I think the problem is like there's a seasonal cycle, and many of the processes involved have an intrinsic timescale that is about 2 months or a season, right? So as you showed from Kretschmann or the study, right? And then the mixed layer also has like a few weeks or whatever. So everything is wobbling around, and we always look at equilibria. When we do perturbation studies, we often look at zonal mean equilibrium responses, right? Even though everything is responding, and at the same time the forcing is changing. So, and I think we have to disentangle that, but you can turn off seasonality in models, you can turn off topography in models, right? You can tease out the different timescales for different components.
Yeah, very nice comment.
I think we have an online question, so let's go to that.
Hi, I just wanted to jump back to the two questions about the Southern Ocean pacemaker. One thing I think I noticed, and please correct me if I'm wrong, was that the pacemaker experiments when they were warming versus cooling had different impacts on the subpolar gyre. So the cooling pacemakers seemed to have a large negative impact on the subpolar gyre, but the warming didn't. And I was just curious if you had any thoughts as to why this might be.
Which basin are you referring to?
So in your pacemaker experiments, the Atlantic, sorry, the North Atlantic subpolar gyre.
Yeah, we haven't really looked at the gyre circulation or analyzed them in these experiments. But I also want to point out that the forcing is not exactly asymmetric. So if you can see the pattern of the prescribed cooling in both experiments, there is a lot of spatial or zonal asymmetries. And I think that's something to look into if you want to focus on specific basins. Yeah, thank you.
Great, thanks for the question. Let's go to that side of the room.
Wisław Maslowski, Naval Postgraduate School. Primarily question to Luke, but others might well want to comment as well. So tug of war in terms of the tropical warming due to greenhouse gases and the sea ice decline. Would that somehow affect the detectability of the teleconnections from the declining sea ice in Arctic to the mid-latitudes? I wonder if you have any comments on
that. Sorry, could you how the tug of war affecting the detectability in relation to the
All the simulations suggest that sea ice decline is basically within the noise level of the atmospheric variability. So if you account for that tug of war, artificial tug of war, whether that would increase or make it more detectable in climate simulations, effect of sea ice on teleconnection?
Well, the artificial heat is going to exaggerate. I don't know if it has much bearing on like the historical record. Most of this is focused on like artificial perturbation experiments focused on the future, where it would probably reduce the detectability of teleconnections because what you thought was just sea ice forcing is actually like something like double the forcing. So the actual signal attributed to sea ice loss is weaker than what you thought it was before.
Hey, Claire Desser, NCAR. I had a question for Luke on this artificial heat. So when we do atmosphere-only runs where we supply a future ice state and compare it with the present day, obviously there is a lot of artificial heat to where you prescribe ice loss. So how are we also, I mean, in any kind of, model control where we're controlling one field, is this an issue as well? I just want to hear some more discussion because I'm a bit confused.
Yeah, that's a good point. I've been thinking about the atmosphere-only simulation. So I think because you're specifying SSTs, where there's sea ice loss, usually SSTs are specified from the future warmed state. I think that's right. In that case, the artificial warming would come from, there would be artificial warming from the fact that the SSTs are, the warmed SSTs are coming in part from greenhouse forcing. So you have some greenhouse forcing in the sea ice experiment.
Yeah, so the early experiments with atmosphere-only models, we didn't change the SST. That was kind of a later step, and it didn't really materially affect the response.
Yeah, I mean, I do think it would be weaker in the, just a guess, but I think the effect would be weaker in the atmosphere-only simulations because you're not constraining the whole thermodynamic sea ice model. It would just be this effect on the SSTs, like in the marginal sea ice regions. That's my guess.
Okay, thank you.
Patrick Taylor, NASA Langley. I'm going to hold it so I don't have to squat down. But this question mostly for Sally, but anybody could sort of comment. In these teleconnections, we know that atmosphere-ocean exchanges are important, and we know that well, actually, before I keep going, Sally, what's the resolution of your ocean model? Is it the 1 degree? 1 degree. Okay. So where I'm going is I'm curious how some of these teleconnections might be influenced if we increase the resolution of the ocean model, because we know that the mesoscale and submesoscale ocean can impact the jets, and that'll impact their surface turbulent fluxes and all these interactions. So I don't know if you've thought about that, or if that's something we should pursue to see if we better resolve the ocean, how these teleconnections could potentially change.
That's a great question and a really interesting point. We've seen in the IHASP, so the high resolution fully coupled simulations, that over the Southern Ocean there is way more decadal variabilities that the low resolution model does not have, at least for CESM1. So that is definitely suggesting that the mesoscale ocean eddies are making a difference over the Southern Ocean. And in their simulations, they also see increased predictability that expands over the Southern Ocean, and also that pattern extends into the tropical Eastern Pacific. So I suspect that if we do a pacemaker style experiment with a high resolution version of the model, we might see a different response in the tropics. That's, I think, unknown and needs to be explored.
I also have a question for Sally. In your Southern Ocean pacemaker experiment, you briefly talk about interesting interhemisphere interaction. So there is Southern Ocean cooling, and you see some signal cooling in the subpolar North Atlantic. I wonder, is that more related to the atmospheric process causing this hemispheric teleconnection, or through the ocean process, such as the change in AMOC?
That's a good question, and we haven't really analyzed. So yeah, we definitely noticed the signal in the North Atlantic, and initially we were worried about the initial condition of these experiments and whether the response of the AMOC is sensitive, because all the ensemble members start from the same kind of ocean initial condition. But I was also told, I think we need to definitely work with oceanographers in understanding that signal, whether potentially waves in the ocean can propagate that signal, because we're only looking at trends over a 35-year period. In terms of AMOC, that might be quite fast for the AMOC to fully respond to the perturbation over the Southern Ocean. But yeah, I'm happy to talk more about that.
Hi, Chen Ken from University of Chicago. I have a question for Luke. In the pattern scaling approaches, you have a full global warming simulation and a sea ice loss simulation, so you can track out the impact of lower latitude warming. So I was wondering if you can do that the opposite way around, and would that be an approach to account for the impact of artificial heating?
By opposite, you mean doing an experiment where you have some greenhouse forcing with sea ice at a constant state?
Or like you have a greenhouse gas forcing and you tweak something in the lower latitude so that you can attribute, you have an answer for the higher latitude changes.
Like you nudge the lower latitudes or something like that?
Kind of way. I know it could be a difficult.
Yeah, so I think most of any approach where you're nudging to a mean state, like where the means, so in like nudging experiments where you're nudging the winds, the nudging is not nudging to a different mean, right? It's just reproducing variability. So you can assume that the nudging on the mean has no effect on or has minimal effect on the simulation. But if you're nudging the model to a state that has a different mean from what it's in, I think you're going to run into this issue no matter what you try. So I think it would probably apply to nudging lower latitude SSTs. It would also apply to what I thought you were talking about, which is running an experiment where you have future sea ice loss, or you have greenhouse forcing where you hold sea ice fixed.
Follow-up. I have a follow-up. I think this is really crucial for me especially, but everybody, how we deal with this artificial heat issue in our coupled experiments. So for example, the Southern Ocean pacemaker runs, are they subject to the same issue here? And is our approach, can we continue to use these protocols with the coupled models to probe, how different regions impact remote regions, but apply maybe a pattern scaling to then mitigate that artificial heat? Is there a problem with Southern Ocean pacemaker runs in a nutshell?
Well, I'm sorry for my ignorance, but
yeah.
A pacemaker run, you're nudging to observed internal variability, is that right?
We're observed anomalies relative to some, climatology in the observations for SST. But, I mean, the Southern Ocean has cooled, so it has really been drifting to a different mean state. We could have done it, as two different future,
right,
later state and earlier state.
Yeah, I think if you're nudging to a different mean state, it probably would run into the same. If you're nudging to anomalies, I think that might be a different story, because on average you could assume that whatever you're adding, whether it's SSTs or wind, like the momentum or heat flux that you're adding averages out to roughly zero. But if you're nudging to the entire field that has a different mean state, then yeah, I think it might run into a similar issue.
So what is our way forward as a community? Do we then apply pattern scaling? I mean, I'm completely just opening it up. Yeah.
I can just add that I think I'm thinking back to like Xiyue Deng's work where she looked at freshwater hosing experiments. And one of the nice things about that is you don't need to impose SSTs which effectively is imposing some kind of heat flux to nudge the Southern Ocean. So I'm excited about SOFIA as a kind of model intercomparison to extend that approach to look at feedbacks in tropical teleconnection from the Southern Ocean, where you don't have to worry about these kind of things because you're not adding any energy to the model, or very little, by adding some fresh water in the Southern Ocean. So that's one way forward, but beyond that, I'm not sure.
Fresh water will have a different impact on stability, et cetera. I mean, I think there's a lot of issues here.
Well, I thought what Luke was saying was that if we nudge with the model's mean state and add the observed anomalies, it wouldn't be as big of an issue as...
Yeah, if you nudge with the model's mean state. But I thought that was kind of it. You get important differences whether you nudge to anomalies or the mean state. I think the approach suggested in the original England paper was kind of, focusing on more specific processes like hosing or only looking at the effect of albedo, the albedo feedback. So more like process-based rather than the effect of sea ice loss as a whole, which is, I think that's viable. I don't love the idea of just running the pattern scaling correction that I showed. I think it's a decent like first order correction, but it doesn't account for much detail of the artificial effect. It's basically just scaling down the entire response in the sea ice perturbation simulation based on the energetics. Another approach, I think the approach by Igwo Dai in a 2019 paper, basically they go into the coupler code, and I think they use, basically they just tell the coupler, I'm actually forgetting exactly what they did now, but they tell the coupler to see the sea ice thickness in the future simulation. Don't quote me on that. I have to double check the paper, but I thought that approach might be viable. I think that should be looked into.
Unlike Patrick, I have to move it down. This is Ann Nguyen at UT Austin. So I'm an oceanographer. I primarily use the ocean model, force with atmospheric states. And so I think it's a little bit related to Will's question, but I think in the opposite sense, I would say, in that, in my experience, it has, my experience has been that I think the forcing that we received is not taking into account enough the ocean and sea ice state, the variability of it, according to what we, as from the couple ocean sea ice, is seeing in the response of the ocean alone compared to observation. So what I mean by that is, for example, we use the forcing from atmospheric reanalysis, right? And it has been, since I started using it in 2007, but it has been dated all the way back to the beginning of ECMWF, for example, that they had been using a slab ocean with some slab sea ice model as their lower boundary, similar to, I think, some of the experiment, for example, Chen mentioned the slab ocean, or in your case, you were talking about the ocean. And it has been known to us, the oceanographer, at least in the Arctic, that it has a bias since the beginning of the time series when they provided, and it has now been 20-something years later, and we are still facing with 5 degrees Celsius bias of the air temperature in the atmosphere, forcing the sea ice. So obviously, I think the ocean is very important, and to go back a little bit to, for example, to these couple ocean model that people use, that I do know the community used to look at the atmosphere. Whenever I look at the Arctic Ocean circulation or the general subpolar North Atlantic circulation, I would think that this is not represented at all in what we would observe in the circulation and the changes in the ocean. So typically, we wouldn't even use these to study anything related to ocean circulation or changes because they don't represent the circulation. So I think a lot of the feedback that you see or the teleconnection you see, I think it might be depending on whether you even represent the ocean properly. So that was more of a comment. And then I just have a slight question on, because you show the result depending on CASM 1 or 2, that obviously you get a very different response. And as a modeler, we understand as well that supposedly we improve the model physics maybe, or what is it in general that suddenly you get, you know, let's say a stronger response. You still see similar response in the previous version, but now you get a stronger response. And if we are to conduct scientific, you know, publications on a result, and the next generation you get quite different response or even opposite sign, how is the community, you know, respond to these kind of changes? Are they within the error bar of the model structural error? What are the improved physics, and yeah, how we would go about it?
Yeah, so we have not looked at every component of the model to compare the difference between the two, but what we do know is that in CSM2, there's a pretty big change in the atmospheric model involved with clouds in the subtropics, and CSM2 has a more realistic representation of the low cloud feedback. That's something we did quantify, but there are other potential factors for sure.
I think we're nearly out of time, but let's go with the final question to Pat if we can do it quickly.
Okay, I'll try to be fast, but I'll go back to what Clara was mentioning about, you know, this methodological kind of challenges that we have. And I think part of it's because we are trying to pull them apart, right? And try to come up with these perturbation experiments that isolates one impact or the other. And so I don't think it's been mentioned here, but I just wonder if, and I know, Nicole, maybe this is something you were thinking about saying or not, I don't know, but she can't respond right now. But it's like, is there any potential for kind of, okay, I think we need an analysis technique that would be ideal if there's a way we could do it from the coupled simulation itself without having to try to pull it apart. So can we use something like a machine learning type approach that might be able to use the coupled simulation itself and pull apart just from many, many model runs and all that model output to isolate these different factors? So could machine learning help us here?
Yeah, I would definitely favor any approach that doesn't require these like idealized or artificial experiments where you can just look at like the CMIP5 ensemble or the CMIP6 ensemble or something. Yeah, like any statistical technique, it could be machine learning, it could be even something more basic. But yeah, I think some thought should be put into how sea ice effects can be diagnosed just directly from CMIP experiments that are already run.
I think we would need both some statistical methods like what I mentioned, the causal inference. I think it's really powerful. We can use it for observations, but also for coupled model runs to try to disentangle different processes. But the experiments are ways to verify or even to identify what variables needs to be probed in machine learning or statistical methods.
Okay, thanks, everyone. I think we're running into break time here, so let's thank our speakers again.